Hello there, and welcome to the Sleepy Science Channel. Tonight, we are stepping beneath the emerald canopy of the rainforest, where sunlight arrives in scattered ribbons, and the air holds the scent of leaf, soil, and rain. This is a living architecture of layers and movement, built from trunks and vines, mist and canopy, and a steady pulse of water cycling between the ground and sky. In these vibrant ecosystems, life is always in a state of flux. Roots trade nutrients in darkness, insects write invisible paths along bark, and distant calls travel through green corridors that seem to stretch forever. The rainforest can feel like a single organism, breathing out moisture, drawing in heat, and shaping storms far beyond its own borders. There is always more happening than the eye can catch, and that is part of the wonder. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Allow your body to soften, allow your breathing to slow, and let the day gently fade away as we wander through the rainforest together. Let's begin. There are leaves in the rainforest large enough to shelter an entire child. Some plants grow leaves so monumental that they seem designed for giants. Broad and smooth, they spread out like natural roofs that catch falling rain and sunlight. In storms, water cascades from their wide surfaces in steady streams. In gentle weather, they create dry havens beneath their shade. These enormous leaves often grow on plants that live close to the forest floor. Because sunlight is precious down there, each leaf expands to capture as much as possible. Animals use them as platforms, nurseries, or shields. Frogs lay eggs in the pools that gather on their surfaces. Insects hide along their ribs. Even small mammals may rest beneath their protection. Despite their size, the leaves remain delicate, adjusting their angle to shed water or reduce wind pressure. Their surfaces often carry patterns that reveal how nutrients travel through the plant. To encounter one is to feel the scale of rainforest growth, where nature shapes objects both massive and intricate with equal care. Some trees only bloom once every few decades, in perfect synchrony. Across vast stretches of forest, thousands of trees can burst into flower at the same moment, even though years may have passed since their last display. Each individual waits in silent readiness, sensing subtle cues in temperature, rainfall, and light. When the moment arrives, the canopy transforms into a sea of blooms that perfume the air and attract clouds of pollinators. This rare synchrony overwhelms animals that might feed on the flowers or seeds, ensuring that enough survive to sustain future generations. For a brief period, the forest becomes a festival of color that can be seen from above as a sweeping wave of brightness. Animals migrate toward the blooming zones, feeding on nectar that appears only once in a lifetime for some species. Afterward, the petals fall like soft rain, covering the forest floor. The trees then return to patient waiting, counting silent years until the next shared awakening. Rainforest plants communicate through underground fungal networks. Beneath the soil lies a hidden web of threads that connect the roots of countless plants. These fungal strands act as silent messengers, carrying signals from one organism to another. When a plant senses danger, it can release chemical warnings into this network. Nearby plants respond by strengthening their defenses even before the threat reaches them. Nutrients also travel across these pathways. A strong tree may share resources with a struggling seedling, helping it survive until it can gather enough light. This underground communication creates a sense of cooperation that shifts constantly as the environment changes. Every connection is alive with information, weaving plants into a community, rather than leaving them to fend for themselves. The network expands as roots grow and contracts when soil dries. It forms an ever-changing map of life just below the surface, hidden from view yet essential to the health of the rainforest. There are frogs so small they can sit on a fingernail. In the rainforest undergrowth, tiny amphibians live within spaces that larger creatures never notice. Their bodies are no bigger than the tip of a pinky finger, light enough to rest on a single raindrop-soaked leaf without bending it. These miniature frogs slip into pockets of moss where moisture gathers in perfect balance. Each droplet becomes a shelter, a hunting ground, and sometimes even a nursery. Their voices are surprisingly loud for their size, rising from the leaf litter as high-pitched calls that blend with the hum of insects. Because they are so small, they rely on camouflage rather than speed. Their skin patterns mimic the speckles of fallen leaves or the mottled texture of bark. Scientists who study them must move slowly and listen carefully, because spotting one often feels like watching a leaf come alive. Their existence reminds us that rainforests are shaped not only by towering trees, but also by creatures delicate enough to disappear between grains of soil. A single jungle tree can be home to more than 2,000 species. In the jungle, a single tree can hold an entire world of life. From its roots deep in the soil to the highest leaves brushing the canopy, countless creatures find shelter. Ants march along the bark, weaving invisible highways. Birds build nests in the branches, while frogs hide in pools of water caught between the leaves. Epiphytes, plants that grow upon other plants, turn the tree into a vertical garden, creating more homes within its crown. Microbes, fungi, insects, mammals, and reptiles can all depend on that one living pillar. Scientists estimate that in some tropical forests, a single large tree can support more than 2,000 distinct species, each one interacting with the others, in ways we are still trying to understand. A single trunk becomes not just a plant, but a city, alive, interconnected, and humming with hidden dramas. The Amazon jungle produces its own rain. The Amazon is often called the lungs of the planet, but it is also a maker of storms. Every tree releases moisture into the air through its leaves, the process known as transpiration. With more than 400 billion trees across the basin, the amount of water vapor rising skyward each day is staggering. That vapor cools, condenses, and returns as rain, falling back to nourish the very forest that created it. Scientists believe that almost half of the Amazon's rainfall is recycled this way, sometimes raining down multiple times before finally drifting away. In effect, the jungle waters itself, sustaining its own abundance. The scale of this cycle is so immense that satellites have tracked vast plumes of moisture drifting from the Amazon into neighboring regions, showing how one forest helps to shape the weather of an entire continent. Some jungle vines can grow over 200 feet long. In the competition for light, jungle plants will do whatever it takes to reach the sun. Vines, known as lianas, use the strength of trees as ladders, climbing ever upward. Some of these woody vines grow so long they can stretch for more than 200 feet, curling and looping through the canopy like natural ropes. They connect tree to tree, creating bridges for monkeys, sloths, and even leaping frogs. In storms, they can act like anchors, binding multiple trees together and reducing the chance of collapse. But vines also steal resources, sometimes strangling the very trees they climb. The sight of a single liana can be breathtaking, a living cord, thicker than a person's arm, looping endlessly toward the light above. Each one is a reminder of how fierce and creative life can be in its search for survival. There are fish that can climb trees in the jungle. In the flooded forests of the Amazon, some fish have learned to break the boundaries of water. Known as climbing catfish, or sometimes as armored catfish, these small creatures have specialized fins and mouths that allow them to cling to rocks, roots, and even the trunks of trees. When water levels rise during the wet season, these fish are carried into the forest. As the floods recede, Some are left behind in shallow pools. To survive, they climb their way back toward the rivers, gripping bark and slipping between roots with surprising skill. Watching a fish make its way up a tree is both surreal and mesmerizing, a reminder that the jungle is full of adaptations that blur the line between worlds. Here, nothing is entirely fixed. Even a fish may learn to travel where it should not belong. Some rainforest animals glow in the dark. As night settles over the canopy, lights begin to appear that do not come from the sky. Certain insects shine with gentle pulses, forming drifting constellations beneath the branches. Some fungi emit soft green halos across fallen logs. Even a few mammals produce faint glimmers that shimmer when disturbed. These glows come from chemical reactions within their bodies that release tiny flashes of energy. They can use light to attract mates, warn predators, or communicate with their own kind. In deep darkness, the glow becomes a secret language painted across bark and leaves. Each species creates its own pattern, revealing itself only to those who know how to read the soft radiance. To walk through these forests at night is to feel as though the stars have descended and scattered themselves across the living earth. Bioluminescence remains one of the rainforest's most mesmerizing mysteries, hinting at hidden processes that continue whether humans witness them or not. Some butterflies drink the tears of turtles. Near riverbanks, butterflies gather around turtles resting in the sun. They approach cautiously, fluttering close to the corners of the turtle's eyes. Turtles often excrete small amounts of salty fluid, and butterflies rely on these minerals to help balance their diet. The relationship is harmless and has become a delicate dance between two very different creatures. The gentle weight of the butterflies rarely disturbs the turtles, who continue to bask while their visitors sip the precious droplets. This behavior reveals how resources are shared in unexpected ways within the rainforest. Even something as small as a tear becomes an opportunity for survival. These interactions highlight the subtle interdependence among species, where moments of stillness and vulnerability give rise to connections that sustain life across diverse worlds. The rainforest hides spiders that build webs large enough to catch birds. In the dim spaces between branches, enormous webs stretch across open air like shimmering nets. Their silk threads glisten with tiny droplets that highlight the patterns woven with exceptional strength. These spiders create structures wide enough for small birds to brush against while flying. Though they rarely trap birds, the possibility exists because the webs are strong and strategically placed. Insects are their usual prey, but the size of the web grants them access to a greater variety of food. The spiders themselves are striking creatures with colors that stand out in the filtered light. They wait at the center of the web, motionless, sensing vibrations through delicate legs. Each tremor tells a story about what has entered their trap. Despite their size, these spiders play essential roles in balancing insect populations and maintaining the health of the ecosystem. Their presence reminds us that the rainforest contains marvels both beautiful and unexpected. Sloths grow algae in their fur and carry entire mini ecosystems. The thick fur of a sloth forms grooves that collect moisture, creating ideal conditions for algae to grow. This green tint helps sloths blend with the canopy, making them difficult for predators to spot. Within their fur live not only algae, but also insects and fungi that rely on the microclimate the sloth provides. Some moths spend their entire life cycle within this moving habitat. As sloths descend to the ground to defecate, the moths lay eggs in the soil. When the young hatch, they crawl back into the fur, continuing a relationship that has existed for ages. The algae may offer nutrients when sloths lick their fur during grooming. Together, these interactions form a tiny world that travels slowly through the branches. Sloths embody the rainforest's theme of interconnected life, showing how even a single animal can host a community within its gentle movements. more species are found in jungles than in all other biomes combined. When scientists speak of biodiversity, jungles sit at the very top of the scale. These green realms cover only a small fraction of Earth's surface, yet they harbor more than half of all known species. Birds, mammals, amphibians, reptiles, insects, plants, fungi, and microorganisms. The list seems endless. New species are discovered every year, many of them tiny and easily overlooked, yet each one is part of the greater web of life. No desert, grassland, or ocean matches the density of living forms concentrated here. In one patch of forest, no larger than a city block, researchers have catalogued hundreds of tree species, thousands of insects, and countless other forms of life. It is staggering to realize that the majority of the world's living diversity is concentrated in jungles, a reminder that these ecosystems are not just rich, but irreplaceable. Some jungles are so loud they rival a city in volume. Step into a jungle at dawn or dusk, and the soundscape is overwhelming. Birds cry from every direction, insects trill in constant rhythm, frogs croak in unison, and unseen mammals call across the trees. Together, this chorus creates a wall of sound that can rival the noise level of a busy city. Scientists who have measured jungle soundscapes with sensitive instruments have recorded decibel levels similar to those of traffic or bustling marketplaces. Yet unlike human noise, jungle sound is layered, patterned, and alive. Each call has its place. Some creatures sing at higher frequencies, others at lower, leaving room for all to be heard. For the animals, sound is survival, a way to claim territory, attract mates, or warn of danger. For us, it is a reminder that these forests are never still, always speaking in a language of endless life. There are plants that can walk slowly across the forest floor. Among the most unusual plants of the jungle is the so-called walking palm. Its roots grow not just downward, but outward in stilt-like formations. If a tree is shaded or needs more light, new roots sprout on the side closer to the sun, while older roots on the darker side wither away. Over time, the entire tree appears to shift, inch by inch, across the ground. Scientists debate how much a walking palm can actually move, but many believe it may shift several feet over the course of its life. To stand before a tree that seems capable of changing its place in the world is both unsettling and wondrous. In the jungle, even the seemingly immobile can find ways to move, adapting endlessly to the struggle for sunlight. The canopy holds hidden lakes of rainwater high above the ground. The jungle canopy is more than a roof of leaves. In its folds and hollows, water collects and lingers. Bromeliads, with their rosette-shaped leaves, create pools that sit high in the air, suspended above the forest floor. These tiny lakes, no larger than a bowl, can house entire ecosystems. Frogs lay their eggs in them, insects swim through their waters, and even small crabs and snails may make their homes there. To a creature that never descends to the ground, such canopy pools provide everything needed for life. From the outside, the jungle may look like a single, endless sea of green. But inside, every level is a world of its own, complete with rivers, lakes, and hidden habitats, stacked layer upon layer. From the roots underground to the water, filled leaves above. Some rainforests flood so deeply that fish swim among the trees. During certain seasons, water rises slowly through the forest until the ground disappears beneath shimmering pools that stretch for miles. The trunks of towering trees become pillars in a vast submerged world, their roots hidden under calm currents. Fish glide through these underwater corridors as if drifting through an ancient city. They feed on fruits that fall from the branches above, nibbling at seeds and soft pulp. Some species time their migrations with the floods because the expanding waterways provide access to new feeding grounds, birds adjust their hunting strategies, diving into the water between branches. Monkeys watch the shifting landscape from high perches, waiting for the waters to recede. The transformation is so complete that it is easy to forget that dry forest lies beneath the surface. When the flood finally retreats, it leaves behind nutrient-rich sediment that nourishes the entire ecosystem. This cycle reveals how fluid rainforest life can be, adapting with grace to the slow rise and fall of water. The Amazon River carries more water than the next 7 largest rivers combined. This immense river moves with a steady force that shapes the entire landscape surrounding it. Its current is wide and powerful, carrying minerals, seeds, and drifting logs through channels that weave across continents. Many tributaries feed into the main river, gathering rain collected from forests that stretch beyond the horizon. The volume of water is so great that fresh water from the river pushes far into the ocean, creating a plume visible from high above the earth. Within its depths live countless species of fish, some found nowhere else. River dolphins navigate its murky waters using subtle sound patterns. Flooded forests depend on its rise and fall, responding to rhythms that have continued for countless generations. Traveling along its surface feels like moving across a living artery that nourishes everything it touches. The river carries stories of distant mountains, passing them onward to the sea while feeding the rainforest with every surge. Rainforests create their own rain by breathing out moisture. Each leaf in the forest releases tiny droplets of water vapor into the air through a process that turns sunlight and stored water into mist. When millions of leaves do this all at once, the air above the canopy becomes saturated with moisture. Warm currents lift the vapor skyward until it cools and condenses into clouds. Eventually, these clouds release rain that falls back onto the forest, completing a cycle that depends on every plant from the tallest tree to the smallest shrub. This self-made rainfall helps maintain the constant humidity that rainforest life requires. Animals rely on this moisture for drinking water, cooling, and shelter. Even the soil benefits because repeated rains wash nutrients into layers where roots can reach them. What begins as a whisper of vapor from a single leaf becomes part of a vast atmospheric engine. In this way, the rainforest truly breathes, exhaling clouds that return as life-giving rain. Some rainforest trees grow so tall they pierce the clouds. High above the forest floor, these towering giants lift their crowns into layers of mist, but never touch the ground. Their trunks rise for what feels like forever, carrying entire communities of mosses, orchids, insects, and birds along with them. In the upper reaches, the air feels different, cooler and washed with drifting silver clouds. Creatures that live in these heights may never descend, spending their entire lives in a world far above the soil. The immense strength of these trees comes from deep roots that lock into ancient earth and wide buttresses that anchor them through storms. Each trunk records centuries of shifting seasons, quiet floods, and distant lightning. Some of these trees were already old when the first human stories were told. They serve as pillars of life, holding up the green architecture of the rainforest and creating safe pathways for gliders, monkeys, and wind-carried seeds. To stand beneath one is to feel the presence of time itself, stretching upward beyond sight. Some jungle trees release chemicals that create clouds. High above the canopy, chemistry begins to shape the sky. Some trees release tiny organic compounds into the air, invisible to the human eye. Once aloft, these molecules interact with sunlight and other particles, forming microscopic aerosols. These aerosols act as seeds for cloud droplets, helping water vapor condense into visible clouds. In this way, the trees themselves influence the weather, summoning shade and rain from the air. Satellites have captured plumes of these tree ball emissions drifting above the Amazon and the Congo, showing how forests breathe not only oxygen, also the very materials of clouds. It is astonishing to think that a stand of trees can alter the sky, bending the atmosphere toward rain. Jungles are not only rich in life, they are engines that sculpt the climate above them. A single square mile of jungle can contain more than 50,000 insect species. Insects dominate the jungle in both numbers and diversity. A single square mile of tropical forest can contain more than 50,000 distinct species of beetles, ants, flies, moths, and countless others. Many of these creatures are still unnamed, existing only as fleeting encounters between researcher and specimen. To walk through the forest is to pass by an endless parade of forms, from jewel-bright beetles that glitter like metal to camouflaged insects that vanish into bark or leaf. The sheer abundance is almost beyond comprehension. Insects pollinate flowers, recycle nutrients, feed larger animals, and shape the forest in ways both subtle and immense. Every tree, every leaf, every drop of water is alive with them. The scale of insect diversity in jungles is not just remarkable, it is one of the greatest concentrations of life anywhere on Earth. Certain jungle ants farm fungi underground. In the hidden chambers beneath the jungle floor, some ants have become skilled farmers. Leafcutter ants collect pieces of fresh greenery, not to eat directly, but to carry back to their underground nests. There, they chew the leaves into pulp and cultivate a special fungus that grows only within their colonies. This fungus becomes the ant's primary food source, tended with care and protected from contaminants. Workers prune away unwanted molds, while others bring in new leaves to feed the fungal garden. The scale of these operations can be astonishing. A single colony may contain millions of ants and vast networks of tunnels. Long before humans learned to farm crops, these tiny insects had already mastered agriculture. Their hidden gardens are some of the most sophisticated examples of cooperation in the natural world. Poison dart frogs carry enough toxin to kill large animals. Brightly colored and no larger than a thumb, poison dart frogs are among the most striking creatures of the jungle. Their brilliant hues, yellow, blue, green, or red, are warnings, signals of the danger they carry within. Some species possess enough toxin in their skin to kill a large animal, or even several humans. Indigenous peoples of South America once used these potent chemicals to tip the points of hunting darts, giving the frogs their name. The toxins are not produced by the frogs themselves, but are derived from the insects they eat, concentrated and stored in their bodies. What makes them extraordinary is the delicate balance of survival they represent. Fragile in size, yet equipped with one of the most powerful defenses in nature. A tiny frog, luminous under the canopy's shade, becomes a living symbol of the jungle's beauty and danger. The rainforest canopy is a suspended world with its own weather. Far above the forest floor lies an airborne realm where sunlight pools in golden sheets and warm breezes drift between leaves that rarely touch the ground. This living ceiling is a labyrinth of branches, vines, and hidden hollows. Animals move through it as easily as others walk along Earth. Up here, moisture gathers in pockets that become tiny fogs. Rain can fall inside the canopy without ever reaching the soil. Entire storms may be softened into gentle showers before they descend. The temperature can rise and fall independently of the world below because sunlight collects on broad leaves that warm the air. Plants take advantage of this unique climate, spreading wide crowns to catch light and channel water into reservoirs that feed creatures who never descend the Pell. Trunks. Scientists describe this space as a floating city built by nature, rich with life that most people will never see. Every gust of wind rearranges it, yet the structure endures through centuries of change. Beneath the canopy lies a dark, humid realm few creatures ever leave. Down below the bright roof of leaves is a shaded world where the air remains heavy and still. Sunlight struggles to reach the ground, creating a place where dusk lasts all day. Plants grow slowly here, stretching patiently toward rare beams of light. Animals that dwell in this zone have adapted to near darkness. Some rely on scent instead of sight. Others move silently through damp litter that blankets the ground. The soil itself feels alive as insects, worms, roots, and fungi weave through it in constant motion. Fallen fruit decay quickly in the warmth, releasing rich nutrients that feed an entire community of hidden organisms. Every step is soft, cushioned by centuries of leaf fall. To creatures that live here, the forest floor can feel like a different planet compared to the canopy above. Many never climb upward because they have become experts at navigating the shadows, thriving in a place shaped by quiet and depth. In some rainforests, tree roots climb rather than dig. Instead of burrowing into the soil, certain trees send their roots upward and outward, gripping the surface of trunks and rocks like living hands. These unusual roots spread across bark in delicate lattices that look almost like lace. They help the tree capture moisture from mist rather than water from the ground. This strategy allows life to grow where soil is thin or entirely absent. Some roots creep toward pockets of light, forming bridges that connect one tree to another. Others coil around their host in spirals that support the entire structure through storms. These climbing roots also provide homes for countless tiny organisms. Ants, spiders, beetles, and even small frogs find shelter within the grooves and tunnels they form. Because they are exposed to the air, they pulse with the humidity of the forest and become pathways for nutrients that move across the outer skin of the tree. This remarkable adaptation shows how inventive rainforest life can be when seeking new ways to survive. Epiphytes create floating gardens in the sky. High above the ground, these remarkable plants take root not in soil, but on the branches of towering trees. They live suspended in air, catching moisture from mist and nutrients from drifting dust. Some form thick mats that cradle entire communities of insects and frogs. Others gather water inside natural basins formed by their leaves. These small pools become nurseries for tadpoles and drinking stations for birds. Epiphytes add layers of texture to the canopy, creating miniature forests above the main forest. Orchids, bromeliads, and mosses weave together into lush clusters that shimmer when dew settles on them. They do not harm the trees that host them. Instead, they use height to reach sunlight that would never touch the forest floor. Their presence helps shape the canopy into a vibrant world filled with life and color, resting gently on the shoulders of ancient giants. The Amazon has more than 400 billion individual trees. Stretching across 9 countries, the Amazon jungle is home to an almost unthinkable number of trees. Scientists estimate there are more than 400 billion individuals, representing over 16,000 species. Each tree is a world unto itself, supporting vines, orchids, insects, and countless other organisms. Together, they create the largest continuous canopy on Earth, a living roof that spans millions of square kilometers. These trees regulate global climate, storing vast amounts of carbon and producing moisture that feeds weather systems far beyond South America. To grasp the scale, imagine counting one tree every second. It would take more than 12,000 years to finish. The Amazon is not just a forest. It is an unfathomably vast assembly of living beings, a green expanse so immense that even satellites struggle to capture its entirety. Some jungle flowers open only once every several decades. Hidden deep within tropical forests are plants whose lives unfold on timescales far beyond our own. One of the most mysterious is the giant Titan arum, sometimes called the corpse flower for its overwhelming odor. This colossal bloom can take decades to store enough energy to flower. When it finally does, the event lasts only a few days, releasing a smell of rotting flesh to attract pollinating insects. In the jungles of Southeast Asia, another flower, Rafflesia, opens into a massive red blossom that can be 3 feet across, also appearing only rarely. These plants seem to measure time differently, waiting years, even lifetimes, before revealing their astonishing blooms. To encounter one is to witness a fleeting miracle, the jungle pausing for a brief dramatic spectacle before returning to its hidden rhythms. In jungles, vines can strangle fully grown trees to death. Competition for sunlight in the jungle is fierce, and some plants take ruthless approaches to survival. Strangler figs begin life as seeds dropped by birds onto the branches of other trees. From there, they send roots downward, wrapping around the host's trunk. Over time, the fig's roots thicken into a lattice, tightening their grip while drawing nutrients and blocking sunlight. Eventually, the host tree weakens and dies, leaving behind a hollow column of fig roots that have fused into a new trunk. What begins as a delicate seedling perched high in the canopy ends as a towering fig that has consumed its host. This dramatic transformation is a reminder of how survival in the jungle is not always peaceful, but often a matter of slow, inexorable conquest. A jaguar's bite can crush through a turtle's shell. The jaguar is the largest cat of the Americas and one of the most formidable predators in any jungle. Unlike lions or tigers, which usually target soft areas when hunting, the jaguar has an unusually powerful bite. Its jaw muscles and skull are built for strength, allowing it to pierce through the armored shells of turtles with ease. This unique ability sets it apart from other big cats, enabling it to feed on prey that would be inaccessible to most predators. Jaguars often hunt silently, swimming across rivers or stalking through dense undergrowth, before delivering a single crushing bite to the skull or shell of their target. Their power is extraordinary, but it is paired with a quiet elegance, a reminder of how strength and stealth combine in the jungle's apex hunters. Some trees survive by strangling others from the top down. Beginning life high in the branches of a host tree, these seedlings send roots downward through open air until they reach the soil far below. Once anchored, the roots thicken and wrap around the trunk that once supported them. Slowly, patiently, the gripping lattice tightens, limiting the host tree's growth and eventually surrounding it completely. As the original tree weakens, the newcomer rises in strength, building its own trunk and branches. Over many years, the host may disappear entirely, leaving a hollow column where its body once stood. Animals use the resulting structure as shelter, climbing inside the empty spaces created by this transformation. Though dramatic, this process is not driven by malice. It is simply one of many strategies evolved to reach sunlight in a crowded forest where life competes for every beam. When the tallest trees fall, entire light gaps bloom into jungles. A single fallen giant can reshape the landscape for decades. When it crashes to the ground, the canopy opens and sunlight pours into a space that has known dimness for generations. Seeds waiting silently in the soil suddenly awaken. Young plants surge upward in a race toward the new brightness. Vines stretch across the open air. Shrubs and saplings cover the ground in a patchwork of green. Animals flock to the opening because flowers and fruits appear quickly in the warm light. Birds hunt insects stirred from the soil. Small mammals explore the fresh pathways created by the fallen trunk. Over time, this light gap becomes a nursery for the future canopy, filled with fast-growing pioneers that prepare the way for slower, longer-lived species. Eventually the gap closes again, but the forest remembers the moment through every tree that rises from that brilliant burst of renewal. Jaguars have been known to swim across flooded forests. During seasonal rains, rivers swell until they spill into the forest, blurring the line between land and water. Jaguars navigate this changing world with powerful strokes, gliding between trunks that rise from the flood like pillars. Their muscles ripple beneath patterned fur as they move with calm assurance through dark pools. Unlike many big cats, jaguars enjoy water and use it to their advantage when hunting. They slip silently beneath low branches, listening for the splash of fish or the movement of caiman. Climbing is effortless for them, so they can shift from swimming to leaping onto a low branch in a single motion. Their paws make almost no sound when they reach the bank again. These journeys show how adaptable jaguars are in an environment that transforms dramatically from season to season. Water shapes their world, yet they remain graceful and sure in every form of movement the rainforest demands. There are birds in the rainforest that can mimic almost any sound they hear. Deep within the trees, some species possess extraordinary vocal talent that allows them to imitate a vast range of noises. They can reproduce the rhythm of dripping water, the call of other birds, or the rustle of branches swaying in the wind. Some even echo the sounds of distant animals they rarely encounter. Their ability comes from complex voice structures that vibrate in fine, controlled layers. Young birds learn through careful listening, matching tones with incredible precision. Mating displays become performances in which they showcase the full range of their mimicry. These displays attract mates and also signal territory to rivals. Within their songs lies a living archive of the sounds of the forest, because each generation carries patterns they learned from previous ones. When they call, the rainforest itself seems to speak in many voices at once, blending memory and presence into a single flowing melody. Some jungle plants can sense touch and curl away from it. Not all jungle plants are passive. The sensitive plant, known scientifically as Mimosa pudica, responds dramatically to contact. When touched, its feathery leaves fold inward within seconds, collapsing as though retreating from harm. This movement is caused by rapid changes in pressure within the plant's cells, shifting water in and out to create motion. The effect is so striking that it seems almost animal-like, a plant visibly reacting to the world around it. Scientists believe the behavior helps deter herbivores and reduce damage from heavy rain or falling debris. To brush against a cluster of these plants in the jungle is to witness something uncanny. Greenery that does not simply endure, that responds, recoils, and defends itself in the moment. Termite mounds in jungles can be taller than people. Beneath the surface of the jungle, termites work in colossal societies. These small insects gather soil, saliva, and plant matter to construct towering mounds that can rise higher than an adult human. Inside, the architecture is astonishingly complex, with tunnels, chambers, and ventilation shafts that regulate temperature and humidity. Some mounds are so vast that they can house millions of termites, functioning like superorganisms with specialized castes for workers, soldiers, and royalty. From the outside, they look like strange earthen sculptures blending into the landscape. But within, they are bustling with life, organized and precise. These structures show how even the tiniest creatures can shape their environment on a monumental scale, leaving marks on the jungle that can last for decades, or even centuries. The humidity in jungles can be close to 100%. Walking into a jungle is like stepping into a living cloud. The air is heavy with water vapor, clinging to skin and filling every breath. In some regions, humidity levels approach 100%, creating an atmosphere that feels almost liquid. This constant dampness shapes every aspect of jungle life. Leaves grow large with pointed tips to shed water. Animals adapt to thrive in endless moisture, from frogs whose skin must stay wet to fungi that flourish in the damp shadows. For humans, the sensation can be overwhelming. Sweat does not evaporate, clothing clings, and the air itself seems to press down with weight. Yet for the organisms that live here, such conditions are perfect. The jungle is not just wet from rainfall, it is wet from the very air, a place where moisture is as constant as the green. Some jungles have rivers that boil. Deep in the Peruvian Amazon flows a river unlike any other, known locally as Xanatimpixca. meaning boiled with the heat of the sun, its waters reach temperatures hot enough to cause serious burns. Stretching for several miles, this river appears to bubble and steam as if fed by volcanic springs. Yet it lies far from any volcano, leaving scientists puzzled. The heat is thought to come from geothermal activity deep underground, where rainwater seeps into cracks and is superheated before rising back to the surface. Local legends tell of spirits guarding the river, while modern research marvels at its uniqueness. To stand at its banks is to witness a phenomenon so rare that few places like it exist on Earth, a boiling river hidden within the jungle, where water becomes a Z, dangerous as fire. Some ants grow entire fungal gardens underground. Beneath the forest floor, there are chambers carved through soil, where colonies cultivate fungus with remarkable care. The ants gather leaves, clean them meticulously, and use them as a base for the fungus to grow. Workers tend these gardens day and night, trimming away damaged sections and feeding fresh plant matter to the expanding network. The fungus provides nourishment to the colony, and in return the ants protect it from pests and competing organisms. Paths extend from the nest into the surrounding forest, forming complex routes used for harvesting. Each trail reflects the colony's needs at that moment. The underground gardens remain warm and humid, maintained through precise airflow created by the arrangement of tunnels. These living farms have existed for countless generations, evolving alongside the ants. Observing them reveals a partnership so refined that no part of the colony survives alone. Together, they form one of nature's oldest examples of agriculture. There are monkeys that howl so loudly you can hear them miles away. Howler monkeys use deep, resonant calls that roll through the rainforest like distant thunder. Their enlarged voice boxes and specialized throats allow them to project sound across vast distances. At dawn and dusk, groups communicate their location to others, reducing conflict by letting neighboring bands know where they are. The calls vibrate through leaves, drift along rivers, and rise through the canopy. Hearing them for the first time can be startling because the sound is powerful enough to seem much closer than it is. Despite their fierce voices, howler monkeys often lead calm, slow-paced lives. They rest for much of the day, conserving energy by eating leaves that offer little fuel. Their vocal strength contrasts dutifully with their gentle movements. They play a crucial role in seed dispersal, helping young plants take root far from their parent trees. Electric blue frogs live among fallen leaves, warning predators with their brightness. Their vivid coloration announces their presence boldly, signaling to potential predators that they do not make easy prey. These frogs carry natural toxins produced through their diet of ants and small insects. The brilliance of their skin reflects sunlight in a way that catches the eye even in dim undergrowth. Despite their size, they play a significant role in controlling insect populations. Their calls are soft compared to their striking colors, forming gentle chirps that blend into the background. They raise their young in small pools of water held within plants, transporting tadpoles one by one to safe nurseries. Every movement they make reveals a balance between vulnerability and strength. Their presence adds flashes of color to the forest floor, turning the quiet world of fallen leaves into a landscape of tiny wonders. Some rainforest clouds are born from the trees themselves. When sunlight warms the canopy, it releases scents, oils, and moisture into the air. These invisible particles rise and begin to gather, attracting water vapor that clings to them. As more vapor collects, small droplets form and slowly merge into clouds. These newborn clouds drift above the forest, sometimes staying low enough to brush the leaves, sometimes rising high into the sky. Their shapes change constantly, shaped by the movement of warm air rising from the forest below. When conditions align, these tree-borne clouds contribute to local storms that water the land. This process shows how closely the atmosphere and the rainforest are intertwined. The forest does not simply exist beneath the sky. It participates in shaping the sky. Each cloud that forms carries a trace of the leaf, bark, and breath of the forest, turning the air into a canvas painted by living trees. The forest floor can be so dark that few plants grow there. Beneath the thick ceiling of leaves, sunlight struggles to touch the ground. In some jungles, less than 2% of daylight ever reaches the forest floor. The result is a shadowed world, humid and quiet, where very few plants can grow. Instead of green carpets, the ground is often bare, layered only with fallen leaves and the roots of towering trees. The lack of light forces life to adapt in unusual ways. Seedlings may wait years, even decades, for a gap in the canopy to open, suddenly racing upward when a tree falls. Animals take advantage of the dimness, moving softly and unseen. It is a world of patience and shadows, where growth is measured in moments of opportunity and where survival often depends not on abundance, but on waiting for the light car to break through. Certain trees can communicate with each other through fungi. Hidden beneath the soil lies a network as complex as any highway system. Tiny filaments of fungi connect the roots of different trees, allowing them to share signals and even resources. Through this wood-wide web, trees can warn neighbors of insect attacks or send nutrients to weaker companions. In the jungle, where life is densely packed and competition is fierce, this underground network adds another layer of cooperation and complexity. A towering tree may funnel energy to its own seedlings, giving them a better chance to survive in the dim forest floor. Others may transmit chemical messages that trigger defenses in nearby plants. To know that trees are not isolated beings but parts of a vast hidden conversation changes how we see the jungle, not as a collection of individuals, but as a living community whispering through the soil. Some jungle bats pollinate flowers at night. When the sun sets and the forest darkens, bats take flight. While many hunt insects, some species specialize in sipping nectar from jungle flowers. With long tongues and sensitive noses, they hover at blossoms, dusting themselves with pollen before moving on to the next. By morning, entire stands of plants may have been pollinated, all thanks to these night-flying mammals. In places like Central and South America, bats are essential for crops such as bananas, guavas, and cacao, the source of chocolate. Their work sustains not only the jungle's wild plants, but also foods that humans rely on. The relationship is delicate. Flowers often open only at night, releasing scents that draw bats to them, perfectly timed for these nocturnal visitors. In the unseen hours, while most of the forest rests, bats quietly knit together the cycles of life, one sip of nectar at a time. The harpy eagle has talons bigger than a grizzly bear's claws. High in the canopy lives a predator as awe-inspiring as any jungle cat, the harpy eagle. With a wingspan stretching more than 7 feet, it is one of the largest and most powerful eagles in the world. But its most extraordinary feature is its talons. Each one can be up to 5 inches long, larger than the claws of a grizzly bear. With this incredible grip, the harpy eagle can snatch monkeys and sloths directly from the branches, carrying them away in powerful flight. Despite their size, these eagles move with astonishing agility, weaving through the trees with precision. They are rare and elusive, often glimpsed only briefly as a shadow overhead. Yet in that moment, the jungle reveals one of its most formidable hunters, a bird whose strength rivals that of beasts far larger than itself. Rivers in the rainforest can suddenly turn acidic from falling leaves. As leaves drop into the water and begin to decay, they release tannins that darken the river and alter its chemistry. These tannins can give the water a deep tea-colored tint and create acidic conditions that influence which species can thrive. Some fish prefer these dark waters because they offer protection from predators. Others rely on the chemical shift to trigger breeding behaviors. The acidity also affects the growth of aquatic plants, shaping the underwater landscape in subtle ways. During certain seasons, when leaf fall increases, the transformation becomes rapid. The river changes character almost overnight. This natural process has occurred for ages, maintaining balance within the ecosystem. Even predators like river dolphins and caiman adjust to the altered clarity and scent of the water. These changing conditions reveal how closely connected the forest floor and river currents truly are. A single leaf can ripple through an entire ecosystem. Trees that live in flooded forests can breathe through their bark. In areas where water covers the roots for long periods, certain trees have evolved remarkable adaptations that allow them to survive. Their bark contains specialized tissues that let oxygen pass inward even when the trunk is submerged. This ability acts like a natural snorkel, delivering air to the living cells beneath the surface. Some species grow swollen bases or flared supports that help hold them steady in the shifting currents. Others develop channels within their trunks that move oxygen downward toward the roots. These adaptations allow the trees to remain alive in conditions that would suffocate most plants. During long floods, the forest seems almost still, yet these submerged trunks continue exchanging gases with the surrounding air. When the waters finally recede, the trees resume normal growth, as though nothing unusual has happened. Their quiet resilience demonstrates how the rainforest accommodates dramatic seasonal change. The forest floor can vanish underwater for half the year. In certain regions, seasonal rains transform the landscape so thoroughly that the distinction between land and river disappears. Water rises inch by inch until the undergrowth is submerged. Plants that usually cling to soil find themselves swaying in gentle currents. Fish swim over roots that were once hidden beneath dry leaves. Birds perch on branches now reflected in still pools. Many animals adapt their behavior to this temporary world. Some retreat to higher ground while others venture into newly reachable areas. The soil beneath the water absorbs nutrients washed in by the flood, creating fertile conditions for future growth. When the waters retreat, the ground emerges renewed. Seeds germinate in the freshly enriched earth. Footpaths reappear. Small mammals return to forage. This cycle sustains the forest and shapes the lifetimes of countless species. The temporary disappearance of the forest floor reveals the fluid nature of rainforest ecosystems. Some fish migrate through forests instead of rivers. When seasonal floods spread water across the land, fish take advantage of the expanded habitat. They move through submerged undergrowth, weaving between tree trunks and fallen branches. This journey allows them to reach fruiting trees, whose offerings drop directly into the water. Many species rely on these seasonal meals to gain strength for breeding. The new roots also provide access to safe nurseries, why predators find it harder to chase them. Young fish shelter among roots and leaf litter, feeding on insects washed from the soil. As waters recede, the fish return to the main channels, carrying the next generation with them. These migrations reflect a deep connection between fish and forest. They show that boundaries between land and water shift constantly in the rainforest. When fish glide through a sunlit grove that once held walking animals, the landscape reveals its dual identity as both forest and sea. Lightning can spark wildfires even in the wettest places on Earth. Although rainforests are known for constant moisture, powerful lightning strikes can ignite dry pockets of leaves or branches that have been warmed by sunlight. Once a small flame begins, it may smolder quietly for days before conditions allow it to spread. These fires often remain low to the ground and move slowly, clearing debris without destroying the canopy. In doing so, they create space for new plants to grow. Some species even depend on occasional fire to germinate seeds or clear competition. Animals sense the change quickly and move to safer areas until the flames pass. Afterward, the forest floor bursts with fresh growth. green shoots rise through ash, and insects return to reclaim their habitats. These natural fires remind us that even in landscapes defined by rain, fire plays a role in renewal. The rainforest contains cycles shaped by both water and flame. The rhythm of rainforest rain changes with the moon. As the moon moves through its cycles, subtle shifts occur in tides, winds, and atmospheric pressure. These changes influence humidity and cloud formation over the rainforest. During certain lunar phases, rain becomes more frequent and falls in softer, more evenly spaced showers. During others, storms can build with greater intensity. Animals respond instinctively to these cycles. Frogs may call more often under certain moonlit skies. Insects emerge at times when moisture levels rise. Plants release scents or pollen that drift more easily in the damp night air. The interplay between moonlight and rainfall creates a soft heartbeat that pulses through the forest each month. This rhythm has continued for ages, guiding migrations, blooming cycles, and the quiet unfolding of night. To listen to the rainforest under a full moon is to sense a connection between sky and earth that unfolds in patterns older than memory. Some rainforest flowers bloom for a single night, then vanish forever. These rare blossoms wait through seasons of quiet growth, gathering energy until the exact conditions align. When warmth, moisture, and moonlight meet in perfect harmony, the flower unfurls in silence. Its petals glow faintly in the darkness as though illuminated from within. Sweet scents drift into the air, calling moths and other nocturnal pollinators. The bloom lasts only until dawn when the first rays of sunlight touch the petals. By morning, the flower closes forever and begins to wilt, leaving behind only a developing fruit or seed pod. This fleeting display ensures that pollinators are drawn to the moment with full attention, because the opportunity will never repeat. Some plants produce these blossoms only once in many years. Others bloom at irregular intervals that scientists still struggle to predict. Witnessing such a flower feels like watching time pause, offering a glimpse of something delicate and profound that the forest carefully guards. There are trees that bleed red when cut. In the deeper parts of the rainforest, certain trees release vivid crimson sap when their bark is pierced. The sap oozes slowly, bright against the dark trunk, spreading into patterns that resemble flowing paint. This striking color comes from natural compounds that protect the tree from insects and bacteria. The thick liquid forms a seal over the wound, preventing further damage while also discouraging animals from feeding on the exposed tissue. Many cultures traditionally use this sap in rituals or medicine because its appearance evokes a sense of life force and resilience. Despite the dramatic sight, the tree feels no pain. It simply responds to injury with a protective mechanism evolved over countless generations. Birds, insects, and small mammals sometimes investigate the scent and texture, attracted by its unusual properties. These trees demonstrate the rainforest's ability to surprise, revealing beauty even in moments of damage or stress. Certain vines grow in spirals to climb more efficiently. These vines coil upward in graceful curves, wrapping around branches and trunks in patterns shaped by light and gravity. Their spiral growth allows them to rise quickly toward the canopy without needing a thick, self-supporting stem. Each twist strengthens their hold, distributing weight evenly so they can stretch remarkable distances without breaking. As they climb, they adjust their direction based on subtle cues in the environment, reaching toward patches of brightness that filter through the leaves. Their movements are slow yet constant, shifting position day by day as they explore new footholds. Animals use the vines as pathways between trees, turning them into natural bridges woven through the forest. Some vines develop specialized structures that help them grip rough bark or smooth surfaces. The spiraling shapes they create add elegance and texture to the rainforest, forming intricate networks that connect different layers of this towering ecosystem. Some rainforest plants can trap and digest insects. In nutrient-poor soil, certain plants have evolved extraordinary strategies to survive. Their leaves form cups, sticky surfaces, or delicate jaws that lure insects with scent or glistening droplets. Once the unsuspecting visitor lands, the structure closes or holds the insect in place. Digestive fluids begin to break down the prey, allowing the plant to absorb essential nutrients. These carnivorous plants do not rely solely on insects, but the additional nourishment helps them thrive in areas where other plants struggle. Light plays a major role in guiding their behavior. Some species adjust the angle of their traps to collect rainwater without washing away potential prey. Others rely on ultraviolet patterns invisible to humans that draw insects into their reach. These plants show how life in the rainforest adapts creatively to the challenges of limited resources. Their presence adds a sense of wonder to the forest floor, reminding us that even the quietest greenery can possess surprising powers. There are seeds in the rainforest that can survive being eaten and excreted by elephants. Elephants swallow fruits whole, their powerful digestive systems breaking down pulp while leaving certain seeds unharmed. As the animals travel long distances, they deposit the seeds far from the parent tree, embedded in nutrient-rich material that helps them sprout. This journey not only spreads the species across the landscape, but also increases the chance that the seedlings will grow in a location with adequate light and space. Some seeds even require the rough passage through an elephant's digestive tract to crack their outer shells and activate germination. This remarkable partnership has evolved over ages, shaping the structure of entire forests. Without elephants, many of these trees would struggle to reproduce effectively. Their relationship demonstrates how large animals can act as gardeners of the rainforest, carrying the next generation of life through rivers, valleys, and dense undergrowth. A single rainforest tree can hold more than 1,000 different insect species. Within the branches, bark, leaves, roots, and hollow spaces of one mature tree lives a bustling world of tiny creatures. Each insect finds its own niche, from beetles that burrow into decaying wood to moth caterpillars that hide among curled leaves. Ant colonies may build nests in the trunk, while spiders weave delicate homes among the branches. Some insects feed on sap, while others graze on the algae and fungi growing along the bark. The diversity comes from the tree's ability to create numerous microhabitats, each with its own temperature, humidity, and food sources. Even the areas exposed to sunlight differ greatly from the shaded spaces near the roots. These layered environments support complex food webs where insects interact in ways that ripple outward through the entire forest. The sheer variety of life contained within one tree illustrates how densely packed rainforest ecosystems can be. There are plants that mimic the appearance of other plants to survive. These clever imitators shape their leaves, colors, and growth patterns to resemble neighboring species. By blending in, they avoid detection by herbivores that might otherwise feed on them. Some mimic poisonous plants so convincingly that animals avoid them without hesitation. Others copy the growth habit of tougher species, giving the illusion of strength they do not actually possess. Their deception extends through entire seasons as they adjust subtle traits based on the conditions around them. Even insects can be fooled, sometimes laying eggs on the wrong plant because of a well-crafted disguise. This mimicry allows the plant to conserve energy that would otherwise be spent producing toxins or repairing damage. Their survival depends on being overlooked, and the rainforest offers endless opportunities for disguise. The practice shows how life in dense ecosystems evolves through delicate balances of adaptation and camouflage. Some rainforest trees release chemicals that prevent other plants from growing nearby. To reduce competition, these trees send substances into the soil that slow or stop the growth of surrounding vegetation. These chemicals seep from roots or fallen leaves, creating a zone in which only certain species can thrive. This strategy ensures the tree has access to sunlight, water, and nutrients without battling dense undergrowth. The effect can be subtle, appearing only when seedlings try to sprout. They may fail to develop roots or wither shortly after emerging. Over time, the cleared space around the tree becomes a distinctive feature of the forest floor. Animals notice the pattern and may use the open ground as pathways or resting spots. Despite the competitive nature of this adaptation, it helps maintain diversity by shaping the distribution of plants. Each chemical interaction influences the structure of the forest in ways scientists are still working to understand. Certain rainforest fungi can control the minds of insects. These fungi release spores that land on unsuspecting insects, attaching to their bodies and slowly growing within. As the fungi spread, they release compounds that influence the insect's behavior. The insect begins to climb upward, seeking elevated places where the fungus can best release its spores. Once the insect reaches a suitable height, it attaches firmly to a leaf or twig. The fungus completes its life cycle by emerging from the insect's body and sending spores into the air. Although the process appears eerie, it forms a natural part of the rainforest's balance. Other insects, birds, and scavengers help cleanse the environment by feeding on infected individuals. Researchers study these fungi to understand how microscopic organisms can shape the behavior of larger creatures. Their complex interactions reveal a world of hidden influences where life responds to forces that operate quietly but powerfully. Some plants use ultrasonic sounds to attract pollinators. These remarkable plants emit vibrations that pulse through the air at frequencies too high for human ears to detect. Certain insects, however, can sense these signals with great precision. When they approach, the subtle hum guides them toward flowers that may be concealed by leaves or positioned in shaded areas. Once the pollinators arrive, they find nectar arranged in patterns that match the shape of their bodies. The ultrasonic vibrations may also help loosen pollen or warm the floral tissue slightly, making the bloom more inviting. This communication method allows the plant to reach pollinators even in dense forest, where visual cues can be limited. It represents a sophisticated form of interaction shaped through countless evolutionary cycles. Each transmission of sound reflects the plant's attempt to overcome obstacles of shadow and distance, drawing life toward itself by means other than sight or scent. Some rainforests are older than the Amazon River itself. In certain parts of the world, ancient forests began forming long before the Amazon River carved its first path across the continent. These forests grew during eras when Earth's atmosphere, oceans, and temperatures were profoundly different from today. Layer after layer of vegetation rose and fell across ages that stretched beyond human comprehension. As continents drifted and mountains rose, these forests adapted to shifting winds, changing rainfall, and new forms of life that appeared across the planet. Their soils became deep reservoirs of memory, built from countless generations of fallen leaves that decomposed slowly in the humid air. Within these layers lie chemical traces of climates long vanished, along with the fossilized remains of insects and plants that once dominated the landscape. Trees that live here today share ancestry with species that survived immense transitions and global transformations. When you walk beneath their branches, the stillness feels ancient, as though the forest carries the patience of time itself. These regions remind us that the rainforest is not simply a habitat, but a survivor of worlds that rose and vanished before modern ecosystems even began to form. Fossils show that ancient rainforests once grew in Antarctica. Long before the continent became encased in ice, Antarctica held forests that flourished under unique conditions of nearly continuous summer sunlight. Extended winter darkness. Deep within its rocks, scientists have discovered leaf impressions, petrified wood, and delicate structures from ferns and seed plants that once spread across a warm and humid landscape. These fossils preserve the fine textures of fronds and the intricate patterns of ancient bark, showing that life once thrived where frozen deserts now dominate. The trees grew slowly yet steadily, adapting to long periods without direct sunlight by storing energy during bright seasons. Insects likely scurried across the leaf litter, feeding on decaying material in a world that felt more like a modern rainforest than a polar continent. Studying these remnants offers insight into how climates can shift over immense spans of time. The presence of ancient forests beneath present-day ice reminds us that Earth has never been static. It breathes, changes, warms, cools, and reshapes itself again and again as life adapts in extraordinary ways. The DNA of rainforest plants holds clues to Earth's earliest ecosystems. When researchers analyze the genetic structures of plants that thrive in rainforests, they find traces of evolutionary chapters written long before humans existed. Some genes within these plants link directly to early land vegetation from a time when Earth was still experimenting with the first roots, stems, and protective coatings. Other sections of DNA reveal relationships between plants that appear dramatically different on the surface, yet share deep connections in their ancestry. These genetic signatures help scientists understand how early ecosystems functioned and how plants responded to ancient patterns of drought, flooding, volcanic activity, and atmospheric change. Some rainforest species show remarkable genetic stability through time, suggesting that their environments remained supportive and steady for millions of years. Others contain evidence of sudden bursts of evolution when climate or geography shifted in ways that forced rapid adaptation. Each leaf and seed carries an archive of information that cannot be found in rocks alone. By examining these living codes, researchers glimpse the long arc of plant evolution and the intricate history of the ecosystems that eventually shaped modern-day forests. Some insect lineages in rainforests have remained unchanged for millions of years. In the quiet spaces beneath leaves and along the bark of towering trees, there exist insects that resemble creatures preserved in ancient amber. Their body shapes, feeding habits, and life cycles mirror the forms that existed during eras when enormous reptiles roamed across warm and humid landscapes. These insects survived countless climatic shifts by retaining strategies that worked so well they required little modification. They continued pollinating plants, breaking down decaying matter, and serving as prey for larger animals just as their ancestors did in ancient forests. Modern researchers studying their behavior see patterns so old that they stretch across geological ages. The persistence of these lineages provides a living connection to ecosystems that no longer exist. When one watches a small beetle crawl across a fallen branch, it is possible to imagine the same movement taking place millions of years ago in forests now, lost to time. Their survival demonstrates how certain designs remain effective and how stable rainforest environments can preserve ancient life for astonishing lengths of time. Tropical rainforests were once the cradle of flowering plants. Deep in the distant past, when early forests covered vast regions of a warm planet, the first flowering plants began to experiment with new forms of keen reproduction. Before this moment, most plants relied on wind or water to move their spores. The arrival of flowers created new partnerships between plants and insects. These early blooms produced scents, colors, and shapes that drew pollinators toward them. As insects traveled between blossoms, they carried genetic material from one plant to another, encouraging rapid diversification. Tropical forests provided an ideal environment for this explosion of creativity because they offered stable temperatures, abundant rainfall, constant opportunities for interaction among species. Over time, flowering plants spread outward from these warm cradles into other habitats, transforming ecosystems with fruits, seeds, and intricate reproductive cycles. The modern rainforest still holds descendants of those early pioneers. Within their petals lie echoes of the moment when Earth shifted from simple plant forms to the lush diversity that now covers much of the planet. Some rainforest species trace their ancestry to when dinosaurs roamed the Earth. In remote corners of tropical forests, organisms thrive that have changed very little since ancient times. Certain ferns unfurl fronds that closely resemble fossilized leaves found in strata, dating back to eras when giant reptiles dominated the land. Some reptiles and amphibians move through leaf litter with behaviors that echo their prehistoric ancestors. Even a few insects display patterns and wing structures matching those preserved in amber from the time of dinosaurs. These species survived mass extinctions by retreating into stable, sheltered environments where humidity, temperature, and light remained steady. The rainforest acted as a refuge when global circumstances shifted violently. Today, these living relics continue their ancient routines as though untouched by the march of deep time. Observing them evokes a sense of wonder, for they offer a direct link to worlds that vanished long before humans emerged. Certain rainforest trees are living fossils from a vanished world. These trees stand as remnants of eras that predate many mountain ranges and continents in their current positions. Their leaves often follow patterns seen in fossil collections more than 100 million years old. Their seeds and cones maintain structures that reflect early experiments in plant reproduction. They flourish in small pockets where environmental conditions mimic those of their distant past. Some grow slowly in shaded ravines that preserve ancient humidity levels. Others stand on mountain slopes where temperatures remain steady throughout the year. Because they survived so long, they carry unique genetic information that helps scientists reconstruct the evolution of plant life. Each trunk rises like a pillar of memory, connecting the present to chapters of Earth's history that would otherwise remain silent. Standing beneath one of these trees can feel like entering a temple built by time itself. Rainforest sediments preserve the stories of Earth's climate past. In the quiet depths of forest ponds, in slow-moving floodplains, and beneath still waters that collect between roots, fine particles settle year after year. These layers trap pollen, spores, minerals, charcoal, and fragments of leaves that drift down from the canopy. Over centuries, they stack gently into time mimes that scientists can read like diaries. The presence or absence of certain pollen types reveals which species dominated the forest at different periods. Shifts in mineral content show how rains changed or how distant volcanic eruptions altered the atmosphere. Even tiny pieces of charcoal tell of ancient fires that moved through the forest long before written history began. When researchers draw sediment cores from these quiet places, they unravel the climate stories of thousands of years. Each layer reveals how the rainforest responded to droughts, floods, and transitions in global temperature. The sediments hold these memories patiently, waiting for those who know how to read them. The oldest known rainforest tree species may date back over 100 million years. Hidden within the vast diversity of tropical forests are species whose genetic roots reach into a time before many modern plant groups had even appeared. The ancestors of these trees lived through shifting continents, rising seas, and dramatic climate swings. Their leaves still follow patterns shaped in ancient climates, and their reproductive cycles preserve methods developed long before flowering plants reached their full diversity. These trees have endured because the rainforest offered stability across unimaginable spans of time. Within their bark lie chemical traces of ancient processes that continue even now. Their seeds fall into soil enriched by countless generations of predecessors, continuing a lineage that began when enormous reptiles still wandered the earth. To touch the trunk of such a tree is to make contact with an age so distant that it feels almost mythic. Some rainforest organisms evolved alongside extinct megafauna. Long ago, forests echoed with the sounds of enormous herbivores that fed on leaves, bark, and fruits in abundance. Many plants adapted their structures to withstand browsing by these giants. Some developed thick protective rinds around their fruit. Others grew large seeds that needed to pass through massive digestive systems before they could germinate properly. When the megafauna eventually disappeared, many of the plants survived despite losing their original partners. Their traits remain as echoes of ancient relationships. Even some insects appear to have co-evolved with these towering animals, feeding on materials created by their movements or waste. Today, these plants and insects continue to display characteristics shaped by an age that ended long before modern forests took form. They carry the imprint of interactions with creatures that no longer walk the earth, reminding us that evolution is a living map of connections that stretch far into the Dendes past. A teaspoon of rainforest soil can hold more microbes than there are people on Earth. Within a tiny scoop of rainforest, Earth lives a universe of organisms so small and so numerous that they exceed the human population many times over. Each microbe fulfills a specific role that shapes the health of the entire forest. Some break down fallen leaves into nutrients. Others form partnerships with tree roots, helping plants absorb minerals that would otherwise remain locked within the soil. Many species remain unknown to science because they cannot easily be grown or studied outside their natural environment. When researchers examine rainforest soil under powerful microscopes, they see countless shapes and movements within a single drop of moisture. Some microbes drift like floating dust. Others cling to tiny mineral grains or form delicate networks that anchor them in place. Together, they create a living foundation that supports every organism above them. Without these unseen workers, the forest would lose its ability to recycle nutrients, regulate water flow, and sustain new growth. The soil becomes a quiet world where life thrives in miniature, proving that even the smallest spaces in the rainforest hold astonishing abundance. There are fungi that live entirely inside leaves, never touching the air. These fungi spend their entire lives within the delicate tissues of leaves, weaving through microscopic spaces between plant cells. They remain invisible to the naked eye, forming intricate networks that help protect the leaf from harm. Some strengthen the plant by defending it against invading microbes. Others produce compounds that deter insects from chewing through the leaf surface. Because they never emerge into open air, they avoid drying out and remain shielded from predators. The plant benefits from their presence, and the fungi rely on the stable environment within the leaf. This partnership often lasts for the entire lifespan of the plant tissue. When the leaf eventually falls, the fungi help decompose it, returning nutrients to the soil. Their existence reveals a hidden dimension of rainforest life where entire ecosystems unfold inside spaces too small for humans to see. These fungi expand our understanding of biodiversity and show that the rainforest contains layers of life within layers of life. Some lizards change color to match the shadows of different trees. In the shifting light beneath the canopy, certain lizards possess an extraordinary ability to alter their color so they blend with the precise shade of the branch or bark they rest upon. Their skin contains specialized cells that expand or contract to adjust the mixture of pigments visible from the surface. These adjustments occur in response to light intensity, temperature, mood, and the patterns surrounding them. When a cloud drifts overhead and casts a cooler tint across the forest, the lizard subtly darkens to remain concealed. When sunlight pierces through the leaves and paints the world with warmer tones, its skin brightens. This constant adaptation allows the lizard to avoid predators and approach prey without detection. Scientists studying this phenomenon find that each species responds to specific cues that reflect its unique ecological niche. The rainforest becomes a living stage where color flows in harmony with light, shadow, and movement. Rainforest bats use sonar to navigate tangled jungle corridors. As night envelops the forest, bats take to the air with astonishing precision. They emit high-frequency pulses that bounce off branches, vines, insects, and trunks. The returning echoes form a detailed map within their minds, allowing them to move swiftly through dense vegetation without ever brushing a leaf. Each pulse reveals distance, shape, and direction, creating an ever-shifting acoustic image of their surroundings. These bats hunt moths and beetles that also fly in darkness, adjusting their flight path mid-air with remarkable speed. Some species communicate with one another through variations in their calls, coordinating movements within shared hunting territories. Their ability to navigate through such complex environments demonstrates the sophistication of echolocation. When they glide among tree trunks that twist in unpredictable patterns, they depend entirely on sound and instinct. Watching a bat weave through the forest at night is like observing a creature reading invisible pathways known only to sound and motion. The humidity inside a rainforest orchid can reach near boiling levels. Hidden within the folds of an orchid flower lies a pocket of air that can trap heat and moisture to an astonishing degree. As sunlight warms the petals, the space within becomes a sheltered chamber where humidity builds to extreme levels. This warm interior creates an ideal environment for delicate reproductive processes. Pollinators that enter the flower find themselves surrounded by thick moisture that enhances the release of scent and assists in pollen transfer. Some insects remain inside for brief periods, feeding on nectar while the orchid ensures successful pollination. The heat trapped within the bloom also discourages small predators that might otherwise damage its fragile structures. Each orchid species shapes the internal climate of its flowers with remarkable precision, adjusting the size and curve of the petals to regulate airflow. This hidden world exists only for a short time before the bloom wilts and returns its energy to the plant. Within these ephemeral chambers, the rainforest reveals another example of how nature engineers intricate environments on a scale small enough to disappear. With a closing petal, some mosses in the rainforest glow under ultraviolet light. On dim forest floors where sunlight arrives in scattered fragments, certain mosses contain pigments that emit a soft radiance when touched by ultraviolet rays. Although this glow is invisible during ordinary daylight, it becomes visible under the special wavelengths present at dawn, dusk, or during low light periods. The glow may help attract insects that assist in spore dispersal, or may protect the moss from damage caused by intense radiation. These pigments form delicate patterns across the moss surface, creating a subtle shimmer that blends with the damp earth and fallen leaves. Scientists studying these species find that each type of moss produces its own distinctive glow, almost like a quiet signature left upon the forest floor. The radiance highlights the beauty of organisms often overlooked because of their size. In the presence of ultraviolet light, these tiny plants reveal an unexpected brilliance that turns a shaded corner of the rainforest into a gentle bar, constellation of living green stars. There are centipedes in the rainforest that prey on bats. Within the darkness of caves and hollow trees, enormous centipedes climb walls with silent precision. Their legs grip even the smoothest surfaces, allowing them to position themselves just below roosting bats. When a bat drops lower or shifts to a vulnerable angle, the centipede lunges upward, using strong mandibles to seize the creature in mid-air. It coils its long body around the struggling bat until movement ceases. This surprising predator relationship shows how rainforest life can push the boundaries of what seems possible. The centipede's sensory organs help it detect heat and vibration, giving it an advantage in the darkness. Despite their impressive abilities, these creatures rarely encounter humans because they prefer hidden spaces. Their existence illustrates how predators come in many forms in the rainforest, some unexpected and astonishing. Observing such interactions deepens our understanding of food webs that operate far from daylight. In the rainforest, even water droplets can become miniature ecosystems. After a rainfall, droplets cling to leaves, branches, and delicate moss beds. Within each drop, microorganisms begin to gather. Some drift in on the wind. Others wash down from higher canopy layers. These droplets can contain entire chains of life, from tiny plankton-like creatures to microscopic predators that feed on smaller organisms. The chemistry within each droplet shifts as sunlight warms it and as nutrients dissolve from the leaf surface. Some insects rely on these droplets to lay eggs that hatch into larvae. Frogs may deposit their young in larger pools held within curled leaves. Each droplet becomes a tiny world that lasts only until it evaporates or falls to the soil. Yet in that brief time, it holds interactions that mirror larger ecosystems. Energy flows from sunlight to microbes to predators in cycles too small for human eyes to follow without specialized tools. The rainforest reminds us that life flourishes at every scale. Tiny beetles can survive the pressure of falling from a 100-foot tree. In the canopy, accidents happen constantly. Wind shakes branches. Predators scatter prey. Leaves release their grip on insects resting upon them. When a beetle tumbles from a great height, it does not break. Instead, its small size and rigid body structure allow it to ride the air, slowing its descent through a combination of lift and passive resistance. Many beetles curl their legs inward and let their body rotate gently as they fall. Some even spread microscopic hairs that increase air resistance just enough to reduce impact force. By the time they reach the forest floor, they land almost as lightly as drifting seeds. This remarkable resilience allows them to explore the canopy without fear of fatal accidents. Their ability to survive such significant falls contributes to their success in the rainforest environment, where vertical space is as important as horizontal cracras. Ground. Some butterflies have transparent wings that shimmer like glass. In sunlight, these butterflies appear almost invisible, except for faint outlines that flicker as they move. Their wings contain specialized scales spaced far apart, allowing light to pass through rather than reflect it. This transparency provides exceptional camouflage because predators struggle to track something that blends with the shifting colors of the forest. When the butterfly tilts its wings, certain angles catch the light and produce gentle flashes that look like tiny panes of colored glass. These subtle gleams are not meant to be warnings, but rather a side effect of delicate wing structure. The butterflies settle on leaves where their bodies become nearly impossible to see unless one observes the faint movement of antennae. Their presence adds an ethereal touch to the rainforest, as though fragments of the sky drift silently among the trees. At night, the rainforest sings with thousands of unseen voices. When darkness settles over the canopy, the rainforest awakens into a symphony woven from countless creatures. Frogs begin the chorus, their calls rising from pools, branches, and curled leaves that cradle beads of water. Insects respond with vibrating wings that create shimmering tones. Mammals add soft rustles as they move through the undergrowth. Even the trees contribute subtle sounds as cooling air shifts through their towering branches. The forest seems to inhale and exhale in rhythms shaped by nocturnal life. Many of these voices belong to species that hide from daylight, emerging only when shadows deepen. Each sound carries information about territory, courtship, danger, or discovery. Yet the layers overlap in ways that create a tapestry rather than chaos. As you listen, patterns emerge that reveal how deeply connected these animals are to one another and to the land itself. The night chorus becomes a reminder that the rainforest never sleeps. It simply changes the language through which life expresses itself. There are flowers that only open under the full moon. In secluded pockets of the rainforest, certain plants wait for the exact brightness of a full moon before unfurling their petals. These blossoms rely on pale light that filters through the canopy, guiding nocturnal pollinators directly toward them. Their petals often appear white or silvery, so they glow gently under lunar illumination. The air around them fills with scent that intensifies only during these nights, drawing moths and beetles that navigate by moonlight. The bloom is brief and precise, timed to align with the cycles of the sky. When the moon begins to wane, The flowers close once again, conserving energy until the next period of ideal light returns. These plants embody a relationship between earth and sky that unfolds quietly yet with astonishing accuracy. Their blooms become fleeting celebrations of celestial timing and the deep intelligence of nature. Nocturnal monkeys leap silently through the branches in pitch darkness. In the deepest night, when even moonlight struggles to penetrate the canopy, certain monkeys move with astonishing grace. They rely on finely tuned senses other than sight, such as acute hearing and an ability to detect subtle changes in air movement. Their hands and feet grip bark with practiced familiarity as they judge distances through memory, instinct, and the faint texture of surrounding branches. These monkeys travel in family groups that communicate with gentle clicks or soft notes that do not disturb sleeping creatures nearby. They forage for fruit or insects hidden within curled leaves, using touch to replace the guidance of light. Watching them reveals how fully animals adapt to nocturnal life. They do not hesitate, even when leaping across wide gaps. Their bodies seem shaped for darkness, navigating a world that appears invisible to human eyes, yet perfectly clear to them. Bioluminescent fungi light up the forest floor like stars. When night deepens and moisture thickens the air, small clusters of fungi begin to glow with soft green or blue radiance. This light emerges from chemical reactions within their cells that occur when the fungi break down decaying material. The glow is often subtle, visible only when all other light fades. Yet in completely dark spaces, the forest floor can take on an otherworldly appearance, dotted with faint points that resemble scattered stars. Insects drawn to the glow may help spread spores as they land and explore the illuminated surfaces. Some fungi brighten after rainfall, while others glow most intensely when approaching maturity. Scientists continue to study why these species produce light, yet each discovery reveals deeper complexity. The forest becomes a cosmic landscape beneath the canopy, where decay transforms into delicate radiance. This quiet glow reminds us that life can express beauty even in its final stages. Night vision snakes glide through black water under a canopy of silence. In flooded forests, certain snakes move effortlessly through dark water without relying on visible light. Their bodies contain heat-sensing structures that allow them to detect the warmth of prey hidden among roots or drifting branches. They slip between submerged logs with fluid movements, disturbing nothing as they pass. Their eyes gather whatever faint light exists, while their tongues sample chemical traces carried by the current. These snakes often hunt fish, amphibians, or small mammals that venture near the water's edge. Their presence becomes known only by the brief ripple that trails behind them. The rainforest around them remains quiet, as though holding its breath. The snake's journey through the dark water reflects the deep subtlety of nocturnal life, where survival depends on senses that operate beyond human perception. Even in silence, the forest brims with unseen movement and purpose. Some moths hear the echolocation calls of bats and dodge them mid-flight. In aerial battles invisible to the eye, moths have evolved extraordinary hearing organs that detect the high-frequency pulses emitted by hunting bats. When these pulses reach them, the moth reacts instantly, folding its wings or altering its flight pattern with unpredictable twists. Some dive sharply downward, while others veer into chaotic paths that confuse predators. These evasive maneuvers occur in fractions of a second, shaped by millions of years of evolutionary pressure. The forest sky becomes a realm of constant negotiation between hunter and prey. Moths that succeed pass their heightened sensitivity to the next generation, refining this remarkable survival skill. Observing them reveals the intricate arms race unfolding each night in the canopy. Their responses contribute to the delicate balance of rainforest ecosystems, where adaptation defines every relationship. Tree frogs change their color entirely between day and night. During daylight, Certain tree frogs display bright patterns that help them blend with sunlit leaves or warn predators of natural toxins. As night approaches, their skin shifts into deeper tones that conceal them among shadows. This transformation occurs through pigment cells that expand or contract within the skin. The process is influenced by temperature, moisture, and the subtle rhythm of the frog's internal clock. Once darkness settles, the frogs climb higher into the canopy, using their altered colors to avoid nocturnal predators. In the morning, their colors brighten once again. This daily cycle highlights the dynamic interplay between behavior, physiology, and environment. Their outer appearance becomes a living response to changing light, revealing how deeply creatures attune themselves to the cycles of the rainforest. Nocturnal beetles send pulses of infrared light invisible to the human eye. Certain beetles communicate at night using flashes of light that fall outside the visible spectrum. These pulses travel through the air in narrow beams that only other members of the species can detect. The beetles use this hidden language to locate mates or coordinate movement through dense vegetation. Their bodies contain specialized structures that produce heat-based light in brief bursts. Because predators cannot see these signals, the beetles communicate safely without attracting unwanted attention. This invisible conversation forms another layer of the rainforest's nocturnal world. Scientists studying these beetles often require specialized cameras to capture the signals. When viewed through this equipment, the darkness reveals a silent exchange of glowing threads. These insects remind us that countless interactions unfold beyond our senses, and that the rainforest contains entire conversations hidden within wavelengths people cannot perceive. At night, the forest breathes differently than it does by day. When the sun sets, the rainforest shifts its entire rhythm. Plants slow their release of oxygen and increase the uptake of carbon dioxide. The temperature cools, allowing moisture to condense into beads that coat leaves, vines, and branches. The air thickens slightly as humidity rises. Animals adjust to this change. Nocturnal species emerge to feed, while daytime creatures retreat into sheltered hollows. Sounds shift from the chatter of birds to the hum of insects and the deep calls of amphibians. Even the soil cools, releasing scents that attract nighttime foragers. The forest moves into a softer pattern that allows creatures to rest or awaken depending on their biological clocks. This nightly transformation illustrates the rainforest's ability to operate as a vast, breathing organism with cycles that shape every living thing within it. Some carnivorous plants only trap prey after dusk. Certain carnivorous species time their feeding activity with the arrival of darkness. Their traps remain open during the day, appearing harmless to insects that wander across their surfaces. As night falls, the plants shift their internal chemistry, making their surfaces more adhesive or altering the movement of trap structures. Some release subtle scents that attract nighttime insects seeking moisture or nectar. Once the prey lands, the trap closes with slow yet decisive movement, beginning the process of digestion. This nocturnal strategy allows the plants to avoid competition with daytime predators while taking advantage of insects active at night. Their ability to coordinate feeding with environmental cues demonstrates a refined adaptation to the rhythms of the rainforest. Under the moonlit canopy, these quiet hunters wait patiently for the right moment to secure nourishment. The Congo Basin rainforest pulses with storms like a living heart. Across this immense landscape, weather does not simply arrive. It builds slowly within the forest itself, gathering strength as countless trees release moisture into the sky. Warm air rises in towering columns until clouds begin to swirl above the canopy. In the distance, thunder murmurs like the slow beat of something ancient. Lightning flashes across the horizon and illuminates the trunks of colossal trees that have felt this rhythm for ages. Rain begins as a soft patter, barely perceptible among the ferns, before swelling into a powerful downpour that sweeps through the forest with the energy of a living pulse. Animals sense these changes long before the first drop falls. Birds retreat into thick foliage. Elephants adjust their routes. Even insects alter their flight patterns as pressure shifts. When the rain arrives, it cools the air and replaces the heavy stillness with a fresh scent rising from soil newly awakened. The storms ebb and swell in patterns so consistent that the forest seems to breathe in storms and exhale calm. This cycle shapes life across the basin, nurturing plants and animals that rely on the dependable rhythm of sky water and thunder. Southeast Asia's rainforests echo with the calls of gibbons at dawn. As the first pale light touches the canopy, gibbons begin their elaborate songs. Their voices rise in sweeping arcs that carry across valleys and riverbanks, weaving through vines and drifting above treetops. Each call contains patterns that communicate territory, companionship, and the subtle rhythm of family bonds. Their long arms and agile bodies allow them to swing from branch to branch with effortless grace as they sing, creating music and movement that blend into a single expression of dawn. Other creatures awaken in response. Birds answer with their own layered notes. Insects begin their daily chorus. Even the leaves seem to vibrate as sunlight grows stronger. Gibbon families often sing together, creating harmonies that travel great distances over the humid air. These morning performances mark the beginning of the forest's daily unfolding. The songs act as landmarks of sound that define space and time for creatures near and far. Hearing them feels like witnessing the forest open its eyes for the first time each day. Australia's ancient rainforests shelter some of the world's rarest marsupials. Hidden among the lush greenery of Australia's oldest forests, live marsupials found nowhere else on Earth. Some glide silently through the night on folds of skin that catch the humid air. Others move slowly across moss-covered branches, their large eyes designed for dim light filtered through ancient canopies. These species trace their ancestry across millions of years, surviving dramatic climate shifts and the arrival of countless new predators and competitors. The rainforest offers them shelter in the form of dense understory, cool ravines, and tree hollows shaped by centuries of growth. Many depend on specific plants for food, choosing leaves, nectar, or fruits that grow only in narrow ecological niches. Their existence reveals the strength of ancient ecosystems that preserve life forms deeply connected to the past. To encounter one of these marsupials is to witness a living chapter of evolutionary history, preserved by forests that have endured since times long before modern bow animals emerged. New Guinea's rainforest is home to birds that build elaborate courtship stages. Within the deep green of New Guinea's forest, certain birds create intricate arenas designed purely for the purpose of attracting mates. These stages often begin as simple clearings on the forest floor. Over time, the birds decorate them with carefully selected leaves, berries, sticks, and objects that catch the eye. Some arrange materials in spiral patterns. Others build small towers or archways. Each design reflects the individual's creativity and strength. Once the stage is complete, the bird performs dances filled with sweeping gestures, fluttering movements, and precise steps that display its skills. Nearby females watch the performance and evaluate the artistry, rhythm, and effort shown. The building and dancing can continue for many days as the bird refines each detail. These courtship rituals demonstrate extraordinary intelligence and persistence. They also highlight the rainforest's role as a cradle for complex behaviors shaped by beauty, precision, and the desire to impress. Madagascar's rainforests shelter species found nowhere else on Earth. Separated from other continents for millions of years, Madagascar developed ecosystems that evolved in near isolation. Within its rainforests, live creatures so distinct that they seem like inhabitants of another world entirely. Lemurs leap gracefully through the canopy with movements unlike any other primates. Chameleons shift their colors in response to subtle cues found in these unique habitats. Rare plants produce blossoms with shapes and scents found nowhere else. Even the forest floor contains species of insects, fungi, and reptiles that exist only on this island. The separation allowed life to chart unusual evolutionary paths, creating forms and behaviors seen in no other rainforest. Many of these organisms depend on highly specific microhabitats found only in narrow regions of Madagascar. Their survival reflects both the fragility and resilience of isolated ecosystems. To walk through these forests is to witness life shaped by deep time, guided by conditions unlike anywhere else on Earth. The Daintree rainforest may be the oldest surviving tropical rainforest in the world. Along the northeastern coast of Australia lies a forest that carries the memory of ancient ages. The Daintree has endured shifting climates, rising seas, and continental movements that reshaped the surrounding land. Many plant species found here represent early branches of the evolutionary tree, maintaining forms close to their prehistoric ancestors. Vines climb trunks that have sheltered generations of creatures. Ferns unfurl fronds that echo patterns found in fossils dating back tens of millions of years. The forest's streams flow through landscapes shaped by a lineage of plants and animals that survived when others disappeared. Some insects and birds found in these forests retain traits linking them to ancient lineages. The Daintree offers a rare window into what early tropical forests may have looked like long before modern ecosystems formed. Walking within its shadows feels like stepping into a time that predates human history, carried forward by the patience of nature. Borneo's jungle canopy is alive with orangutans, gliders, and sun bears. High above the forest floor, Borneo's canopy forms an interconnected world where creatures move with astonishing independence from the ground. Orangutans travel through this elevated realm, using powerful arms to navigate from tree to tree in search of fruit, leaves, and bark. Beneath their pathways glide small mammals that spread membranes of skin and float silently from branch to branch. Sun bears climb thick trunks with strong claws to reach honey hidden within tree hollows. Each species uses the canopy in unique ways, turning it into a layered network of activity. The branches act as highways for movement, communication, and feeding. Even plants adapt to this high environment by developing leaves that capture sunlight filtered through many layers of green. Life in Borneo's canopy demonstrates how richness multiplies when species explore different levels of the same forest. Sri Lanka's wet zone forests bloom with flowers not found on any other continent. In the lush wet zones of Sri Lanka, rain nourishes forests that burst into color with exquisite blossoms found nowhere else in the world. Some flowers unfold only in the dim light beneath dense canopies. Others bloom along mist-covered cliffs where cool winds carry their scents across the landscape. Many plants depend on highly specialized pollinators, creating relationships that evolved through countless generations. Birds with bright feathers visit certain flowers exclusively, while insects navigate intricate shapes designed to guide their movements. These unique blossoms mirror the island's long history of isolation and shifting climate. Their presence creates seasonal spectacles across the rainforest, transforming green landscapes into scenes of vibrant color. Each bloom expresses the island's deep ecological identity and adds to the diversity that draws researchers and visitors from around the globe. Central America's rainforests form narrow corridors teeming with jaguars and toucans. Stretching between continents, these forests create living bridges that allow species to travel across great distances. Jaguars roam through shadowed undergrowth, following ancient paths that cross rivers and mountains. Toucans glide between fruiting trees with bright bills that stand out against the canopy. Many species rely on these corridors to maintain healthy populations, moving from region to region in search of new feeding grounds or mates. The forests themselves change gradually along the corridor, blending distinct ecosystems into a mosaic of habitats. Each region supports creatures adapted to subtle shifts in rainfall, altitude, and vegetation. These connected pathways sustain the movement of life across Central America, linking creatures in a web that stretches from one ocean to the other. The corridors become highways of biodiversity where predators, pollinators, and migrants maintain balance across the land. Even Hawaii once held tropical rainforests filled with lost legends and lava trees. Long before large human settlements, Hawaii's volcanic mountains were draped in thick rainforests where unique birds sang from branches coated in moss and pau. Mist. Lava flows from ancient eruptions cooled beneath the forests and left behind hollow pillars known as lava trees. These natural sculptures formed when molten rock surged around living trunks and then hardened while the trees burned away. Over time, plants returned to these landscapes, creating environments rich with species found nowhere else on the planet. The rainforests once sheltered honeycreeper birds with vivid plumage, insects that evolved specialized feeding habits, and plants that flourished in volcanic soil. Many of these species are now rare or vanished, leaving behind traces of their presence in stories and scientific records. The remnants of Hawaii's ancient rainforests offer glimpses of worlds shaped by fire, water, and deep time, where life adapted to the rhythms of an island stillgrass. Growing from the sea, rainforests pull carbon from the atmosphere with every breath. Each leaf within the rainforest acts as a living gateway between the air and the earth. Through the quiet process of photosynthesis, plants draw carbon dioxide from the atmosphere and transform it into the building blocks of their trunks, branches, fruits, and roots. This happens every moment of every day, guided by sunlight that filters through endless layers of green. When you stand among these trees, you stand in the presence of a vast machine that turns air into life. The forest holds this carbon not only in wood, but also in soil enriched by centuries of fallen leaves and roots. Animals add their own contributions as they eat, exhale, and move nutrients across the land. The process is steady and constant, like a deep inhale that continues across generations. Without this immense exchange, Earth's atmosphere would feel very different. Rainforests help moderate temperatures, support stable climates, and offer the world a breath of balance. They do so quietly, one leaf and one moment at a time. The disappearance of rainforests affects rainfall thousands of miles away. Moisture released by rainforest trees rises into the sky, where it gathers into clouds that travel far beyond the boundaries of the forest itself. These clouds carry water across continents, feeding distant farms, rivers, and mountain ranges. When forests shrink, the sky receives less moisture. Air currents lose strength, and rainfall patterns shift. Regions far removed from the tropics can experience drought or unpredictable storms because of changes that begin with tree loss thousands of miles away. Researchers have traced these atmospheric pathways, revealing how vapor born within a single rainforest may journey across oceans before falling as rain in entirely different climates. This global linkage shows that rainforests act not only as local ecosystems, but also as engines that drive hydrological cycles for the entire planet. Their loss disrupts patterns that have taken millions of years to stabilize. Every tree removed weakens a complex chain of events that sustain life far beyond the forest borders. Some rainforest trees release cooling aerosols into the sky. Certain species emit tiny organic particles that drift upward from their leaves and branches. These aerosols interact with moisture in the air, helping clouds to form more efficiently. When sunlight strikes the tops of these clouds, it reflects back into space rather than heating the ground. This creates a cooling effect that benefits not only the forest, but also regions far beyond it. The trees perform this function naturally, adjusting their emissions according to temperature, humidity, and light. During the warmest parts of the day, aerosol levels often rise, assisting the forest in releasing excess heat. Over time, this process shapes local weather patterns and contributes to global climate regulation. Scientists studying this phenomenon describe it as a form of atmospheric communication in which trees help regulate the temperature of the world. These natural particles act as tiny mirrors that soften the sun's intensity and maintain the delicate equilibrium that rainforest life depends upon. Even the shape of rainforest leaves affects how Earth regulates heat. Leaf shapes vary dramatically across the rainforest, from long pointed blades that shed water quickly to broad, rounded surfaces that gather moisture. These shapes influence how sunlight is absorbed or reflected. Large leaves capture warmth and release moisture through gentle evaporation, cooling the surrounding air. Narrow leaves reflect light differently and create subtle airflow patterns around their edges. Dripping tips guide water away from delicate tissues and help prevent overheating during strong sunlight. When billions of leaves perform these functions together, they alter the temperature of the entire forest and contribute to global heat regulation. The combined effect of leaf geometry, surface texture, and water movement creates a dynamic cooling system woven into every level of the canopy. This system helps stabilize temperatures and humidity, ensuring that countless species can thrive in conditions that remain remarkably consistent from season to season. The rainforest becomes a living mosaic where each leaf plays a part in shaping Earth's climate. The loss of rainforest canopy can raise ground temperatures by more than 10 degrees. When trees disappear, the land beneath them feels the change immediately. Sunlight that once filtered gently through leaves now strikes the soil with full intensity. Without shade, moisture evaporates rapidly, and the ground heats to levels that many plants and animals cannot tolerate. Studies of cleared land reveal that temperatures can rise by more than 10 degrees when the protective canopy is removed. This shift alters the balance of the entire ecosystem. Seeds that once sprouted easily become dry and dormant. Insects that required cool understory conditions move away or die. Small mammals struggle to find shelter as the ground becomes too warm for comfortable movement. Even the soil itself suffers, losing nutrients as heat and wind carry them away. The canopy acts as an insulating blanket for the rainforest, safeguarding life below. When it vanishes, the forest loses more than shade. It loses the very conditions required to sustain its extraordinary biodiversity. Rainforests influence the flow of entire jet streams across the planet. The rising columns of warm air above tropical forests do more than create local weather. They shape the pathways of powerful winds that circle the globe. These high-altitude currents, known as jet streams, respond to shifts in heat distribution. When rainforests release moisture and regulate temperature, they create distinct patterns in atmospheric circulation. Changes in forest cover can alter the strength, direction, and stability of these winds. Such shifts may affect the timing of storms, the arrival of monsoon seasons, and the formation of droughts in faraway regions. The forest acts as both anchor and guide for the jet streams, helping maintain balance in systems that govern weather across continents. This reveals that the rainforest is connected not only to tropical climates, but also to deserts, grasslands, and temperate zones. It participates in global dialogue between land, ocean, and sky, influencing events thousands of miles beyond its borders. Soil in untouched rainforests can lock away carbon for centuries. Beneath the dense web of roots and fallen leaves lies soil that has built its richness over unimaginable spans of time. Organic material decays slowly in the humid yet shaded conditions, creating a foundation that stores vast amounts of carbon. Microbes and fungi break down plant matter at rates perfectly balanced by the forest's continual input of fresh material. This slow cycling allows nutrients to remain in the soil for centuries before returning to the atmosphere. In untouched regions, the soil becomes a deep archive of stored carbon that contribute significantly to Earth's long-term climate stability. Disturbance of this soil releases carbon back into the air, accelerating warming and disrupting the ancient balance. Protecting intact forests, therefore, protects these subterranean reservoirs that have quietly supported the planet for ages. The soil beneath the rainforest is more than Earth. It is a living vault shaped by time, moisture, and the gentle work of countless organisms. Forest fires in the tropics can accelerate the melting of Arctic ice. When fires burn in tropical regions, they release dark particles that rise high into the atmosphere. Winds carry these particles across continents until they eventually settle on snow and ice in polar landscapes. The darkened surface absorbs more sunlight than clean ice, causing it to warm and melt more quickly. This creates a feedback cycle in which melting exposes more ground or water, which then absorbs even more heat. Although the source of the particles may be thousands of miles away, the impact reaches the farthest edges of the planet. The relationship between tropical fires and Arctic melt demonstrates the interconnectedness of Earth's climate system. What occurs beneath a rainforest canopy can influence the fate of distant glaciers. This connection underscores the importance of preventing unnecessary fires and protecting forests that play vital roles in moderating global temperatures. Rainforests are one of Earth's greatest climate stabilizers. They regulate heat, moisture, atmospheric chemistry, and global patterns of wind and rain. They hold vast stores of carbon in trunks, branches, and soil. They cool the air through evaporation and shape weather through cloud formation. Every feature of the rainforest contributes to a balanced climate. Cutting away these forests weakens Earth's ability to maintain stability. Preserving them strengthens natural resilience. Their influence spans continents and oceans, guiding rainfall into parched regions and preventing storms from spiraling into extremes. They create consistent temperatures within their own boundaries and buffer global systems against dramatic shifts. Standing within a rainforest is to stand inside a vast engine of balance. It is a reminder that stability comes from cooperation between living systems, each thread connected to countless others across the planet. Tree roots in rainforests help anchor entire landscapes against erosion. Roots extend far beneath the surface, weaving through soil like living ropes. They bind loose particles together, preventing rainfall from washing the ground into rivers. During storms, these roots act as stabilizing anchors that hold slopes in place and protect riverbanks from collapse. The network of roots also directs water through the soil in slow, steady channels that reduce flooding and maintain groundwater. When forests disappear, this natural support system collapses, causing landslides, muddy rivers, and degraded habitats. In untouched forests, the roots contribute to a complex architecture that shapes the terrain itself. They create spaces for insects, fungi, and small mammals to live. They assist the slow release of nutrients that feed the next generation of plants. The landscape remains firm and resilient because the roots hold it together like a foundation made of living strength. Indigenous knowledge of rainforests includes cures modern science has not yet explained. Across rainforests around the world, indigenous healers have developed remedies through generations of careful observation and spiritual connection to the land. Their knowledge grows from listening to the forest's rhythms, watching how animals interact with plants, and learning through stories passed carefully from teacher to student. Some treatments use combinations of leaves, roots, fruits, and tree bark, prepared in ways that concentrate healing properties. These medicines can reduce fever, soothe pain, calm the mind, or bring clarity to the senses. Many have been shared with researchers who continue to study their chemical composition, yet science still struggles to understand how certain mixtures work. Some remedies require preparation only during specific lunar cycles or seasons, because their potency changes with shifts in rainfall, temperature, or even sunlight. To the healers, These details are not mysteries, but parts of a relationship between people and forest that has endured for centuries. Their knowledge is a vast library written in scent, taste, texture, and memory, and much of it remains known only within the communities that protect it. Entire tribes have lived in the rainforest without ever being detected. Deep within remote regions, there are communities who have chosen to remain separate from outside contact. They navigate the forest with an ease that comes from lifelong familiarity, moving through trees and rivers with silent confidence. Their homes blend into the landscape so well that even trained explorers passing nearby may never realize they are close. These tribes hunt with tools crafted from local materials, fish in hidden streams, and cultivate small gardens in sunlit clearings. Their knowledge of the forest is intimate and expansive. They know the seasons of fruiting trees, the signs left by migrating animals, and the patterns of rainfall that shape their movements. Many outsiders learn of these groups only through brief glimpses or traces found along riverbanks. Yet these communities often thrive in harmony with the environment, guided by traditions older than recorded history. Their existence reminds the world that even in the modern age, vast regions remain untouched by outside influence, and entire cultures continue to live in ways shaped entirely by the forest. Some rainforest trails are older than the cities of Europe. Long before large civilizations formed stone streets or towering buildings, forest dwellers created pathways through dense vegetation. These trails followed the movements of animals, the flow of rivers, and the fruiting cycles of trees. Over centuries, the trails became established routes used for trade, seasonal migration, and spiritual journeys. Layers of footsteps packed the soil into firm, quiet paths that still exist today. Some follow ridges shaped by ancient geological processes. Others wind towards sacred grooves, waterfalls, or hidden valleys known only to local communities. In many places, the forest has grown over sections of these paths, yet the underlying structure remains intact. Researchers have traced certain routes that predate many major human cities by thousands of years. Walking these trails is like stepping into a timeline that stretches far beyond written records. They serve as natural highways through the jungle, guiding both humans and animals through landscapes shaped by time, memory, and the enduring presence of the rainforest. There are trees considered sacred and never touched by human hands. Within many rainforest cultures, certain trees hold deep spiritual significance. Some are believed to house protective spirits. Others are seen as ancestral guardians that watch over the land. These trees often stand taller or older than those surrounding them, their roots spreading wide and deep into ancient soil. Communities approach them with reverence, offering prayers, songs, or small gifts placed at their base. No one climbs them, harvests their leaves, or cuts their bark. These trees are allowed to live their full natural lifespan, growing without interference. Birds nest within their branches. Epiphytes form delicate gardens on their trunks. Animals rest in their shade during the heat of the day. Even when branches fall, the wood is left where it lands. Such trees become living monuments to respect and connection between people and forest. Their presence embodies a relationship in which nature is not merely a resource, but a partner, teacher, and elder. Rainforest peoples use plants that mimic animal calls to hunt. In certain regions, hunters carry leaves or stems that produce specific sounds when blown, rubbed, or tapped. These plants create tones that resemble the calls of birds, frogs, or small mammals. By imitating these sounds, hunters attract curious animals or calm them long enough to approach quietly. The technique requires careful practice because each species responds to unique patterns of rhythm and pitch. Some plants imitate alarm calls that cause animals to pause in confusion. Others mimic the soft notes of companionship or mating. The hunters must understand not only the plant's sound, but also the behavior and mood of the target species. This method reflects a deep understanding of the forest's acoustic language, where every creature communicates through subtle tones. The plants used for these calls become tools that bridge human skill with natural resonance. This practice highlights the creativity and adaptability of rainforest cultures whose survival depends on attunement to the environment. Some rainforest languages contain words for birds no scientist has ever documented. Within remote communities, people often name species long before researchers discover them. Many rainforest languages include terms that describe birds known only through local experience. These words carry information about the bird's behavior, its preferred habitat, its song, and even the season when it appears. Some names distinguish between subtle variations in plumage or flight patterns that researchers have not yet recorded. When linguists gather vocabulary lists, they sometimes find references to birds that have never been captured in photographs or scientific surveys. These names reveal relationships built over generations of careful observation. They show that the forest has many residents still hidden from formal study. The languages serve as living maps of biodiversity, preserving knowledge of species that may be rare, shy, or active only during certain hours. This linguistic richness adds depth to the understanding of culture and ecology, reminding us that science and tradition both hold pieces of the world's story. Forest dwellers can identify hundreds of plants by smell alone. In many rainforest cultures, children learn from an early age to recognize plants through scent. They inhale gently to detect the sharp aroma of medicinal leaves, the earthy fragrance of edible roots, or the faint sweetness of flowers that attract specific pollinators. Over time, they develop a finely tuned sense of smell, capable of distinguishing slight differences between closely related species. Some can discern whether a plant is young or old, healthy or stressed, based solely on the scent carried by its leaves or bark. This skill extends into the night, when light is scarce and scent becomes a primary guide. The forest becomes a library of fragrances that reveal location, season, weather, and opportunity. This sensory knowledge allows forest dwellers to forage safely, prepare remedies with accuracy, and navigate landscapes often too dense to rely on sight alone. Their ability demonstrates the remarkable adaptability of human perception when shaped by life within the rainforest. Ceremonial dyes in rainforest cultures come from creatures that can kill if mishandled. Certain insects, frogs, or caterpillars produce powerful compounds that tribes use to create vibrant pigments for rituals, body art, and sacred objects. These creatures often secrete toxins as a natural defense against predators. When handled with respect and skill, their secretions can be transformed into brilliant reds, deep blues, or luminous yellows. The process requires careful knowledge passed through specific family lines. Gatherers may know the exact time of year when the creatures yield the safest and strongest pigments. They understand how to combine the material with plant extracts to neutralize harmful effects. The resulting dyes hold cultural meaning tied to spiritual protection, identity, or celebration. Their creation reflects both reverence for the creatures and an understanding of the delicate balance between danger and beauty. To outsiders, these dyes seem miraculous. To the communities who make them, they are expressions of connection to powerful beings who share the forest. Some traditional rainforest medicines are made using sunlight, sap, and silence. In certain healing traditions, remedies are created with deliberate calm and ceremony. The healer collects fresh sap from specific trees at dawn when its properties are believed to be strongest. The sap is placed in bowls of carved wood that absorb subtle qualities from the material. The mixture is then set in filtered sunlight for a precise amount of time. Some medicines require the complete absence of speech during preparation because sound is thought to disturb their formation. Others require soft humming that aligns the healer with the forest's energy. The final remedy may be applied to the skin, sipped slowly, or used as a compress warmed over gentle fire. Modern analysis sometimes reveals complex chemical interactions that occur when sap meets light, yet the traditional method remains rooted in respect for core, timing, intention, and atmosphere. These medicines are as much spiritual expressions as they are physical treatments. Generations have mapped the rainforest not with paper, but with memory and song. Before written maps existed, rainforest communities navigated through stories sung across generations. These songs often describe the shapes of mountains, the bends of rivers, the calls of birds that marked certain locations, and the presence of sacred groves hidden within the dense canopy. Children learned the landscape through rhythm, melody, and repetition, until the forest became a mental map, woven with sound. Paths were remembered through verses describing the taste of specific fruits found along the way, or the sound of water at particular bends. Even subtle differences in wind or soil were encoded in the songs. Travelers relied on these musical maps to cross great distances, carrying knowledge that adapted with each generation as the forest changed. These song maps reflect deep intimacy between people and place, showing that geography can be preserved not only through lines on paper, but also through memory, shaped by voice and breath. Some rainforest insects can alter the weather by releasing aerosols. Within the rainforest canopy live insects that contribute to atmospheric processes in subtle yet powerful ways. As they feed, move, and release natural chemicals into the air, they emit microscopic particles that serve as seeds around which moisture can gather. These aerosols drift upward through warm air currents created by the forest itself. When they reach cooler layers of the atmosphere, water vapor condenses upon them and forms clouds. Over time, these clouds may grow dense enough to release rain but falls back onto the forest. In this way, even the smallest creatures influence the hydrological cycles that sustain the ecosystem. Their activities add texture and complexity to the rainforest's breathing, blending with the emissions of plants, fungi, and soil microbes. Insects play an active role in shaping conditions that affect their own survival, demonstrating that weather is not solely the product of wind and sun, but also the combined actions of countless living beings. The rainforest sky becomes a living reflection of activity occurring at ground level. Tree roots can send chemical warnings to other trees miles away. Beneath the forest floor stretches a vast network of interconnected roots woven together through soil, fungi, and moisture. When one tree experiences stress due to pests, drought, or injury, it releases chemical signals into this network. These signals travel along root pathways and fungal threads until they reach other trees. Upon receiving the message, neighboring trees begin to alter their internal chemistry by producing protective compounds or adjusting their water use. Some even change the structure of their leaves to reduce vulnerability. This communication can extend across great distances because the underground web links entire sections of the forest. The process occurs silently, without any visible sign on the surface. Yet it demonstrates a hidden cooperation within the ecosystem. Trees behave not as isolated individuals, but as members of a community that shares information essential for survival. Their warnings reveal a sophisticated awareness of danger and an ability to respond as a unified presence. Certain trees hum at ultrasonic frequencies to signal stress. Deep inside their trunks, trees contain networks of vessels that move water from roots to leaves. When a tree experiences drought or damage, the tension within these vessels changes. These shifts create vibrations that travel through the wood as sound waves too high for human ears to detect. Sensitive instruments reveal that stressed trees emit continuous ultrasonic hums that differ from the sounds of healthy ones. Other organisms, including insects or mammals with acute hearing, may detect these vibrations and respond accordingly. Some pests are drawn to the hum, while others avoid it. The forest becomes a quiet orchestra of signals that reflect the changing conditions of its members, Although humans cannot hear this communication, it forms an integral part of the rainforest's hidden dialogue. Each hum marks a moment in which the tree reaches outward into the world, expressing its need through the language of vibration. There are lianas that move towards sound vibrations in the canopy. Certain climbing plants exhibit sensitivity to vibrations in their surroundings. As animals move through the canopy or as wind shifts branches, distinct patterns of motion ripple through the air and through the wood of nearby trees. These vibrations help guide the growth of lianas. Instead of growing randomly, the vines slowly adjust their direction, bending toward the source of consistent vibration. This allows them to locate sturdy trunks that offer reliable support for climbing. The process unfolds gradually, with each new growth tip responding to the faint messages carried by sound. This behavior reveals a surprising sensory capacity within plants, showing that they interact with their environment through more than light and chemical cues. The movement of a liana toward vibration demonstrates the responsiveness of rainforest vegetation to the dynamic activity of animals, weather, and deep air. Neighboring trees. It is a quiet pursuit that transforms the canopy into a web of intertwined lives. Rainforests produce scents that travel across oceans on the wind. Every leaf, flower, and fruit within the rainforest emits natural compounds that rise into the air. These scents combine into a complex signature unique to each region. Once airborne, the molecules enter vast atmospheric currents that carry them far beyond the boundaries of the forest. Over days or weeks, they drift across islands, coastlines, and entire oceans. In some cases, these airborne chemicals seed cloud formation or influence rainfall patterns in distant lands. They also bring hints of the forest's presence to places that may never see its trees. Certain compounds break down as they travel, while others remain intact, continuing their journey across the globe. The rainforest becomes part of a planetary cycle of scent, in which the chemistry of one region influences the air of another. These fragrances reveal that forests broadcast their identity through the sky, participating in interactions that span continents. Some leaves turn away from the sun when danger approaches. In moments of threat, certain plants respond to subtle cues in their environment by adjusting the angle of their leaves. When insects begin to gather, or when nearby plants release signals of stress, these leaves rotate slightly or fold inward. This reduces exposure to herbivores and makes the plant less vulnerable to damage. The movement may also limit evaporation, allowing the plant to conserve water in times of distress. These changes occur through shifts in internal pressure within specialized cells that act like tiny hinges. The forest is filled with such movements during moments of tension. Although invisible from afar, they reveal a world in which even quiet plants respond quickly to information around them. Their ability to sense danger and act upon it demonstrates a level of awareness rooted in evolution. Each leaf movement shows the rainforest's ability to protect itself in ways both subtle and profound. Certain rainforest plants use magnetic fields to orient their growth. Within their cells, some plants possess structures that respond to the magnetic forces of the earth. These structures help guide growth toward favorable directions, ensuring that roots spread efficiently into the soil, while stems rise towards stable light. Magnetic awareness allows the plant to maintain consistent orientation even when wind, rain, or canopy shifts alter the visual cues within the forest. This capacity becomes especially valuable in dense environments where sunlight arrives in scattered fragments rather than clear beams. Plants with this sensitivity grow in a manner that maximizes stability and efficiency. Researchers studying this phenomenon believe it may help certain species survive in challenging conditions where other forms of navigation are unreliable. The rainforest contains countless examples of complex behavior hidden within the biology of its plants, and magnetic sensitivity is one of the most remarkable of these subtle adaptations. light filters through rainforest mist in patterns unique to each location. When sunlight enters the forest at a particular angle, it encounters moisture suspended in the air. This mist scatters the light into rays that drift across leaves, vines, and branches. The patterns formed depend on the composition of the air, the density of the canopy, the temperature of the morning, and the altitude of the land. No two places create identical displays. In some regions, beams of warm gold spill down like tapestries touched by movement. In others, cool white ribbons form delicate columns that illuminate floating pollen. These patterns change moment to moment as wind alters the mist and as trees sway with gentle pulses of air. Animals respond to these shifting lights by adjusting their activity. Birds begin foraging when the first rays brighten their perch. Insects rise into beams that warm their wings. The forest becomes a cathedral of moving light, shaped by the unique conditions of each location. Some organisms in the rainforest have never been photographed alive. There are species so rare, so elusive, or so remote that scientists know of their existence only through traces such as molted skin, footprints, or brief glimpses recorded decades ago. Some appear in local stories but remain absent from scientific documentation. Others are known from museum specimens collected long before cameras became common. These organisms navigate hidden regions of the forest where human presence is rare. They may live high within the canopy or deep within labyrinths of roots. Their avoidance of detection reflects both their rarity and the density of the rainforest, where shadows and layers conceal even large creatures. Researchers continue to search for them using sound recorders, scent traps, and infrared equipment. Each attempt reflects the hope of glimpsing beings that have remained private for generations. The rainforest still holds mysteries that defy our expectation that everything can be seen or measured. There may be species in the rainforest whose existence we still cannot imagine. The rainforest contains so many microhabitats, so many layers of soil, foliage, water, and air, that entire lineages may remain hidden from science. Some could dwell in canopy zones rarely reached by humans. Others might thrive within soil structures or rotting logs where light never enters. There may be organisms with behaviors, shapes, or life cycles beyond anything currently known. Each expedition into unexplored regions reveals new forms of fungi, insects, or tiny vertebrates that reshape our understanding of biodiversity. These discoveries hint at a deeper truth. For every species described, many more remain undetected. The rainforest is not a completed catalogue, but an unfolding realm of possibilities. Within its depths lie beings whose existence challenges imagination. Their discovery may expand our view of what life can be. Until then, they remain part of the forest's quiet mystery. A single jungle leaf can hide an entire micro-ecosystem. To human eyes, a leaf may seem like a simple surface of green. But in the jungle, one leaf can hold a universe. Tiny insects graze on its edges, while others lay eggs in delicate clusters. Ants patrol its surface, guarding against intruders in exchange for nectar. Microscopic fungi and bacteria live in its tissues, breaking down waste and recycling nutrients. Sometimes water pools in the grooves, creating a miniature pond where even smaller creatures swim. Researchers studying individual leaves in tropical forests often find dozens of species interacting on that single surface. To scale it up, imagine how many lives unfold across every tree, every branch, every vine. The jungle teaches us that scale is deceptive. What looks small to us may be vast and teeming for the beings who live upon it. Sloths grow algae in their fur to camouflage. Sloths are among the slowest moving mammals on Earth, and in the jungle, slowness can be dangerous. Yet these gentle creatures have turned their pace into protection. Their thick fur creates a humid environment that allows green algae to grow directly on their bodies. This natural coating blends them seamlessly with the surrounding leaves, making them nearly invisible to predators like jaguars and harpy eagles. The relationship goes further. Moths live in the sloth's fur, and when they die, they provide nutrients for the algae, deepening the camouflage. In return, some sloths even lick the algae, gaining a bit of extra nutrition. What seems like an odd quirk is actually a carefully balanced ecosystem carried on the back of a single animal. A sloth resting quietly in the treetops becomes not just an individual, but a moving garden, hidden in plain sight. Some jungle plants can shoot seeds like tiny bullets. In the dense competition of the jungle, dispersal is everything. Some plants rely on animals to carry their seeds, but others have developed a more dramatic method: explosion. Known as ballistic dispersal, certain seed pods dry and build tension until they burst, flinging seeds outward with surprising force. Some can launch their offspring more than 30 feet away, scattering them far from the shadow of the parent. To witness such a release is startling: a sudden crack, followed by a spray of seeds, whirring into the undergrowth. This strategy ensures that new seedlings have a better chance of finding light and space. In a place where survival depends on avoiding the crowd, even plants have become inventors of motion, turning stillness into sudden bursts of energy that echo through the quiet of the forest floor. There are snakes that glide from tree to tree. Among the most astonishing sights in the jungle is a snake that takes to the air. Certain species, such as the paradise tree snake of Southeast Asia, can flatten their bodies and leap from high branches. By undulating mid-air, they create lift, gliding gracefully from one tree to another. Though they never truly fly, their controlled descent can cover distances of more than 100 feet. For the snakes, this ability offers both escape from predators and access to prey. To see a serpent, normally bound to the earth, transfalling into a ribbon of motion through the canopy, is to be reminded that the jungle is full of surprises. Here, even gravity becomes negotiable, and creatures learn to move in ways that defy expectation. Some jungles house caves full of millions of bats. Within the limestone cliffs of tropical forests lie caverns that seem alive. These caves can house millions of bats, clustered in vast colonies. At dusk, they emerge in a swirling storm, blackening the sky as they fan out to feed on insects. The sheer number of bats can be overwhelming, their wings creating a wind that rustles leaves and bends grasses. Inside the caves, the walls are coated with guano, a nutrient-rich deposit that supports unique communities of insects and fungi. These colonies play an essential role in the ecosystem, consuming staggering numbers of insects each night and fertilizing the forest with their waste. Standing at the mouth of such a cave, one sees the jungle's hidden power made visible, an eruption of life that transforms nightfall into a living cloud. There are ants that explode to defend their colonies. In the endless arms race of the jungle, even the smallest warriors can be dramatic. Some species of ants found in Southeast Asia have evolved a defense so extreme it borders on the unbelievable they can explode. When threatened, these ants rupture special glands inside their bodies, releasing sticky, toxic chemicals that immobilize their enemies. The act kills the ant itself, but saves the colony. This strategy of self-sacrifice is rare in the animal kingdom, yet in the dense competition of the jungle, it offers survival for the many at the cost of the few. To encounter such ants is to realize how far life will go in its drive to persist. Even among creatures so small, the jungle produces strategies as astonishing as any found among its largest predators. The Amazon River carries 1/5 of the world's fresh water. Winding for more than 4,000 miles, the Amazon River is not just the lifeline of the jungle, it is one of the greatest rivers on Earth. At its peak flow during the rainy season, it carries nearly 1/5 of all the fresh water that enters the oceans worldwide. The sheer volume is difficult to comprehend. More water moves through the Amazon each day than through the next 7 largest rivers combined. Its width can stretch so far that a person on one bank may not even see the other. The river nourishes countless ecosystems, floods vast forests, and creates habitats that support fish, dolphins, birds, and insects in staggering abundance. To stand on its banks is to feel the presence of something ancient and immeasurable, a moving sea that reshapes the land with every turn. Some jungle butterflies drink the tears of turtles. In the Amazon basin, a curious interaction unfolds along the riverbanks. Brightly colored butterflies gather around the faces of turtles, gently sipping at their eyes. What seems strange is actually a quest for salt. In the mineral-poor jungle, sodium is rare, yet vital for survival. Turtle tears provide a steady source, and butterflies have adapted to drink them without harming their hosts. The turtles, seemingly unbothered, continue basking in the sun, while dozens of delicate wings flutter around them. Scientists call this behavior lacrophagy, or tear feeding, and it reveals how even the smallest details of life are interconnected in the jungle. The sight of butterflies drinking tears is both tender and surreal, a reminder that in this realm, survival often comes from unexpected relationships, and beauty is bee. Stitched into the fabric of necessity, tree frogs can survive freezing and then thaw back to life. Some tree frogs of the tropics, particularly those living at high elevations or in seasonal forests, have evolved a remarkable survival trick. When temperatures drop dangerously low, their bodies can freeze solid. Ice forms around their organs and even within their tissues, yet they do not die. Special proteins and sugars in their blood act like antifreeze, protecting their cells from damage. When the air warms again, the frogs thaw. Their hearts begin to beat once more, and they return to life as if nothing had happened. This ability is almost science fiction, an animal pausing itself through the coldest nights, then continuing on at dawn. Though rare in the jungle's warm heart, these frogs show the extremes of adaptation. They are living proof that even in the most humid and lush places, nature finds ways to endure the unexpected. The canopy creates its own wind currents. The jungle canopy is not only a roof of leaves, but also a vast living landscape that reshapes the air. Sunlight warms the treetops during the day, creating rising currents of warm air. At night, as the canopy cools, air sinks back down, stirring subtle winds. The sheer density of leaves and branches adds friction, breaking up air movement into swirling eddies that dance through the upper layers of the forest. For insects, birds, and bats, these currents are essential highways, helping them travel or carry scents from flower to flower. Scientists studying the atmosphere above jungles find that the canopy behaves almost like an ocean surface, creating waves and turbulence that ripple through the cane. Sky. Beneath the trees, the air may seem still, but above, an invisible sea of wind flows, shaped entirely by the living surface of the forest itself. Some jungle plants trap insects in pools of water. High in the canopy, where soil is scarce, some plants have turned to ingenious strategies for survival. Bromeliads and pitcher plants create pools within their leaves, filled with rainwater. Insects that wander too close often fall in, unable to escape. Over time, the trapped creatures decompose, releasing nutrients that the plant absorbs. This adaptation allows the plants to thrive in places where other sources of nourishment are limited. These miniature pools become entire ecosystems, housing not only trapped insects but also tadpoles, larvae, and even tiny crabs. Some frogs depend on them as nurseries for their young. What seems like a simple leaf becomes a world of predators, prey, and partnerships, suspended high above the ground. In the jungle, every surface can be a home or a trap. A jungle can create its own microclimate, Step into the dense heart of a jungle, and you are stepping into a world with its own weather. The thick canopy shades the ground, keeping it cooler than the open air outside. At the same time, the immense release of water vapor from millions of leaves keeps the air humid and heavy. Together, these forces create a microclimate, a small-scale atmosphere that can differ dramatically from the surrounding region. Some jungles are so efficient at recycling their rainfall that they generate storms overhead, feeding themselves again and again. Even a clearing within the trees may have its own pattern of wind, light, and moisture. These microclimates allow species to specialize in niches a mere few meters wide. The jungle is not one environment, but countless overlapping ones, layered and shifting, each alive with its own rhythms. Some monkeys use tools made of stones or sticks. Tool use is not unique to humans. In the jungles of South America and Asia, capuchin monkeys and macaques have been observed cracking nuts with stones, using sticks to fish insects from logs, and even probing for water. These behaviors are learned and passed down through generations, evidence of culture among primates. Young monkeys watch older individuals and imitate their techniques, slowly mastering the skills. In some regions, entire groups develop distinctive methods, almost like traditions unique to their troop. This intelligence reveals the deep connections between us and our primate relatives. Watching a monkey hammer open a nut with careful precision feels both familiar and humbling, a glimpse of the shared ingenuity that has shaped life in the jungles for millions of years. There are beetles that glow like living lanterns. As night falls in the jungle, light does not disappear, it changes form. Among the shadows, certain beetles glow with an inner flame. Bioluminescent enzymes within their bodies release a steady green or yellow light, shining like lanterns in the dark. These glows can serve multiple purposes, attracting mates, warding off predators, or luring in prey. Entire hillsides can twinkle with these living sparks, creating scenes that seem like reflections of the stars above. The phenomenon is not limited to beetles, fireflies, and other insects join in, painting the night with pulses of light. To walk through a jungle alive with bioluminescence is to witness one of nature's quiet wonders, a reminder that illumination is not only the gift of the sun, also of life itself, shining softly in the darkness. Jungle vines inspired the first suspension bridges. For thousands of years, human communities living in jungles have studied the natural structures around them. One of the most remarkable lessons came from vines. Stretching like ropes between trees, lianas are strong, flexible, and enduring. Observing their strength, early civilizations in South America wove vines together to create suspension bridges over rivers and ravines. Some of these living bridges, reinforced by plants that continued to grow, lasted for centuries. The idea spread into architecture, inspiring modern suspension bridges of steel and cable. What began as a jungle adaptation, plants climbing toward light, became the model for human engineering feats that now span entire cities. In every strand of liana swinging above the forest floor, there is not just a path for animals, but also the blueprint for human imagination. Some jungle ants march in columns stretching hundreds of feet. Army ants are among the most feared and fascinating insects of the jungle. They travel in massive columns, with millions of individuals moving as a single coordinated force. These living rivers can stretch for hundreds of feet, flowing across the forest floor in search of prey. Anything caught in their path, insects, spiders, even small vertebrates, may be quickly overwhelmed and stripped clean. Yet the march is also a marvel of organization. Scouts rush ahead, soldiers guard the flanks, and workers carry the spoils back to temporary nests called bivouacs, made entirely of their interlocked bodies. For the jungle, these marches are both destructive and regenerative, recycling nutrients and reshaping the balance of life. Watching such a column is to witness collective intelligence in action, a swarm behaving as if it were a single organism, relentless and unstoppable. Giant centipedes in jungles can hunt bats in flight. The jungle is filled with predators, but few are as unexpected as the giant centipede. Growing nearly a foot long, with dozens of legs rippling in perfect coordination, it hunts not only insects but also frogs, lizards, and even birds. In the darkness of caves, these centipedes perform an astonishing feat. They climb stalactites and ceilings, anchoring themselves upside down, and wait. When bats fly past in dense swarms, the centipede lashes out, seizing one from the air. With its venomous pincers, it subdues the bat and begins to feed, suspended above the cave floor. To see a small invertebrate capture a flying mammal mid-air is shocking. A reminder that size does not always determine power. In the jungle, danger is everywhere, and even creatures that creep silently in the shadows may reveal hunting strategies as dramatic as any of the great cats. The world's largest flower, Rafflesia, grows only in jungles. Deep in the jungles of Southeast Asia blooms a plant unlike any other, Rafflesia arnoldii. Its blossom can measure more than 3 feet across, with thick, leathery petals mottled in deep red and white. At full bloom, the flower can weigh over 15 pounds, making it the largest individual flower on Earth. Yet its beauty comes with a twist. To attract pollinators, Rafflesia emits a smell that resembles rotting flesh, earning it the name corpse flower. Flies drawn to carrion instead crawl across its petals, spreading pollen from bloom to bloom. Rafflesia itself has no leaves or stems. It lives as a parasite within jungle vines, hidden most of the time, only revealing itself when it flowers. These rare events last just a few days, turning the forest floor into a surreal spectacle. When it appears, it feels less like a plant and more like an alien life form, strange and unforgettable. Jungle soil contains secrets of ancient civilizations. The Amazon is often imagined as untouched wilderness, but the soil tells another story. Archaeologists have discovered dark patches of earth called terra preta, or black earth, scattered throughout the basin. Unlike the thin, nutrient-poor soils typical of the jungle, terra preta is fertile and long-lasting. It is filled with charcoal, broken pottery, fish bones, and plant remains, evidence that it was created deliberately by ancient peoples. Some of these soils date back more than 2,000 years, suggesting that large, complex societies once thrived here. The presence of terra preta has transformed our understanding of the Amazon. It shows that the jungle was not simply an uninhabited expanse, but a landscape shaped and enriched by human hands. Today, these soils remain fertile, still supporting crops. Each handful of earth carries whispers of forgotten civilizations, a record of ingenuity hidden beneath the roots of the forest. Some jungles hide entire lost cities beneath their trees. For centuries, explorers spoke of lost cities swallowed by the jungle, dismissed by many as myths. Yet new technologies have revealed that these legends were true. Using LiDAR, a form of laser mapping that can see through vegetation, archaeologists have uncovered vast ancient cities beneath the canopies of Crete, Central and South America. Hidden beneath trees are plazas, pyramids, roads, and networks of canals stretching for miles. Some sites rival modern cities in size, suggesting populations in the hundreds of thousands. Over time, vines, roots, and soil reclaimed these structures until they became indistinguishable from the forest itself. Walking through such a jungle means treading unknowingly above stone temples and streets, history buried in green silence. The jungle is not only home to animals and plants, it is also a vault of human stories, cities erased by time but preserved beneath the relentless embrace of TAC. The forest. The Amazon jungle creates a flying river of moisture in the sky. Above the Amazon basin flows an invisible river, not of water on land, but of vapor in the sky. Billions of trees release moisture through their leaves, a process known as transpiration. Together, they exhale so much vapor that it gathers into a massive plume drifting westward, carrying more water than the mighty Amazon River itself. This flying river sustains rainfall not only in the forest, but also across distant farmland and cities thousands of miles away. Without it, parts of South America would dry into barren landscapes. Satellites have captured these streams of vapor as they rise, proving how powerfully the jungle shapes weather. The Amazon is not just a local ecosystem, it is a climate engine influencing an entire continent. To know that trees summon rivers in the air is to realize that jungles are architects of the sky as much as of the land. Certain plants release fragrances smelling of rotting flesh. In the jungle, survival often depends on attracting pollinators, and some plants achieve this in the strangest of ways. Flowers like the corpse lily and Titan Arum produce odors that mimic decaying meat. To human senses, the stench is overpowering, enough to make people recoil. But to flies and beetles that normally feed on carrion, it is irresistible. Drawn by the scent, they crawl deep into the flower, inadvertently carrying pollen with them. This strategy is crucial for plants that bloom rarely or briefly, ensuring that their brief moment of flowering is successful. Some blossoms are massive, others small and inconspicuous, but all share the same trick of deception. In the jungle, sweetness is not always the way to attract life. Sometimes, the foulest smell serves the most vital purpose, turning decay into a lure and making pollination a drama of disguise. Jungle rivers hide electric eels that can deliver shocking jolts. Beneath the muddy waters of the Amazon swim electric eels, among the most remarkable fish in the world. Despite their name, they are not true eels, but relatives of catfish. They can grow over 8 feet long and possess thousands of specialized cells called electrocytes. By discharging them in unison, the eel generates shocks up to 600 volts, enough to stun prey or deter predators. These jolts are so powerful that they can knock a human off balance or cause an animal to retreat instantly. Yet electric eels also use gentler pulses like radar, mapping their environment in dark, murky waters. In the flooded forests where visibility is poor, electricity becomes both weapon and sense. To encounter one is to witness a creature that has mastered an invisible force, carrying lightning in its body as naturally as lungs carry air. Some jungle insects can walk on water. At the edges of jungle streams, delicate insects called water striders perform a quiet miracle of physics. Their legs are long and tipped with microscopic hairs that repel water, allowing them to distribute their weight across the surface without sinking. They skate effortlessly, darting across pools and rivers in pursuit of prey. From above, their movements ripple outward in perfect circles. For these insects, the water's surface is not a barrier, but a pathway, a hunting ground, and an escape route in one. They feed on small creatures that fall into the water, recycling energy back into the ecosystem. To see them skim across a glassy pool is to realize that in the jungle, even the laws of nature are stretched into possibility. The line between air and water becomes a stage, and creatures learn to dance upon it. Macaws can live for more than 50 years in the wild. Brilliant flashes of red, blue, and yellow sweep across the canopy when macaws take flight. These parrots are not only striking in appearance, but also remarkable in longevity. In the wild, many macaws live for more than 50 years, and some in captivity surpass 70. They form lifelong pair bonds, with mates often seen flying together, calling back and forth in constant communication. Their intelligence allows them to solve problems, mimic sounds, and pass knowledge to their young. In the jungle, their loud voices echo for miles, helping flocks stay together as they search for fruit and nuts. A single macaw may outlive multiple generations of other animals, becoming a steady presence in the forest for decades. To think of a bird watching the jungle change over half a century is to glimpse the deep, slow rhythms of life in the canopy. There are fungi that turn ants into zombies. The jungle hides dramas stranger than fiction, and few are more unsettling than the story of zombie ants. A parasitic fungus called Ophiocordyceps infects an ant and begins to grow inside its body. The fungus releases chemicals that alter the ant's behavior, compelling it to climb a plant and bite into a leaf or stem. Once anchored, the ant dies, and the fungus bursts forth, releasing spores that drift down to infect others. Each species of fungus is specialized to target a specific type of ant, a chilling precision honed by evolution. For the colony, these infections can spread like wildfire, disrupting entire populations. To witness an ant frozen in place, with a strange stalk sprouting from its head, is to see nature's darker side, an organism controlling another from within. In the jungle, even minds can be conquered in the endless struggle for survival. Some trees can flood entire valleys with their roots. In the jungle, roots can dominate landscapes as much as trunks and branches. Certain figs and banyan trees send down aerial roots from their branches, like living ropes. Over decades, these roots thicken into secondary trunks, spreading outward in all directions. Eventually, a single tree can give rise to a whole forest of interconnected pillars, shading an area that once stretched across open ground. In some valleys, these sprawling root systems alter the flow of water, creating new wetlands and redirecting streams. For animals, such root forests become shelter. Monkeys leap between columns, birds nest in hollows, and snakes coil within their shade. Humans, too, have noticed their power, with some cultures using the trees as gathering places and landmarks. A banyan or strangler fig is more than just a plant. It is an ecosystem, a living cathedral, capable of reshaping the very terrain beneath it. Jungle clouds release nutrients back to the soil. The jungle does not just recycle water, it also recycles life. As trees release moisture into the air, tiny particles of organic matter rise with it. Pollen grains, fungal spores, fragments of leaves, and even microscopic life are swept upward into forming clouds. When rain falls again, these nutrients return to the soil, feeding plants far below. Scientists studying rainfall in the Amazon have detected traces of phosphorus, nitrogen, and calcium in every drop. This means that rain is not simply water, it is a delivery system for fertility, a sky-borne compost heap feeding the earth. In places where jungle soils are thin and easily leached, this nutrient cycle keeps the forest alive. The clouds are not just weather above the trees, they are extensions of the forest itself, rising and falling, carrying the building blocks of life in endless rhythm. The Amazon houses more than 2.5 million species of insects. The scale of insect diversity in the Amazon is almost beyond human comprehension. Scientists estimate that more than 2.5 million species live there, though only a fraction have been formally described. In a single square mile, thousands of different beetles, moths, ants, and flies can be found, many entirely unknown to science. Researchers once examined a single tree and discovered hundreds of unique beetle species clinging to its bark and leaves. These insects pollinate flowers, recycle nutrients, and form the foundation of the food web that sustains everything else. Without them, the jungle would collapse. Their abundance is also staggering. Trillions upon trillions of individuals living and dying in cycles so vast they are invisible to us. To walk through the Amazon is to walk through a storm of life so diverse that we may never know it in its entirety. There are spiders that fish using silk lines. Not all spiders weave delicate webs in branches. Some jungle species specialize in fishing. These spiders perch on the edges of streams, lowering silk lines onto the surface of the water. Sensitive hairs on their legs detect the ripples of swimming insects or small fish. With lightning speed, the spider pulls up its line and seizes the prey, wrapping it in silk before it can escape. Some species are even capable of diving beneath the surface, using air bubbles trapped in their hairs to breathe as they pursue underwater prey. Watching a spiderfish challenges every assumption we might hold about these creatures. In the jungle, they are not limited to the air or the land. They are hunters of rivers as well, using silk, the same material that catches flies, to reel in creatures from the water's surface. Some vines grow in spiral patterns that twist around trees. The jungle is thick with climbing plants, and many have evolved strategies to secure their place in the race for sunlight. Some vines, called lianas, spiral upward around tree trunks in graceful, tightening curves. Their spiral growth is not random. It maximizes stability and allows the vine to cling tightly without breaking. These twisting forms can take on sculptural beauty, wrapping trunks in patterns that look almost deliberate. For animals, the spirals are useful too. Frogs climb them, monkeys swing from them, and birds perch along their coils. Yet beneath the elegance is competition. By entwining around trees, vines often weaken or strangle their hosts, using another's strength to fuel their climb. In this way, the jungle creates shapes that are at once beautiful and ruthless, spirals that seem like art, but which are really strategies for survival in a crowded world. Jaguars often hunt by swimming. Unlike most big cats, jaguars are at home in the water. They are powerful swimmers, using rivers as hunting grounds. In the flooded forests of the Amazon, they glide silently through channels, their spotted coats blending with dappled light on the surface. Jaguars hunt capybaras, caimans, turtles, and even large fish, using their extraordinary bite to pierce skulls and shells. Their affinity for water makes them unique among the great cats, feared not only on land but also in the rivers that thread through the jungle. This dual mastery gives jaguars an advantage few predators possess. To see one slip into the water, barely disturbing the surface, is to witness an apex hunter moving with perfect confidence. In the jungle, even rivers are not safe havens. They are extensions of a jaguar's hunting ground, patrolled by stealth and strength combined. Some jungle frogs carry their tadpoles on their backs. Parental care in the jungle takes many surprising forms, and among frogs, some species go to astonishing lengths to protect their young. The poison dart frog, for instance, carries its tadpoles on its back, ferrying them one by one to tiny pools of water in bromeliads high above the ground. There, each tadpole is deposited in its own miniature pond, safe from predators. The parent may return to feed them, laying unfertilized eggs as food until the young are strong enough to survive alone. This behavior ensures that more offspring reach maturity, despite the dangers of the forest floor. Watching a frog, small enough to rest on a fingertip, carefully carrying its squirming young up into the canopy, shows a tenderness often hidden in the wild. In the jungle, survival is not only about strength and competition, but also about care and devotion across generations. A single tree can drop billions of seeds each year. Reproduction in the jungle often takes place on a grand scale. Some towering trees produce such immense quantities of seeds that their yearly output can number in the billions. Each seed is tiny, a speck carried on the wind, washed into rivers, or spread by animals. Most will never grow, falling to the forest floor where competition is too fierce. But sheer numbers increase the odds that a few will find the light and space needed to thrive. The mass release of seeds can transform the forest, carpeting the ground with potential new life. Birds and mammals gorge on the bounty, spreading seeds even farther. This strategy reflects the jungle's balance: abundance matched with attrition, possibility matched with loss. Every towering tree we see today represents one seed among billions that survived the gauntlet of chance. Some jungle insects mimic leaves so perfectly they disappear. Camouflage in the jungle is an art form perfected by countless species. Among the most striking examples are insects that mimic leaves so precisely they seem to vanish. Leaf insects and certain katydids have bodies shaped with veins, edges, and even tiny spots that look like decay. When they rest on real leaves, they are almost indistinguishable, fooling predators that rely on sight. Some species even sway gently as if moved by wind, completing the illusion. This disguise protects them from birds, lizards, and other hunters in the dense forest. The level of mimicry is so astonishing that even trained scientists sometimes overlook them in plain sight. In a place where life is everywhere, sometimes the best survival strategy is invisibility. These insects remind us that in the jungle, being unseen can be as powerful as any weapon. Jungle rivers can reverse their flow with the seasons. In parts of the Amazon basin, rivers behave in ways that defy expectation. During the rainy season, the Amazon swells so massively that its tributaries overflow, reversing their flow. Water that once rushed toward the main river is forced back into surrounding forests and wetlands. Entire regions become submerged, creating flooded jungles where fish swim among tree trunks and dolphins glide beneath branches. This seasonal reversal reshapes the ecosystem, spreading nutrients and opening habitats for countless species. When the waters recede, they leave behind rich soils and pools that sustain life until the rains return. The idea of a river flowing backward may seem impossible, yet in the Amazon, it is part of the yearly rhythm. It is one more reminder that in the jungle, the forces of nature operate on scales both vast and bewildering, sculpting the land in cycles of flood and retreat. The Amazon basin creates its own thunderstorms. The Amazon is so vast and so alive that it can summon storms out of thin air. Each day, billions of trees release water vapor into the atmosphere. This moisture rises, condenses, and forms towering clouds that often ignite into thunderstorms. The storms are not just products of regional weather patterns, they are generated directly by the forest itself. The energy released can be staggering. Lightning flashing across the canopy, thunder rolling through valleys, and torrents of rain that drench the ground in minutes. These self-made storms recycle water, cooling the air and nourishing the soil. Without them, the basin would dry, the trees would wither, and the system would collapse. The Amazon is not just a passive receiver of weather, it is a living engine that generates its own sky-born drama, a forest so vast it commands the atmosphere above it. Some ant colonies are so large they can be seen from space. Ants are small, but in the jungle, their colonies can rival the scale of cities. Certain leafcutter ant colonies sprawl across hundreds of feet underground, with millions of individuals cooperating in a perfectly ordered society. The tunnels and chambers they excavate displace so much soil that satellite imaging can pick up their patterns. In some parts of South America, entire landscapes are dotted with regular mounds, each one marking the site of an ancient colony that may have lasted for centuries. These supercolonies function as living machines. Farmers, soldiers, builders, and royalty, all working in unison. The scale is so vast that ants can shape forests, controlling which plants thrive by pruning or harvesting leaves. To know that something as small as an ant can leave marks visible from space is to realize how collective power can transform even the greatest landscapes. Certain jungle trees produce fruits larger than basketballs. High in the canopy of South America grows the jackfruit's giant relative, producing fruits so enormous they can weigh more than 100 pounds. These massive fruits hang directly from tree trunks, like swollen lanterns of green. Inside, hundreds of seeds and sweet pulp provide food for monkeys, birds, and people alike. Their sheer size is an evolutionary strategy. By creating such large and nutrient-rich packages, the tree ensures its seeds will be carried far and wide by many consumers. For those who live near these giants, a single fruit can feed an entire family. Walking beneath their branches, one has to watch carefully. A falling fruit of that size could cause serious injury. The jungle, always abundant, sometimes takes abundance to extremes, producing fruits that dwarf human effort and remind us of the incredible fertility, tropical life. Some jungle rivers flow underground for hundreds of miles. Not all rivers in the jungle run above ground. In certain regions, water carves secret channels beneath the surface, creating underground rivers that flow for hundreds of miles. In Brazil, scientists discovered one such subterranean river, the Hunza, running nearly parallel to the Amazon itself, hidden deep within the earth. Though invisible from the surface, it carries enormous volumes of water, shaping ecosystems in ways only now being understood. These hidden rivers may surface as springs, feeding wetlands or nourishing forests in unexpected places. For centuries, local communities spoke of rivers beneath rivers, their existence dismissed as myth. Now science confirms that the jungle's hydrology is even more complex than imagined. Water above, water below, all moving in endless cycles. To realize that vast unseen rivers are coursing silently beneath the jungle is to glimpse a second, hidden world flowing underfoot. There are fish that leap into trees to eat fruit. In flooded forests, where rivers rise and submerge entire groves, fish take on remarkable behaviors. One such adaptation is fruit eating. When trees drop berries and figs into the water, schools of fish rush to feed, snapping them up like floating treasure. Some species go further, leaping out of the water to pluck fruit directly from overhanging branches. This diet makes them important seed dispersers, spreading plants across vast areas as they pass seeds intact through their digestive tracts. In a place where trees and rivers merge each season, fish have become gardeners of the forest, carrying new generations of plants to unexpected places. Watching a silver flash leap from the water to snatch fruit is a startling reminder that in the jungle, even the line between river and forest is blurred, and fish play roles we would never imagine in shaping the land. Jungle termites build air-conditioned homes. In the sweltering humidity of the jungle, some termites have engineered their own climate control. Their towering mounds, sometimes taller than a person, are riddled with vents and tunnels that channel air in precise ways. These designs regulate temperature and humidity inside the mound, keeping conditions stable for the millions of termites that live there. Scientists studying the structures have found them to be masterpieces of natural engineering, passive cooling systems that humans now try to replicate in architecture. The termites' survival depends on cultivating fungus gardens within their chambers, and maintaining the right environment is critical. To see such a mound is to witness not just a pile of dirt, but a living skyscraper designed by creatures smaller than a fingernail. Their homes stand for decades, outlasting generations of builders, proof of the collective genius woven into jungle life. Some bats sleep inside leaves they fold around themselves. In the jungle canopy, not all bats roost in caves. Some tiny species, like the tent-making bat, carve out a home in broad tropical leaves. They chew through the veins of the leaf so it droops into a protective tent, then crawl inside to rest during the day. Dozens may gather beneath a single shelter, their tiny bodies hidden from predators and rain. By evening, they emerge again, flitting through the trees in search of fruit or insects. The behavior is remarkable not only for its ingenuity, but also for its impact. By modifying plants into shelters, these bats act like architects. shaping the forest in small but meaningful ways. To find one of these leafy tents is to discover a secret world folded neatly in green, a reminder that in the jungle, every leaf can become a home for life. Parrots use clay licks to neutralize plant poisons. In many parts of the Amazon, flocks of brightly colored parrots gather on riverbanks, where they descend to peck at exposed clay walls. At first glance, the sight of birds eating dirt seems strange, but the clay serves an essential purpose. It neutralizes toxins found in the seeds and fruits that make up much of their diet. The minerals bind to the poisons, allowing the parrots to safely digest foods that might otherwise harm them. These gatherings are spectacular. Hundreds of macaws and parakeets crowding the banks, their feathers flashing in a rainbow of hues. Their calls echo over the river as they squabble and feed, turning the clay lick into a living kaleidoscope of sound and color. What looks like unusual behavior is in fact survival strategy. Another example of how animals in the jungle use the land itself as a partner in life. Some jungle frogs are transparent, showing their beating hearts. In the humid jungles of Central and South America live tiny glass frogs, named for their extraordinary appearance. Their skin and even parts of their muscles are translucent, allowing observers to see their bones, organs, and beating hearts. This transparency provides camouflage, blending them into the light-speckled leaves they rest upon at night. When viewed from below, they seem almost invisible, their outlines dissolving into the greenery. For scientists, studying glass frogs is like watching biology in motion, a rare window into the inner workings of a living creature. Their delicate bodies also reflect the fragility of their habitats, which are vulnerable to deforestation and climate change. To hold one in the palm is to cradle a living jewel, a creature whose body reveals life's inner rhythms in the most literal and mesmerizing way. In the jungle, some plants release heat to attract insects. Most plants rely on scent or color to attract pollinators, but a few go further, generating heat. These thermogenic plants, such as certain arons, can raise their temperature well above the surrounding air. The warmth helps spread their scent more effectively, often mimicking the smell of decay to draw in flies and beetles. For the insects, the heated flower also provides a cozy shelter, encouraging them to linger longer and increasing the chances of pollination. The energy cost for the plant is immense, but the payoff is success in reproduction. To walk past one of these blooms is to feel a surprising rush of warmth radiating into the cool jungle air. It is one more reminder that in the tropics, survival strategies can border on the miraculous, as even plants find ways to bend the laws of nature to their advantage. Some jungle flowers smell like chocolate or vanilla. Not all jungle scents are heavy and musky. Some flowers have evolved aromas that echo the sweetest indulgences. Certain orchids release a fragrance that smells remarkably like vanilla, while others mimic the warm richness of chocolate. These scents are not meant for us, but for pollinators. Bees, butterflies, and moths are drawn to the sugary perfume, which promises nectar and pollen. For humans wandering through the forest, the experience can be disorienting. To catch the scent of dessert in the middle of dense greenery is like stumbling into an invisible kitchen. The diversity of these perfumes reflects the competition among plants to stand out in an environment already overflowing with flowers. In the jungle, survival may come down to who smells most enticing. By producing the scent of sweetness, flowers create irresistible invitations, reminding us that allure is as much a weapon as color or shape. The Amazon has pink river dolphins that can turn their heads. Gliding through the flooded forests of the Amazon are dolphins unlike any others. Their skin glows with a soft pink hue, ranging from blush to vivid rose, depending on age and activity. Unlike ocean dolphins, these river dwellers have flexible necks, allowing them to turn their heads from side to side. This adaptation helps them navigate tight, twisting waterways, weaving between submerged trees and roots. They also have long, slender snouts, perfect for catching fish in the murky shallows. Local legends often portray them as mystical beings, shapeshifters that walk among humans at night. Scientists, meanwhile, marvel at their intelligence and social behavior. These pink dolphins embody the strange and beautiful adaptations of the Amazon, mammals that have left the open seas behind to master rivers instead, living among brabah, flooded jungles where water and forest blend into one extraordinary realm. Certain ants keep aphids as tiny cattle. Ants in the jungle have perfected farming not only with fungi, but also with living creatures. Some species herd and protect aphids, treating them much like farmers treat cattle. The aphids feed on plant sap and excrete a sweet liquid called honeydew, which the ants eagerly collect. In return, the ants guard their tiny herds from predators and even move them to fresh leaves when food runs out. This mutual relationship blurs the line between instinct and agriculture. Watching a line of ants tending to aphids reveals a miniature pastoral scene played out on stems and leaves instead of fields and barns. The ants stroke the aphids gently with their antennae to encourage more honeydew, a gesture both strange and tender. In the dense jungle where survival often means invention, ants have reinvented farming again and again, showing that cooperation can evolve in many unexpected forms. Some jungle trees can pump water against gravity to great heights. Towering jungle trees rise more than 200 feet, yet every leaf at the top requires water drawn from the soil below. To achieve this, trees perform one of nature's greatest feats. Through a combination of root pressure, capillary action, and the pull of evaporation, they pump water upward against gravity through xylem tubes thinner than a hair. At full strength, a single tree can move hundreds of gallons in a day. The process is so efficient that water can climb to dizzying heights without mechanical pumps or moving parts. Scientists still marvel at the exact physics, which rely on cohesion among water molecules, each droplet pulling the next upward in an unbroken chain. To stand beneath such a tree is to stand under a living pump system operating silently, a reminder that the jungle's giants are not passive, but engines of flow and life. The canopy is so dense, it can take rain 10 minutes to reach the ground. When storms break over the jungle, rain does not always fall directly to the soil. Instead, it lands first on the canopy, where vast layers of leaves intercept the drops. Water trickles slowly downward, bouncing from leaf to leaf, pooling briefly and dripping again. In some forests, this cascade can take up to 10 minutes to reach the ground. The delay creates a constant, rhythmic soundscape, the roar of rain above, followed by softer drips below. It also affects life at every level. Epiphytes drink directly from canopy leaves. Frogs hide in the miniature pools that form. And the forest floor receives a gentle, filtered rain instead of a flood. What feels like one storm is really many storms, staggered in time. Even water learns patience in the jungle, turning a single rainfall into an extended performance across layers of green. Some vines can store water inside their hollow stems. In the heat of the jungle, water is everywhere, but not always where you need it. Some vines, called water lianas, have developed the ability to store large amounts of water in their hollow stems. Indigenous people have long known how to cut into these vines and drink from them, using them as natural canteens. For animals, the vines provide vital reserves during dry spells, offering hydration when streams run low. The stored water is often clean and cool, filtered by the plant itself. These vines are more than simple climbers. They are reservoirs, lifelines running high above the forest floor. In a place where survival can hinge on access to fresh water, their adaptation is a quiet marvel. Hidden within their woody shells, they carry the very essence of life, waiting to be tapped when the jungle grows thirsty. The jungle floor can stay wet for weeks after a storm. Rain does not vanish quickly in the jungle. Once it falls, the dense canopy, thick undergrowth, and heavy soils trap water in countless forms. Puddles linger for weeks, feeding mosquitoes and frogs. Mosses and fungi absorb the moisture, releasing it slowly. Even the air itself stays damp, humidity pressing against the skin. For humans, this wetness can feel oppressive, but for life, it is a constant gift. Seeds germinate quickly in moist soil, leaves remain lush, and amphibians thrive. The downside is that decay also accelerates. Fallen branches rot within days, returning nutrients to the ground. The jungle is a place where water is never truly absent. Even after storms pass, their legacy remains for weeks, soaking the earth, saturating the air, and sustaining the endless cycle of life that flourishes in the shadows of Carl. The Green Cathedral. Some insects sing at volumes louder than chainsaws. The jungle is alive with sound, and some of its loudest performers are tiny insects. Certain cicadas and katydids produce calls so powerful they can exceed 100 decibels, louder than a chainsaw at close range. Their songs are created by vibrating special membranes, amplified by hollow bodies. To human ears, the noise can be overwhelming, a wall of sound that fills the air from dawn until dusk. For the insects, however, it is essential communication, drawing mates and staking territories. The din creates a chorus that defines the jungle's soundscape, blending with birds, frogs, and monkeys into an almost continuous roar of life. At night, other insects take over, ensuring the music never stops. The fact that such tiny creatures can produce such overwhelming sound is one of the jungle's paradoxes. The smallest voices often make the loudest mark. In some jungles, day and night are equally loud with life. Silence is rare in the jungle. By day, birds call, monkeys shriek, and insects buzz in deafening layers. As the sun sets, a shift occurs, but not into quiet. Instead, frogs begin their croaks, cicadas scream, and nocturnal creatures add their voices. The sound may change in tone, but not in intensity. In some forests, the nighttime chorus is just as loud as the daytime one, creating a continuous cycle of noise that never truly ceases. For those unaccustomed, the jungle can feel overwhelming, as though the air itself vibrates with voices. Yet for the creatures within, this is the language of survival, calls to mates, warnings of predators, and declarations of presence. In this way, the jungle is always awake. Whether bathed in sunlight or cloaked in darkness, life fills every moment with sound, refusing to let the forest rest. Some plants can grow entirely inside the hollows of trees. Trees in the jungle are not always solitary beings. Many host entire gardens within their hollows. Seeds carried by birds or wind settle into crevices where water and decaying leaves collect. There, they sprout into small ferns, orchids, or even miniature trees. Over time, these inner residents grow into lush microforests inside the larger host. Some animals depend on them, nesting in the hollows or drinking from the water that collects there. The result is a layered system, one tree hosting many, each supporting further webs of life. From the outside, the tree may appear ordinary, but within it is a hidden world of greenery. The jungle, already dense and layered, folds in upon itself, turning even a single trunk into a habitat. It is a reminder that in this environment, no space is wasted. Every crevice becomes an opportunity for life. The Amazon is home to the world's largest snake, the green anaconda. In the swamps and rivers of the Amazon lurks the green anaconda, the heaviest snake in the world. Some individuals can grow over 25 feet long and weigh more than 500 pounds. Despite their massive size, these snakes are stealth hunters. They lie submerged in water, eyes and nostrils barely above the surface, waiting for prey to approach. When the moment comes, they strike with incredible speed, coiling their muscular bodies around capybaras, caimans, or even deer. Unlike venomous snakes, anacondas kill by constriction, tightening until their prey can no longer breathe. Though their reputation inspires fear, attacks on humans are exceedingly rare. More often, these giants play an essential role in controlling populations of other large animals. To see one is to glimpse raw power and ancient design, a living reminder of the prehistoric world, where reptiles once ruled with quiet patience. Overwhelming strength. Jungle bees can make blue or red honey depending on the flowers. Most honey we know is golden, but in the jungles, bees sometimes create honey in extraordinary colors. By collecting nectar from unusual flowers or even fruit, their honey can take on shades of blue, red, or deep purple. The color reflects the chemistry of the plants, rich in pigments and unique compounds not found elsewhere. These honeys are rare, often seasonal, and sometimes used in traditional medicines for their unusual properties. In local markets, jars of vividly colored honey look almost unreal, shimmering like stained glass. For the bees, of course, it is simply food, concentrated energy to sustain their hives. For humans, it is a reminder of how diverse and surprising the jungle's offerings can be. Even something as familiar as honey becomes extraordinary when filtered through the infinite variety of tropical plants and the tireless work of bees. Some monkeys teach their young complex calls. In the noisy jungle, communication is essential, and some monkeys pass down their knowledge through teaching. Young monkeys learn to recognize and reproduce alarm calls that warn of predators, as well as social calls that signal food or maintain group bonds. Studies have shown that older individuals actively correct mistakes, reinforcing the right sounds until the young can produce them accurately. This learning process mirrors aspects of human language, where culture and practice shape communication. In species like capuchins and howler monkeys, the range of calls is vast, each with subtle variations. The fact that these vocal traditions are taught, not just instinctive, suggests that monkey societies are rich with culture passed between generations. In the canopy, every voice is part of a conversation, one that echoes through families, teaching survival and connection in a world that demands both vigilance, cooperation. There are plants that can grow new leaves in a single night. Growth in the jungle is often explosive, and some plants push the limits of speed. Certain species can produce new leaves so rapidly that they unfurl overnight. At dusk, a bud may be tightly coiled, but by morning it has spread wide, capturing sunlight. This acceleration allows the plant to take advantage of sudden rains or breaks in the canopy. Observers describe the sound of leaves cracking and stretching as they grow, a faint rustle in the darkness. The rapid growth comes at a cost, thin tissues that are vulnerable to insects and disease. Yet the gamble often pays off, giving the plant a head start in the endless race for light. To wake and see new green where none existed the evening before is to witness the jungle's restless energy, where life never pauses, even in the hours when we sleep. Jungle ants have a social system more complex than many mammals. Ant colonies in the jungle are paragons of organization. Millions of individuals live in intricate societies with divisions of labor so precise they rival the complexity of mammalian communities. Workers forage, soldiers defend, nurses tend to the young, and specialized castes perform unique roles. Communication is constant, using chemical signals that function like language, coordinating activities across vast distances. Some colonies wage wars, form alliances, or even enslave other ants, demonstrating behaviors that mirror politics and strategy. The colony itself behaves like a superorganism, with each ant serving as a cell in a larger body. Scientists studying these systems compare them to human cities, dynamic, ordered, and endlessly adaptive. To look at a column of jungle ants is to see not chaos, but choreography, a collective intelligence greater than the sum of its parts, pulsing beneath the forest, floor and canopy alike. Some butterflies can see light invisible to humans. Butterflies in the jungle perceive the world in ways we cannot. Many species can see ultraviolet light, a spectrum invisible to human eyes. To us, their wings may appear simply colorful, but to them, they are covered in hidden patterns glowing with ultraviolet signals. These markings act like secret codes, guiding courtship, territory, and recognition. The ability extends beyond wings. Flowers, too, reveal ultraviolet nectar guides, luminous pathways pointing pollinators toward food. For butterflies, the jungle is painted in colors we can only imagine, a kaleidoscope far richer than what we perceive. Scientists have used special cameras to glimpse this hidden world, but for the butterflies, it is simply reality. They move through forests lit with signals invisible to us, proof that the jungle holds dimensions of beauty forever beyond our direct experience, reserved for DARS. Eyes tuned to other frequencies of light. The Amazon's flooded forests create underwater jungles. Each rainy season, the Amazon swells and overflows, submerging vast areas of forest. Entire groves of trees vanish beneath muddy waters, creating surreal underwater jumbles. Fish swim among trunks and branches, feeding on fruits and seeds that drop into the water. Dolphins glide through the flooded groves, hunting in a world where the boundary between land and river has dissolved. For months, these submerged forests thrive as aquatic ecosystems, supporting unique species adapted to the cycle of flood and retreat. When the waters recede, the ground reappears, enriched by nutrients carried in the flood. This seasonal transformation is one of the most dramatic in nature. Forests becoming rivers, rivers becoming forests. It shows how flexible life can be in the tropics, where ecosystems do not remain fixed, but shift fluidly, adapting to the pulse of rain that drives everything. Some trees release seeds that can float across oceans. The jungle's reach often extends beyond its own borders. Certain trees, like mangroves and coconuts, release seeds designed to float for months or even years across the sea. Encased in tough shells, these seeds drift with currents, carried to distant shores where they may sprout into new forests. This strategy has allowed tropical plants to colonize islands and coastlines far from their origins, turning the ocean itself into a dispersal network. For centuries, sailors found coconuts washed up on beaches thousands of miles from where they grew, proof of their endurance. Each floating seed carries not only the potential for a new tree, but also the story of resilience and expansion. In this way, jungles are not confined to land. They send emissaries adrift, trusting the sea to carry their lineage into the unknown, expanding the green frontier one seed at a time. Jungle rainfall can be recycled several times before leaving the forest. Rain in the jungle does not simply fall once and vanish. The process of transpiration, trees releasing moisture into the air, ensures that much of it cycles back as new rain. Studies in the Amazon suggest that a single droplet of water can fall, evaporate and fall again as many as 5 or 6 times before drifting away. This recycling effect keeps the forest perpetually moist, maintaining the lushness that defines it. Without this system, the Amazon and other jungles would dry dramatically, unable to sustain their vast biodiversity. Each cycle of rainfall is like a heartbeat, pulsing through the forest, renewing life again and again. It means that the jungle's rains are not only a gift from the sky, but also a creation of the forest itself, a self-sustaining loop that embodies the balance and interdependence of life within it. There are lizards that run across water, In the sunlit streams of the jungle lives the basilisk lizard, often nicknamed the Jesus Christ lizard for its astonishing ability to run across water. When threatened, it dashes upright on its hind legs, slapping the surface with its feet in rapid succession. Specialized fringes on its toes trap air, giving it enough lift to keep from sinking for several yards before it drops beneath the surface. This skill allows it to escape predators quickly, vanishing into the opposite bank or diving to safety. Watching one sprint across a pond is like witnessing a miracle, a defiance of gravity and expectation. For the basilisk, it is simply survival, but for observers, it feels like magic made real. In the jungle, even physics seems flexible, and creatures find ways to turn water into a pathway rather than a barrier. Some jumbled trees can explode when struck by lightning. In the dense humidity of the jungle, lightning strikes carry astonishing power. When they hit certain trees, the heat is so intense that the water stored inside the trunk instantly vaporizes. The sudden expansion creates explosive pressure, causing the tree to split apart or even shatter violently. Massive chunks of wood are hurled outward, leaving behind a scarred crater of splinters. For animals sheltering nearby, the event can be deadly, like a natural bong erupting from the canopy. These explosions are rare, but they remind us of the immense energy locked inside even a single storm. To witness one is to see nature's raw power released in an instant. Electricity, water, and wood combining into a devastating burst. In the jungle, where everything holds water, even lightning is amplified, turning trees into thunderclaps of destruction and altering the forest in a flash. Orchids in jungles have more than 25,000 species. The orchid family is one of the largest groups of flowering plants on Earth, and jungles are their greatest stage. With more than 25,000 known species, orchids come in a dizzying array of colors, shapes, and strategies. Some mimic insects to lure pollinators, others bloom only at night, and still others thrive high in the canopy, drinking rain from the air. Each species is finely tuned to its environment, its survival tied to specific pollinators or conditions. Some are so rare they bloom only once every few years. For people exploring the jungle, the sight of orchids feels like a hidden treasure, delicate splashes of beauty among the endless green. To realize that tens of thousands of variations exist is to grasp the depth of biodiversity within tropical forests. Orchids are not just flowers, they are emblems of adaptation, diversity, and the jungle's infinite creativity. Certain insects communicate using drums on leaves. Communication in the jungle is not limited to sound, and some insects use vibration. Katydids and tree hoppers, for example, tap or drum on leaves to send messages. The vibrations travel through plant tissues, reaching others nearby who respond in kind. To human ears, these signals are silent, but with special equipment, scientists can hear the rhythms, patterns of knocks and pulses that carry information about gene, territory, mating, or danger. Entire conversations unfold across a network of leaves, hidden beneath the louder calls of birds and frogs. This form of communication shows that the jungle has layers of voices, some audible, others secret and subtle. The forest is not only alive with sound, but also with invisible tremors, a silent orchestra playing beneath the cacophony. For the insects tapping their tiny drums, each leaf is both a stage and a telephone line. Some jungle frogs guard their eggs from predators. Parental care in the jungle often takes remarkable forms, especially among frogs. While many simply lay eggs and depart, some species actively guard their clutches. They remain nearby, fending off ants, insects, and other small predators that might consume the vulnerable eggs. In some cases, the parent hydrates the eggs by carrying water in its skin or by sitting atop them to keep them moist. These efforts dramatically increase the chances of survival in a place where danger is constant. The devotion is striking in animals so small, yet it shows the universal power of parental instinct. Each guarded clutch represents a gamble of energy and risk, but the reward is the continuation of the species. In the chaos of the jungle, where life is abundant but fragile, the quiet image of a frog watching over its eggs reveals tenderness amid struggle. Fireflies in jungles can synchronize their flashes. In the warm nights of the jungle, fireflies sometimes gather in astonishing displays. Instead of flashing at random, entire groups coordinate their pulses of light, glowing and dimming in unison. These synchronized flashes can stretch across trees and riverbanks, creating waves of light that ripple through the darkness. The effect is mesmerizing, as though the forest itself is breathing with luminous rhythm. Scientists believe the synchronization helps males attract females more effectively, creating a chorus of light much like the songs of frogs or cicadas. For humans, witnessing such a display feels like stepping into another world, where stars have descended into the branches. The jungle is already alive with sound, scent, and movement. But in these moments, it also becomes alive with light, a symphony of biology and physics, a reminder that beauty is as integral to survival as strength or cunning. Some plants can change their leaf shape as they grow taller. Adaptation in the jungle often means flexibility, and some plants take this literally. Certain species change the shape of their leaves as they mature. Young plants, growing in the dim light of the understory, produce broad, thin leaves to capture as much sunlight as possible. As they climb higher and reach the brighter canopy, their leaves become narrower, thicker, or differently angled to withstand stronger light and wind. This transformation allows one plant to optimize survival at different stages of growth. To the observer, it may seem like two different species until closer inspection reveals the truth. This ability to alter form over time is one more way the jungle fosters resilience. Life here is not static. It evolves within a single lifetime, reshaping itself to meet challenges as they come, showing that even leaves are dynamic tools of survival. The Amazon jungle alone stores more carbon than any other ecosystem. The Amazon is often called the lungs of the earth, and for good reason. Its vast expanse of trees and plants stores more carbon than any other ecosystem on the planet. Each year, billions of tons of carbon dioxide are absorbed from the atmosphere, locked away in trunks, roots, and soils. This storage slows the pace of climate change, acting as a buffer for the entire Earth. When the forest is damaged, however, that carbon can be released back, magnifying global warming. Scientists studying the Amazon emphasize that protecting it is not only a matter of conserving biodiversity, but also of safeguarding the planet's climate. Balance. To imagine billions of trees working in concert to regulate the air we breathe is humbling. The Amazon is more than a forest of life. It is a planetary safeguard, quietly stabilizing Earth's atmosphere with every breath of green. Some jungle trees are older than recorded human history. Amid the ever-changing jungle, where decay and renewal happen constantly, there are trees that endure for millennia. Some massive individuals, like certain ceiba or fig trees, have lifespans stretching back thousands of years. They were already old when human civilizations first began to record their histories. These giants bear witness to centuries of storms, floods, and human arrivals, standing as living monuments to resilience. Their immense trunks host entire communities of life, from orchids to insects to monkeys, each relying on the stability of the ancient host. For local cultures, these trees often become sacred symbols, their age lending them authority and reverence. To stand beneath one is to feel time collapse, to realize that the span of human memory is short compared to the life of a tree. The jungle holds not only life abundant, but also life ancient beyond imagination. There are fungi that glow green in the dark, On damp jungle nights, faint green glows sometimes appear on fallen logs or leaf litter. These are bioluminescent fungi, organisms that produce their own light through chemical reactions. The glow, sometimes called foxfire, can be bright enough to read by in the darkest corners of the forest. Scientists believe the light may attract insects that help spread spores, or it may serve as a defense by startling predators. Whatever the purpose, the effect is enchanting. A rotting log becomes a lantern, the forest floor sprinkled with glowing stars. For humans, stumbling upon this glow feels magical, as though the earth itself is lit from within. The fact that decay, usually hidden and silent, can shine so beautifully is a reminder that in the jungle, even endings are luminous, and even fungi participate in the forest's endless celebration of life and renewal. Some jungle fish can survive entirely out of water for hours. In the fluctuating rivers of the jungle, some fish have evolved to survive on land for surprising lengths of time. Species like the walking catfish and certain eels can breathe air directly, wriggling across mud or through vegetation in search of new water. During the dry season, when pools shrink and oxygen dwindles, this ability becomes essential. Some even burrow into damp soil, waiting until rains return. Watching a fish move across land challenges our very definition of what a fish is. These creatures blur the line between water and earth, hinting at the ancient evolutionary transitions that gave rise to amphibians. In the jungle, they are simply survivors, using ingenuity to endure the shifting rhythms of flood and drought. They remind us that life here is endlessly adaptable, finding ways to persist in places where we least expect it. Jungle animals create complex highways through the underbrush. In the dense jungle, movement is difficult. Vines tangle, roots rise, and shrubs block the way. Yet animals have solved this challenge by carving invisible highways. Generations of tapirs, peccaries, jaguars, and monkeys follow the same paths, trampling trails into the underbrush. These corridors become so established that other creatures adopt them, forming a shared network of passageways. For researchers, stumbling upon one of these trails is like finding a hidden road system, complete with crossroads and shortcuts. The highways allow predators to stalk more efficiently and prey to flee with speed. They also connect water sources, feeding grounds, and nesting areas, binding the jungle into a living map. Though unseen from above, these pathways are vital arteries of the forest, shaped not by humans, but by the daily rhythms of countless animals, each step carving new order into the green chaos. The Amazon contains more than 400 indigenous tribes. Beyond plants and animals, the Amazon is also home to extraordinary human diversity. More than 400 distinct indigenous tribes live within its borders, many with their own languages, traditions, and ways of life. Some have regular contact with the outside world, while others remain uncontacted, choosing to live in complete isolation. Each group carries knowledge honed over millennia, medicines derived from plants, techniques for hunting and farming, and spiritual traditions deeply tied to the forest. Their presence reveals that the jungle is not a wilderness devoid of people, but a landscape shaped by human stewardship as well as natural forces. Protecting the forest often means protecting these communities, whose survival is bound to its health. To acknowledge them is to remember that the Amazon is not just a sanctuary of biodiversity, but also of human culture, resilience, and memory stretching back countless generations. Some jungle trees produce natural rubber. The heavier Braziliensis tree, native to the Amazon, is the source of natural rubber, a substance that has changed human history. When its bark is tapped, a milky latex flows, which can be processed into the elastic material we know today. For centuries, indigenous peoples used rubber to waterproof clothing, make balls for games, and create durable tools. In the 19th century, rubber extraction fueled global industries, from tires to electrical insulation. This boom reshaped economies and societies, sometimes with devastating impacts on local communities. Yet in the jungle, the rubber tree remains simply part of the fabric of life, one of many plants with remarkable properties. Its gift is both practical and symbolic: resilience, flexibility, and strength. To see a tree bleed white sap is to realize how many of humanity's inventions trace back to the hidden laboratories of the forest. Certain frogs lay eggs that hatch directly into froglets. In the jungle, survival often means skipping dangerous stages of life. Some frog species avoid the vulnerable tadpole stage altogether. They lay eggs that develop fully inside their protective capsules, hatching directly into tiny, fully formed froglets. This strategy spares the young from aquatic predators such as fish or insects, giving them a head start on land. For the parent, it requires investing more energy into each egg, but the payoff is higher survival rates. Watching a clutch of eggs hatch into miniature frogs is like seeing evolution fast-forwarded, the usual cycle compressed into a single leap. These species reveal the creativity of life in adapting to danger, finding new ways to continue in a forest filled with hazards. Each froglet hopping free from its egg is a triumph of adaptation, proof that even reproduction can bend to the challenges of the jungle. Some jungle insects can jump distances many times their body length. Among the undergrowth, tiny insects perform athletic feats that seem impossible. Flea beetles, froghoppers, and certain grasshoppers can leap more than 100 times their own body length. For a human, that would be like jumping the length of a football field in a single bound. These insects store energy in specialized leg structures, like biological springs, releasing it in explosive bursts. Their leaps serve as both escape and attack, allowing them to vanish from predators or launch onto food plants with precision. In the dense jungle floor, where predators lurk at every turn, the ability to disappear in an instant can mean survival. Observing such leaps reminds us that size is not a barrier to power. Even the smallest beings can command astonishing abilities, moving through the forest not with stealth or strength, but with sudden, gravity-defying speed. The canopy's leaves create a soundscape of constant dripping water. In the jungle, even silence is filled with sound. After a rainstorm, the canopy holds thousands of gallons of water suspended on its leaves. Drop by drop, the water falls, creating a ceaseless chorus of drips, splashes, and trickles. The sound continues long after the rain has ended, a background rhythm that defines the forest's mood. For animals, this dripping sound becomes part of their daily lives, masking movements and offering cover for calls. For humans, it is hypnotic, a reminder of the forest's constant cycle of water and renewal. The canopy is not just a barrier above, it is a living instrument, turning rainfall into music. To sit beneath it is to listen to a concert of water and leaf, endless and gentle, a soundtrack to the persistence of life in one of the planet's wettest and most abundant environments. Some plants can store toxins to defend against herbivores. The jungle is a place of constant battles between plants and the creatures that eat them. To survive, many plants produce toxins in their leaves, stems, or fruits. These chemicals can deter herbivores, making them bitter, nauseating, or even deadly to consume. Some species go further, storing toxins at high concentrations as a defense against persistent predators. Yet animals adapt too. Certain insects and birds evolve immunity, allowing them to feed on toxic plants while others cannot. In some cases, animals even turn the toxins to their advantage, using them as defense against their own predators. This arms race between plants and consumers drives much of the jungle's diversity. Every bite carries risk, every leaf a potential trap. To walk through the forest is to stroll through a vast battlefield where survival is written not only in claws and teeth, but in chemistry. The Amazon River basin is larger than the whole of Europe. The Amazon River basin is almost unimaginably vast, covering more than 2.5 million square miles. That makes it larger than the entire continent of Europe. Within this expanse lies the world's largest river by volume, the longest stretches of unbroken forest, and countless ecosystems woven together into one giant system. The scale is so immense that the basin influences global weather patterns, generating rainfall far beyond South America. From above, it appears as an endless carpet of green, broken only by winding rivers that gleam like silver threads. To grasp its size is to recognize the Amazon not as a single forest, but as a continent-spanning entity, a living, breathing part of Earth itself. Its reach in water, carbon, and climate extends to every corner of the globe, binding distant lands to the rhythms of its rivers and trees. Some jungle creatures remain completely unknown to science. Despite centuries of exploration, the jungle still hides secrets. Scientists estimate that millions of species, insects, fungi, plants, and even larger animals remain undiscovered. Some may live in canopy layers rarely studied, others in soils or river depths too difficult to reach. Occasionally, new discoveries astound the world. A frog that sings in unique tones, a monkey with striking features, or a tiny insect with previously unseen behaviors. Yet countless more remain unnamed, living entire lives unseen by human eyes. The jungle is not just a place of known wonders, it is a realm of mystery, where each expedition might uncover life never before recorded. This hidden abundance reminds us of our limits, that even in the age of satellites and global maps, vast swaths of life remain beyond our knowledge, thriving in silence and secrecy beneath the leaves. Jungles are so vast that entire species may live and die without ever being seen. The jungle is not only abundant, it is overwhelming. Its vastness is such that entire species may evolve, thrive, and vanish without ever being observed by humans. Remote valleys, inaccessible canopies, and flooded forests provide homes for creatures that no one has ever recorded. Their songs, colors, and behaviors exist in full, rich detail, but only for themselves and the ecosystems around them. For us, they remain invisible, ghosts of possibility. This reality humbles scientists who know that what we catalogue is only a fraction of the whole. It also makes the loss of jungle habitats even more tragic. When a patch of forest disappears, it may take with it species we never knew existed, stories untold, voices unheard. The jungle reminds us that the world is far larger and stranger than our understanding, filled with lives that unfold unseen. The world's largest living organism is a forest fungus. Hidden beneath the soil of Oregon's Blue Mountains lies something almost impossible to imagine. It looks like an ordinary forest floor at first glance, scattered with trees and fallen leaves. But beneath it all stretches the threads of a single fungus, weaving through the earth like a living web. This organism, Armillaria ostoyae, covers an area of nearly 4 square miles and is believed to be thousands of years old. Though its mushrooms sprout briefly above ground, the real body of the fungus is an underground lattice of microscopic filaments called mycelium. Scientists consider it the largest living organism on Earth, far bigger than any whale, tree, or coral reef. What makes it astonishing is not only its size, but its quiet persistence. Year after year, it slowly spreads beneath the forest, connecting trees, feeding on shell, roots, and reminding us that life is often hidden, yet immense. The Amazon alone holds 10% of all known species. The Amazon rainforest is often called the crown jewel of Earth's ecosystems, and for good reason. Within its immense green expanse, stretching across 9 countries, lives an extraordinary fraction of all life known to science. 1 in every 10 species on Earth makes its home in the Amazon. That means millions of plants, animals, insects, and fungi share the space beneath its towering canopy. Jaguars stalk the forest floor, while pink river dolphins swim through winding channels. Entire tribes of ants cultivate underground gardens of fungus, while orchids cling to branches high above. Scientists estimate that there are still thousands, perhaps millions, of undiscovered species hidden in its depths. The Amazon is not just diverse, it is dense with life, layered from its dark soil to its sunlit canopy. To walk in it is to step into a living encyclopedia of the planet, unfolding leaf by leaf, call by call. The boreal forest stores twice as much carbon as all the world's oil reserves. The boreal forest, stretching like a green crown across Canada, Russia, and Scandinavia, may not be as famous as the Amazon, but it holds a power that shapes the whole planet. Beneath its vast carpet of spruce, pine, and larch lies an immense storehouse of carbon. Much of it is locked in its soils and wetlands, preserved in cold, slow-decaying layers of moss and peat. Scientists estimate that the boreal forest contains nearly twice as much carbon as all the known oil reserves of the world combined. This means the boreal acts as a giant brake on climate change, quietly absorbing and storing carbon for centuries. But warming temperatures are beginning to thaw permafrost, risking the release of this buried carbon back into the atmosphere. In a sense, the boreal forest is like a vault, and the future of Earth's climate depends on keeping that vault sealed tight. The Amazon rainforest produces its own rain. When people think of rainforests, they picture storms rolling in from faraway oceans. But the Amazon is different. It doesn't just receive rain, it makes its own. Each day, countless trees lift water from the soil and release it into the air through tiny pores in their leaves. This invisible mist rises skyward, forming thick clouds that drift and break into rain. Scientists call this process evapotranspiration, and in the Amazon, it creates an atmospheric river that cycles water again and again over the forest. In fact, a single large tree can release hundreds of gallons of water in a day. Without this cycle, the forest would wither, but with it, the Amazon sustains its own weather, creating thunderstorms, feeding rivers, and even sending moisture as being. Far away as the U.S. Midwest. It is a self-sustaining engine of life, a forest that drinks and rains in the same breath. Trees communicate through underground networks of fungi. Beneath the forest floor lies a hidden world of threads so fine that millions can exist in a single handful of soil. These fungal strands explore the ground in every direction until they find the roots of trees and gently fuse with them. Once connected, they become part of the shared system that moves signals and materials with remarkable flexibility. When conditions shift toward drought, the flow of water can travel from one region of the network to another, guided by subtle changes in chemistry. When a section of the forest is suddenly shaded or disturbed, the roots there can receive nutrients from distant trees that are still thriving in stable light. This underground lattice works slowly, yet it maintains a steady balance that keeps the forest functioning as a cooperative whole. The individual trees do not act alone. They operate as nodes in a living circuit that spreads across the soil like an invisible blueprint of the entire woodland community. Some trees can warn each other about danger using airborne signals. When the surface of a leaf is disturbed, its chemistry changes in an instant. Molecules begin to form within the damaged tissue and drift outward into the air where they mix with the surrounding atmosphere. These drifting vapors are so faint that humans rarely notice them in the wild, yet nearby trees detect them through tiny openings in their leaves. Once the signal is received, internal pathways activate and begin adjusting the plant's internal balance. Defensive compounds rise in concentration. Leaf toughness increases. Growth slows so the tree can place more energy into protection. All of this begins before any visible threat reaches the trunk or canopy. The surrounding trees respond as though they have been given early warning. They begin preparing themselves for the same challenge, even if the source of danger is still far away. Forest air may feel calm, but it carries constant information shaped by the lived experiences of the plants that inhabit it. Certain trees release chemicals that call predators to defend them. When insects such as caterpillars or beetle larvae attack a tree, the damage triggers a series of internal reactions that change the composition of the air around the pell. Leaves. These new airborne molecules travel outward and function as a targeted request for assistance. The signal is not directed toward other plants. It is directed toward animals that prey on the very insects causing the harm. Small hunting insects are highly sensitive to these chemical cues and can follow them from surprising distances. Once they arrive, they eliminate or disrupt the pests that initiated the damage. This process turns the broader ecosystem into a defensive force that supports the tree without any physical struggle on its part. The tree's survival becomes tied to a complex food web that responds naturally to the scent of conflict in the leaves. Over time, these interactions strengthen entire forests, creating living landscapes built on quiet exchanges between plant and predator. There are trees that keep time using internal biological clocks. Inside the cells of a tree are repeating patterns that rise and fall with remarkable consistency. These patterns act like an internal schedule that controls when the tree opens its pores to release water, when it closes them to conserve moisture, and when it prepares for major seasonal changes. Even if the tree is placed in environments with constant light or constant darkness, these internal rhythms continue for many days without fail. They coordinate cellular activity, helping every part of the organism remain synchronized. The timing of budding, leaf production, flowering, and the eventual shedding of leaves is shaped by this inner sense of time. Trees use sunlight and temperature only as additional cues, not as the core mechanism. The real structure of their daily and yearly routine originates from within. This built-in timing system allows trees to anticipate the world around them instead of simply reacting to it. The oldest known trees began growing before the pyramids were built. In the mountains of California and Nevada, high above the desert floor, grew trees so ancient that their lifespans stretch back into prehistory. These bristlecone pines, twisted and weathered by centuries of wind and snow, are the oldest living individual organisms on Earth. Some are nearly 5,000 years old. That means they were already old when the first pyramids were rising in Egypt. They have stood through the rise and fall of civilizations, surviving droughts, fires, and freezing winters. Their secret is not speed, but slowness. They grow so gradually that even after thousands of years, many stand no taller than a suburban house. Their wood is dense, resin-rich, and resistant to decay. When you look at a bristlecone, you are looking at a living being that has endured across nearly all of recorded human history, a reminder that time moves differently. For trees, in the taiga, trees can explode in extreme cold. The taiga, Earth's largest forest, sweeps across Siberia, Canada, and Scandinavia. Winters there plunge to brutal lows, sometimes below -60 degrees Fahrenheit. In such extremes, even trees can suffer in ways hard to imagine. Their sap, filled with water, can freeze so rapidly that it expands faster than the tree can withstand. The result is a sudden rupture, a sound like a crack of gunfire as the trunk splits open. In rare cases, parts of the tree may even burst outward, earning the description that trees explode in the cold. While most trees have adaptations to endure freezing, such as antifreeze-like chemicals in their tissues, these safeguards are not always enough. The exploding trees of the taiga are reminders of just how harsh this biome is. where survival pushes every living thing to its limits in the battle against cold. The Congo rainforest holds more carbon than the entire United States emits in a decade. Second in size only to the Amazon, the Congo rainforest is often overlooked, but its role in stabilizing the planet is immense. Beneath its green canopy lies one of the greatest carbon vaults on Earth. The forest itself, along with its vast peatlands, stores more than 80 billion tons of carbon. To put that in perspective, it is more than the entire United States emits in a decade of burning fossil fuels. Much of this carbon is buried in soggy peat soils, where oxygen cannot break it down quickly. But rising temperatures and human disturbance threaten to unlock this storehouse. Scientists warn that if these peatlands dry, the release of carbon would be catastrophic. For now, though, the Congo stands as one of Earth's most powerful protectors, a green fortress quietly holding back the tide of climate change. The tallest trees on Earth reach higher than a football field is long. If you stand at the base of a coastal redwood in California and crane your neck upward, the tree just keeps going. These giants, some over 370 feet tall, are the tallest living organisms on Earth. To picture their size, imagine a football field standing on end. The tree rises even higher. Their crowns sway in winds no human can feel from the ground, and entire ecosystems live in their upper branches, including ferns, mosses, and even small salamanders. The redwoods grow in fog-shrouded groves along the Pacific coast, where they drink moisture from the air itself. Despite their size, they are fragile, surviving in only a narrow band of climate. Yet they remind us of nature's ability to reach for the sky, stretching toward the clouds in a feat of endurance and quiet ambition, unmatched anywhere else on Earth. Some trees can change their leaf chemistry to repel specific insects. When an insect begins feeding, the leaf does not simply endure the damage. Sensors within the tissue detect the saliva of the attacker and begin producing substances designed to discourage that particular species. The change can involve creating bitter flavors, altering the texture of the leaf surface, or building compounds that interfere with the insect's ability to digest plant material. The response is precise enough that two different insects feeding on the same tree may trigger completely different defensive strategies. This targeted approach allows the plant to conserve energy because it produces only the compounds that matter for the threat it currently faces. The transformation continues until the danger passes, after which the leaf often shifts back toward normal growth. The adaptability of this process reveals a level of responsiveness that is far more dynamic than the calm appearance of a leaf might suggest. A few trees can clone themselves into vast connected forests. Some species possess the ability to produce new trunks from their roots, resulting in large clusters of genetically identical stems that all belong to a single organism. While each trunk looks like an individual tree from the outside, all are fed and supported by a continuous underground system that can stretch across a wide 18 landscape. As older trunks age and fall, new growth emerges from the same enduring foundation. This pattern continues for centuries and can create a forest that behaves more like a single organism, expressing itself in many separate bodies. When fire, drought, or cold damages part of the colony, other trunks continue to supply resources to the remaining root system, allowing regeneration to begin almost immediately. The resilience of these connected forests comes from their unity. What appears to be a group of individuals is truly one life form, exploring space through many distinct vertical stems. Some ancient trees are older than entire civilizations. In isolated valleys and high mountain regions, there are trees that began growing long before the earliest known written stories. Their roots have held the same soil for hundreds upon hundreds of years, while climates shifted, coastlines moved, and cultures rose and faded. When researchers study the growth rings in their wood, they uncover detailed evidence of ancient droughts, periods of unusual warmth, and sudden environmental panic. events that would otherwise be lost to time. These trees have endured storms that reshaped entire landscapes and survived conditions that would end the lives of younger species. Their longevity is not a simple matter of slow growth. It is the result of highly efficient internal systems that repair damage, resist disease, and maintain delicate balance even during long stretches of hardship. Standing near one of these ancient beings is a reminder that the planet carries memories far older than our species. There are trees that never truly die, but instead continually rebuild themselves. Some species retain living tissues deep within their bases, even after their central trunks hollow out or collapse. As long as these hidden tissues remain intact, the organism continues to generate new growth from the same root system. Fresh shoots rise where old wood has fallen away, creating younger trunks that carry the identity of the original tree into the next century. Over time, the outer appearance of the plant may change completely. The individual trunks may fall, rot, or scatter, yet the living core remains active and continues to create new growth from its protected interior. These trees survive not by maintaining a single structure, but by repeatedly rebuilding themselves in a steady cycle of decay and renewal. What appears to be a small cluster of young trunks is often the latest chapter of a life that began long before the surrounding forest reached its present form. Redwoods can live for more than 2,000 years. The redwoods are not only the tallest trees on Earth, but also among the longest lived. Some individuals have stood for more than 2,000 years, silently watching centuries of human history unfold. Their bark, thick and fibrous, can resist both insects and fire, allowing them to endure where other trees would fall. When fires do come, the flames often clear away competition while leaving the redwoods intact. Their roots, surprisingly shallow, interlace with those of neighboring trees, binding the forest together into a shared network of support. In this way, a grove of redwoods becomes more than a collection of individuals. It is a single, ancient community. Walking among them feels like stepping into a living cathedral, where pillars rise into mist and time stretches beyond comprehension. They stand as reminders that endurance itself can be a kind of strength, etched in rings and centuries. Cloud forests drink directly from the sky. High in the mountains, where mist rolls thick over the treetops, live forests unlike any others. Cloud forests are shrouded in near-constant fog, and the trees there have adapted to capture water straight from the air. Their leaves and mossy branches comb moisture from drifting clouds, turning mist into droplets that drip steadily down to the forest floor. In this way, they drink from the sky, even when no rain falls. This unique ability allows cloud forests to thrive in regions where rainfall alone would not be enough to sustain them. The water they capture often feeds rivers and streams that flow into valleys below, supporting both ecosystems and human communities. To walk through a cloud forest is to be inside a living cloud, where every surface glistens and drips, and where the air itself is part of the forest's hidden heartbeat. Some forests glow at night with bioluminescent life. Step into certain forests after dark, and you may notice an otherworldly glow. Tiny mushrooms, scattered like lanterns on rotting logs, emit a soft green light. This phenomenon, called bioluminescence, is created by chemical reactions inside the fungi. The glow is thought to attract insects that spread their spores, helping the fungi reproduce. In tropical forests, entire patches of the undergrowth may shimmer faintly, turning the forest floor into a starlit scene. Even fireflies add to the effect, flashing among the branches like sparks. For centuries, people have described these glowing forests as enchanted. Today, scientists study the exact chemistry behind the light, hoping to understand why some species evolved this trait, while most did not. To the human eye, it feels like magic, a hidden electricity that flickers alive in the dark. reminding us that even when the sun sets, forests have ways of shining on their own. Some forests burn regularly as part of their natural cycle. Though it may seem destructive, fire is a natural and necessary part of many forests. In places like North America's pine forests or Australia's eucalyptus groves, fires sweep through every few years. These flames clear away underbrush, recycle nutrients into the soil, and even trigger certain trees to release seeds. Without fire, these ecosystems would actually suffer. Pines, for example, have cones sealed with resin that only open in the intense heat of flames. After a fire, the ash-rich soil creates the perfect conditions for new growth. Animals too have adapted. Some birds follow the smoke to hunt insects fleeing the fire. Of course, when humans disrupt this cycle with logging or suppression, fires can grow unnaturally large and dangerous. But in their natural rhythm, forest fires are less an ending than a reset, a way for the ecosystem to breathe, renew, and begin again. Some tree species can regrow entirely after being cut to the ground. In species with strong regenerative abilities, roots store large amounts of energy during normal growth. They also preserve tiny dormant buds that remain inactive until the upper portion of the plant is removed. When the trunk is cut, these buds awaken and begin to grow rapidly, supported by the rich supply of sugars and nutrients in the buried root system. New stems appear in clusters and grow faster than typical young trees because they can draw on the resources accumulated during the previous life of the trunk. Over time, the strongest of these stems develops into a new main trunk, restoring the tree's structural form even though the original above-ground body was lost. This regenerative cycle allows these species to endure repeated disturbances and remain a stable presence in their ecosystems. A few resilient trees can survive complete fire damage by sprouting from hidden buds. In fire-prone regions, some trees develop thick protective layers around their most important tissues. Beneath the outer bark lie small living structures that stay insulated even when the surrounding trunk becomes charred. When a fire passes through, the visible canopy may vanish entirely, and the tree may appear lifeless. Yet the protected buds remain safe inside their natural shield. Once rain returns and temperatures drop, these buds begin to extend new shoots. Green growth spreads across blackened stems or rises directly from the base. The tree does not rely on seeds to recover. It rebuilds itself using parts that were prepared long in advance. This strategy allows entire landscapes to return to life after severe fire seasons and ensures that the species can persist even under challenging sky. Environmental cycles. Some trees create their own microclimates that shape entire ecosystems. A large canopy does more than cast shade. It changes the entire behavior of the air beneath it. The leaves slow the movement of wind and reduce the intensity of sunlight long before it reaches the soil. As a result, moisture lingers for longer periods of time, and temperatures shift less dramatically between day and night. This stable environment supports insects that cannot tolerate direct sunlight, birds that prefer cooler air, and plants that would not survive in open ground. Over time, a single tree can influence the humidity and temperature of an entire patch of forest. The branches intercept rainfall, breaking it into softer droplets that fall gently to the soil. That changing water flow alters how nutrients move and how roots anchor themselves. Even the soundscape becomes different because the canopy softens the impact of rain and wind. When scientists study these zones, they find that the presence of a large tree does not simply host life. It engineers the conditions that make that life possible. There are trees that make rain by releasing moisture into the air. In warm regions where sunlight is intense, trees have developed a remarkable strategy for cooling themselves. They pull large amounts of water from the soil and send it upward through their trunks until it reaches the leaves. Once there, the water evaporates into the atmosphere, as a fine mist that rises through the canopy. As countless leaves release moisture at the same time, the surrounding air becomes more humid and begins to rise into the sky. When this moisture collects in the upper atmosphere, clouds form more easily. Over large areas, this process can influence patterns of rainfall, turning forests into engines that help maintain stable weather. Researchers have found that entire regions would become far drier without this steady upward movement of water. These trees are not simply responding to climate. They are helping to create it. The cycle of evaporation, cloud formation, and rainfall becomes part of the forest's internal rhythm. Fires can trigger seeds to sprout in forests. In the aftermath of fire, blackened soil may look lifeless. Yet hidden beneath the ash lies a secret. Seeds that have waited, sometimes for years, for the spark of fire to unlock them. Certain plants, like the lodgepole pine or Australia's banksia, have tough seed coatings that only break open under intense heat. Others respond to smoke chemicals in the air, which act like a signal that conditions are finally right to grow. The result is that just weeks after a blaze, a forest floor can burst into green, carpeted with seedlings that could not have sprouted otherwise. Fire, then, is not only a force of destruction, but also a catalyst for renewal. It clears space, lets sunlight reach the ground, and awakens a new generation of growth. The forest's cycle of life and death turns out to be written, quite literally, in flame. Certain trees can survive being struck by lightning. When lightning rips through a forest, the crack and flare can be terrifying. Trees often bear the brunt of these strikes, and many split or burn. Yet some survive. Their survival depends on their bark, moisture, and structure. A tree with thick, insulating bark can channel electricity down its outer layers, sparing the living tissue inside. Moisture within the trunk can also act as a conductor, letting the current pass through quickly without destroying the core. Remarkably, some trees even heal around their scars, the charred grooves left by lightning becoming permanent streaks in the bark. Over years, these scars can spiral upward like black ribbons, silent records of the storm. For the forest, trees that endure such strikes are testaments to resilience, standing tall even after nature's most powerful bolts have tried to bring them down. Some forest fires burn underground for years. Not all fires vanish when the flames die down. In certain forests, particularly in rich soils, fires can smolder underground long after the surface looks calm. These zombie fires can persist for months or even years, creeping slowly through layers of carbon-rich peat. They may reignite above ground long after a wildfire season is thought to be over. Some scientists believe such fires even survive the winter, buried under snow, only to re-emerge in spring. These hidden blazes release enormous amounts of carbon into the air and are notoriously difficult to extinguish, since water rarely penetrates deeply enough to power. Douse them. The smell of smoke can hang in the air for miles, puzzling residents who see no visible flames. They are fires that never quite die, smoldering reminders of how forests can hold on to both life and destruction far longer than we realize. Forests can generate their own lightning. Forests do not just endure lightning, they can help create it. As water vapor rises from leaves into the air, it feeds storm clouds above. Within those clouds, particles of ice and water collide, building electrical charges. Dense, humid forests like the Amazon are particularly good at fueling such storms, releasing vast amounts of moisture into the atmosphere each day. The result is frequent lightning strikes, often thousands per night across the basin. Some studies suggest that aerosols released by trees may even influence how these storm clouds form and behave. In this way, forests are not just passive victims of lightning, but active players in creating the conditions that spark it. Each flash across the sky, each thunderclap, can in part be traced back to the slow, steady work of countless leaves breathing moisture upward, stitching forests into the drama of the atmosphere above them. Tree roots can engineer soil to become more fertile over centuries. Roots do more than search for water. They reshape the very structure of the ground they inhabit. As they grow, they create pathways that allow air and moisture to travel deeper into the soil. When roots die, they decompose and leave behind channels rich with nutrients. Over many cycles of growth and decay, these changes accumulate, transforming compact mineral soil into a loose and fertile layer that supports a wide range of organisms. Certain trees release compounds that bind with minerals underground, forming stable crystals that hold nutrients in place. Others bring elements such as calcium or nitrogen up from deeper layers and deposit them closer to the surface. Microbes gather around these roots, feeding on sugars and producing helpful substances that improve soil structure. Worms and insects follow, attracted to the soft microhabitats created by the constant movement of roots. After centuries of this slow engineering, the ground becomes a complex living system that can support entire communities of plants and animals. Some trees can store enormous amounts of water inside their trunks. In regions where rain arrives in brief bursts followed by long dry seasons, certain species survive by turning their trunks into living reservoirs. Their tissues swell during the wet season as they pull water upward and store it within specialized cells. This stored water remains sealed inside the wood until the environment begins to dry. As moisture disappears from the soil, the tree draws from its internal reserve to keep its leaves functioning and its growth steady. The structure of these trunks is surprisingly complex. Layers of dense tissue surround pockets of softer material that expand and contract with changing water levels. This system allows the tree to maintain stable internal pressure even when the outside world becomes extremely dry. Animals and insects depend on these trees because the stored water supports leaves, flowers, and fruits long after other vegetation has faded. In some landscapes, these water-storing trunks act as the final anchors of life during severe drought. A few desert trees can pull moisture from air that feels completely dry. Desert air often contains far less moisture than a human can detect, yet some trees have evolved surfaces capable of capturing tiny traces of humidity. Their leaves are covered in fine structures that encourage condensation, even when the atmosphere seems barren. Before dawn, when the temperature drops, these structures begin collecting microscopic droplets that gather into films of water. The tree absorbs this moisture through specialized pores, funneling it toward the tissues that need it most. This process repeats every night, allowing the tree to survive in areas where rainfall is rare and groundwater lies far out of reach. Researchers studying these species have discovered that their ability to harvest water from the air supports entire ecosystems of insects and birds that rely on the limited moisture the tree makes available. Each night becomes a slow cycle of collection and renewal, helping the tree endure conditions that few other large plants could survive. Certain coastal trees can survive on salty water. Along shorelines where ocean tides rise and fall throughout the day, some trees must deal with water that is far too salty for most plants. They meet this challenge by filtering out salt at the root level using complex membranes that only allow fresh water to pass through. Other species pull in salty water, but store the salt inside older leaves that eventually fall away, removing the excess from the plant. Some even excrete crystals onto the surface of their leaves where wind and rain carry the salt away. These strategies allow the trees to live in areas flooded with seawater from storms or daily tides. Their presence stabilizes coastlines, prevents erosion, and provides shelter for birds and marine creatures that depend on roots and branches extending over Tquath. The water. Without these remarkable salt handling systems, many coastal ecosystems would lose their most important anchor species. Some forests stay green even during the ice ages. During the Great Ice Ages, when glaciers covered much of the northern hemisphere, it might seem that forests would have disappeared entirely. Yet certain pockets endured. In regions shielded from the worst cold, isolated groves of evergreen trees managed to survive, even as ice pressed down from the poles. These refugia became sanctuaries of green in an otherwise frozen landscape. When the glaciers retreated, the surviving forests spread outward again, receding vast regions of Earth. Today, genetic studies of trees reveal clues to these ancient refuges, showing lineages that trace back tens of thousands of years. The persistence of these forests is why we still have so many species today. Without them, much of Earth's tree life might have vanished forever. They are proof that even in the harshest eras, life finds cracks to hold on, keeping a spark of green alive through the ice. There are fossilized forests beneath the Antarctic ice. Antarctica, now a realm of ice and snow, was once cloaked in forests. Over 200 million years ago, before the continent drifted into its frozen isolation, it lay closer to the equator, covered in towering trees. Fossil evidence reveals stumps, roots, and even whole petrified trunks preserved beneath layers of rock and ice. Some fossils suggest dense polar forests that endured months of continuous darkness each winter and constant daylight each summer. Today, scientists drill into Antarctic rocks and uncover remnants of this lost world, impressions of leaves, fossilized wood, and traces of ancient soils. These discoveries show how dramatically Earth's climate and continents have shifted over time. To imagine forests where glaciers now stand is to glimpse a planet always in motion, reshaping itself across millions of years, where even the coldest, emptiest places once teemed with green life. The Amazon once flowed backwards, changing its forest forever. Today, the Amazon River flows eastward into the Atlantic, carrying more water than any other river on Earth. But millions of years ago, it flowed in the opposite direction, westward, into what is now the Pacific. Geological forces reshaped South America as the Andes Mountains rose and blocked the river's path. Over time, the Amazon's flow reversed, creating new floodplains, shifting ecosystems, and altering the forest forever. The reversal transformed how sediments and nutrients moved, feeding the soil that would nurture one of the richest ecosystems on Earth. It also created habitats where countless species evolved. Without that monumental shift, the Amazon rainforest as we know it would not exist. It's a reminder that even the mightiest rivers, carving through continents, are not fixed. They bend to the planet's deeper rhythms, and their change can give rise to entire worlds of life. Some forests are so wet, rain never reaches the ground. In certain rainforests, the canopy above is so thick that rainfall rarely touches the soil. Instead, the upper layers of leaves and branches capture nearly all of it, holding the water in a suspended world high above the ground. Epiphytes, plants that grow on trees rather than in soil, thrive here, drawing their moisture straight from intercepted rain and mist. For smaller animals, this canopy becomes a home in itself, complete with streams, pools, and microhabitats that never see the forest floor. Scientists who climb into these upper levels often describe it as stepping into another ecosystem entirely, one that hovers above the main forest like a hidden gem. Consummate. Down below, the soil may stay dry for days, even while storms rage above. These forests prove that rain doesn't always fall. Sometimes, it's caught and cradled long before it ever touches the ground. Some trees breathe in patterns that change with the seasons. The tiny openings on the surface of leaves, known as pores, open and close in patterns controlled by light, temperature, and internal pressure. During warm months, these pores open wide to release water vapor into the air and draw carbon dioxide inward for photosynthesis. When cold weather arrives, the pores behave very differently. Many trees restrict their opening times to conserve water, and some close them entirely to protect their tissues from freezing. As the seasons progress, the rhythm of these openings shifts in ways that mirror the changing environment. Scientists can track these patterns in long-term studies and find that each species has a signature breathing rhythm shaped by its evolutionary history. These seasonal movements help trees regulate temperature, conserve energy, and adjust to shifts in day length. The process is subtle, yet it influences everything from growth rate to the timing of leaf drop. A few trees can alter the acidity of the soil around them. Through their roots, some species release substances that change the chemical balance of the surrounding soil. These compounds can increase or decrease acidity depending on the needs of the tree. Altering acidity reshapes which minerals dissolve easily and which remain trapped in solid form. This affects how nutrients become available and influences which other plants can grow nearby. In some forests, a single species changes the acidity enough to create distinct zones where only certain organisms thrive. Microbes respond as well, shifting their activity along with the chemical conditions. Over long periods, these small changes accumulate and transform the soil into a unique habitat supported by the tree's constant influence. The result is a microenvironment shaped by one organism's ability to alter the chemistry of the ground itself. Some tree roots travel farther than the height of the tree itself. Although trunks rise visibly above the ground, much of a tree's presence exists far below the surface. In certain species, roots extend outward several times the distance of the canopy, spreading across the soil in search of moisture and minerals. These long-reaching roots explore cracks in rock, follow ancient underground channels, and anchor themselves in deep layers that hold stable water even during drought. This wide network gives the tree access to resources that smaller root systems could never reach. It also allows the tree to remain steady during storms. The expanded foundation distributes physical stress and prevents toppling even in powerful winds. For researchers, studying these deep and far-reaching structures reveals that the visible portion of a tree represents only a small part of its true footprint. The hidden extent of the roots defines much of its resilience and long-term survival. There are trees with roots that form living bridges over rivers. In certain regions with frequent flooding, communities have learned to guide the growth of particular tree roots across streams and riverbanks. These roots are flexible when young and can be directed over wooden frames or natural supports. As they grow thicker, they fuse together into strong, interwoven structures capable of carrying the weight of people and supplies. These living bridges continue to strengthen over time because the roots remain active and expand with every growing season. They resist rot, withstand heavy rainfall, and adapt to changing river dynamics in ways that man-made structures often cannot. The trees supporting these bridges do not lose stability because their remaining roots continue to anchor them firmly in the soil. The result is a structure that grows more durable with age, representing a rare collaboration between human guidance and natural growth. Rainforests can create thunderstorms. Thunder rolling over a rainforest may not always come from distant weather systems. In places like the Amazon, the forest itself fuels the storms. Through evapotranspiration, trees release massive amounts of water vapor into the sky. This rising moisture forms thick clouds that grow heavy and unstable. By afternoon, the buildup often triggers thunderstorms, complete with lightning and booming skies. These storms are part of a cycle. The rain they bring feeds the trees, which then release more vapor, keeping the pattern alive. The scale is staggering. The Amazon alone pumps billions of tons of water into the atmosphere each year, enough to sustain its own weather system. In this way, the rainforest acts not just as a receiver of climate, but as a maker of it, conjuring its own storms from the air and reminding us that forests can command the skies. Forests can create their own winds. Wind is usually thought of as a global force shaped by ocean currents and atmospheric circulation. But forests, especially vast ones, can create their own. As the sun warms the canopy, hot air rises above it, pulling cooler air from surrounding areas inward. This creates small but steady breezes that circulate within and around the forest. In massive rainforests like the Amazon, these winds can even scale up, influencing regional weather patterns. Leaves also play a part. Their rough surfaces slow down passing air, creating turbulence that mixes and stirs. The result is a forest that doesn't just sit beneath the weather, but actively sculpts it, shaping the movement of air itself. Stand in a forest clearing, and you might feel it, a gentle breath, born not from the sea or sky, but from the living machinery of leaves and trunks around you. Tropical forests breathe out vast rivers of water vapor. Forests breathe not just oxygen and carbon dioxide, but water. Each day, a single large tropical tree can release hundreds of gallons of water vapor into the air. Multiply this by billions of trees, and you have atmospheric rivers flowing invisibly above the canopy. In the Amazon, these vapor streams are so immense they can stretch for thousands of miles, carrying moisture far beyond the forest itself. They help drive rainfall across South America and even influence weather in distant regions. This process is vital for agriculture and climate stability far outside the forest. Scientists sometimes describe the Amazon as a giant humidifier, pumping life-giving water into the sky. The trees, rooted in the ground, reach into the air as well, blurring the line between earth and atmosphere. Their breath, though unseen, is one of the planet's most powerful forces. Certain forests release aerosols that seed distant clouds. When forests release water vapor, they also emit tiny particles called aerosols. These come from plant chemicals, soil organisms, and even microorganisms drifting on the breeze. In the sky, aerosols act as seeds around which water droplets can gather, forming clouds. Some of these clouds may eventually drift thousands of miles away before dropping their rain. In this sense, a forest's breath can help water lands on other continents. For example, aerosols from the Amazon have been traced to influencing rainfall across the Atlantic Ocean. Scientists are still studying the exact chemistry, but the principle is clear. Forests extend their reach far beyond their borders. They don't just create rain for themselves, they play a hand in the water cycle of the world, cloud by cloud, drop by drop, linking distant places through invisible threads of air. The smell of pine trees comes from chemicals that affect climate. That sharp, refreshing scent of pine on a cool day isn't just pleasant, it's chemistry at work. Pine trees release organic compounds called terpenes, which give the forest its distinct fragrance. But these molecules do more than smell nice. Once released into the air, terpenes can react with sunlight and other chemicals to form tiny particles that influence cloud formation. By changing the way sunlight interacts with the atmosphere, they can even help cool the climate slightly. In this way, the familiar smell of pine is tied to processes that ripple through the skies above. To breathe it in is to take part in a cycle that stretches from the soil to the atmosphere, from the comfort of a forest walk to the vast balance of Earth's climate system. It's a reminder that even scents can shape the world. Forests cool entire regions by several degrees. Step into a forest on a hot summer day, and the difference is immediate. Shade is part of the reason, but forests cool the air in deeper ways. Through transpiration, trees release water vapor, which absorbs heat as it evaporates. This natural air conditioning can lower local temperatures by several degrees, creating microclimates that are crucial for plants, animals, and humans alike. On a larger scale, vast forests like the Amazon cool entire regions, influencing weather systems and stabilizing climates. Cities surrounded by forest often experience cooler conditions than those bordered by barren land. In a warming world, these cooling effects become more than pleasant. They're essential. Forests act as natural thermostats, regulating heat through their quiet, constant processes. Each rustling leaf contributes to the balance, making forests not only green havens, but living machines that ease the planet's fever. Forests help keep the poles frozen. It may seem strange to link tropical forests with the icy poles, but Earth's systems are deeply connected. Moisture and heat released from forests influence atmospheric circulation patterns that stretch across hemispheres. In turn, these patterns affect the stability of polar ice. Forests also store massive amounts of carbon, keeping greenhouse gases out of the atmosphere. Without this service, polar regions would warm much faster, hastening ice melt. Even the boreal forests, close to the Arctic, play a direct role, insulating permafrost and shading snow. The fate of the poles, then, is tied to the fate of the forests. What happens in the green belts of Earth ripples outward, all the way to the frozen edges. Protecting forests helps protect ice, and by extension, the oceans and coasts everywhere. The world is a web. Tug one strand, and the poles themselves can shiver. Forests influence global wind patterns. Forests do not simply stand still beneath the atmosphere, they actively shape its movements. As forests pump water vapor upward, they create pressure differences that drive winds across vast distances. This effect, called the biotic pump, is thought to help pull moist air inland from the oceans. Without it, many interior regions of continents might dry into deserts. Studies suggest that forests influence the circulation of air not just locally, but globally, altering jet streams and storm paths. In this way, the swaying of leaves in one place can ripple into weather thousands of miles away. Winds that bring rain to farmlands or steer storms across oceans may owe part of their path to the silent work of trees. It is one of the clearest signs that forests are not passengers in Earth's climate, but pilots guiding the flow of air. Some trees release chemicals that affect human moods. If you've ever felt calmer walking among pines, there may be more than imagination at work. Many trees release airborne chemicals called phytoncides, natural compounds that help protect them from insects and disease. When humans breathe these in, studies suggest they can lower stress hormones, reduce blood pressure, and even boost immune activity. This is one reason why forest bathing, a practice that began in Japan, has become a recommended form of therapy. Inhaling the gentle scents of cedar, pine, or cypress isn't just pleasant, it changes body chemistry in measurable ways. Forest air, then, isn't only oxygen-rich, it carries subtle medicine. Trees, defending themselves, end up soothing us. The connection hints at how deeply intertwined human biology remains with the environments we evolved in, reminding us that forests are not just scenery, but quiet partners in our well-being. Forest sounds can reduce human stress hormones. Close your eyes in a forest, and sound takes center stage. Wind brushing through leaves, birds calling, insects buzzing, water dripping from branches. Research shows that these natural soundscapes can measurably reduce cortisol, the body's primary stress hormone. Unlike the unpredictable noise of traffic or machines, forest sounds are patterned and rhythmic, which the brain interprets as safe. This calming effect helps slow heart rate, deepen breathing, and shift the nervous system into a more relaxed state. Some hospitals even play forest recordings to aid patient recovery, and urban planners study how soundscaping might bring similar effects to cities. Yet nothing compares to the real thing, the immersive, layered chorus of a living forest. Listening to it feels like resetting the mind, a reminder that the simplest medicine can be found not in silence, but in the voices of trees and the lives around them. Forests can change the color of the atmosphere. On a hazy summer afternoon, you might notice a bluish tint over the horizon when looking across a vast forest. That glow isn't an illusion. It's the atmosphere painted by trees. Forests, particularly those filled with pines, release organic compounds that scatter sunlight in specific ways. The scattering shifts the color of the air, giving it a faint blue cast. This effect is so pronounced in the Appalachian Mountains that they're nicknamed the Blue Ridge. What you're seeing is not just distance or haze, but the breadth of trees altering how light bends and spreads. It means that forests literally tint the air around them, changing the way we perceive landscapes. Every shimmering ridge, every misty horizon, is shaped not just by rock and sky, but by countless leaves releasing invisible chemicals into the air. The nighttime forest sky can glow with invisible radiation. Step into a forest at night, and the darkness may feel absolute. But above the canopy, the sky can glow faintly, not with visible light, but with radiation invisible to the human eye. Earth's atmosphere naturally emits faint bands of energy, known as airglow, caused by chemical reactions high above. Forest regions often have less light pollution, making this glow more noticeable with sensitive instruments. To creatures like certain insects and nocturnal animals, these faint emissions may actually be visible, shaping how they navigate and behave. In this way, the night sky above a forest is never truly dark. It hums quietly with energy, a hidden glow that our eyes cannot see. For humans, it adds another layer of mystery to nights in the woods, that even in darkness, there is light flowing overhead, just beyond our perception. Forest air is filled with microscopic particles from trees. Every breath you take in a forest is filled with more than oxygen. The air is thick with microscopic particles released by trees, droplets of water vapor, fragments of organic compounds, even spores and pollen. These particles act as invisible messengers of the forest, drifting upward to shape clouds or downward to settle into the soil. Some particles even serve as seeds for raindrops, meaning the very air above a forest helps determine when and where it rains. For humans, inhaling this air can feel fresher and lighter than urban air, in part because of these natural aerosols. They help scrub pollution and give forests their distinct, clean scent. To breathe forest air is to take in more than molecules of oxygen. It's to join the living cycle of particles, chemistry, and biology that make the forest a system far bigger than the trees alone. A single teaspoon of forest soil contains billions of organisms. Beneath the carpet of leaves and moss lies a universe so small we rarely think about it. Scoop up a teaspoon of forest soil and you are holding billions of microscopic organisms. Bacteria, fungi, protozoa, and tiny nematodes all thrive in the damp darkness, breaking down organic matter and recycling nutrients. Many of these microbes are unknown to science, their function still a mystery. Yet together they form the foundation of the forest's health, feeding trees, shaping soil, and defending roots against disease. Without them, the towering canopy above would collapse. In a way, a forest's greatest diversity is not in the birds overhead or the mammals roaming the floor, but in the unseen world beneath our feet. Every step across the soil is a step across an invisible galaxy of life, buzzing with activity too small to see, yet crucial for everything we can. The forest floor breathes carbon in daily rhythms. Forests don't just breathe across seasons. They inhale and exhale on daily cycles. At night, when photosynthesis stops, the soil and roots release carbon dioxide, building up just above the forest floor. By day, sunlight powers the trees to take that carbon back in, lowering its concentration. This rhythmic inhale and exhale happens so reliably that scientists can measure time of day in a forest by carbon levels alone. In a sense, the entire ecosystem keeps a heartbeat tied to the sun, each day marked by pulses of breath. These daily shifts remind us that forests are not static backdrops, but dynamic, living systems. the quiet breathing of soil and leaves. Unseen but constant is the soundless rhythm that underlies every rustle, caw, and flicker of light beneath the canopy. Insects may outnumber leaves in some forests. Leaves seem endless in a forest, carpeting the canopy and littering the ground. Yet in some tropical forests, insects actually outnumber them. Ants march in armies of millions, termites build towering mounds, and beetles of every shape and color scurry across bark and soil. Scientists estimate that a single hectare of rainforest can contain over 40,000 species of insects, with countless individuals hidden in every layer of the ecosystem. Many have not even been named or studied. This abundance of insects is not just background noise. They pollinate plants, recycle nutrients, and serve as food for countless other animals. Without insects, the forest would unravel. Their sheer numbers make them the true undercurrent of life, more numerous than leaves, buzzing and crawling in an unseen flood of motion that holds the whole ecosystem together. Some forest plants trap and eat insects. Forests are not only filled with insects, they are also home to plants that prey upon them. Carnivorous plants like pitcher plants and sundews lure insects with sweet scents or sticky surfaces. Once caught, the insects are digested with special enzymes, giving the plants a boost of nutrients they can't always get from the poor forest soil. In some tropical forests, pitcher plants grow large enough to catch not just flies, but frogs, and even small mammals. These unusual strategies show how competition shapes survival. In the dense, shady understory where sunlight is scarce and soil is poor, plants adapt in strange and surprising ways. To see a plant feasting on an insect is to glimpse evolution's creativity, a reminder that even in the quietest corners of the forest, drama unfolds between twa, hunter and hunted, leaf and wing. Forests harbor viruses we've never discovered. Deep within forest soils, in pools of water, and even inside the bodies of animals and insects, viruses thrive in numbers, beyond imagination. Many of these viruses remain unknown to science. Some may play roles in regulating microbial populations, balancing ecosystems in ways we barely understand. Others might one day prove useful, carrying genetic tools that could inspire new medicines or technologies. Forests are reservoirs of genetic diversity, and viruses are part of that hidden archive. While some can cause disease, many exist quietly, interacting with their hosts without harm. Studying them is difficult because they often lie dormant or hidden. But the truth is clear. Forests are not only home to towering trees and colorful creatures, but also to invisible worlds of life that may shape the future of Cha. Science. Beneath every leaf and root, unseen forces are at work. The canopy of a rainforest can be as dense as concrete. When you stand in a tropical rainforest, it's easy to feel how much light is filtered above you. The canopy, the interwoven layer of branches and leaves high overhead, can be so thick that less than 1% of sunlight reaches the forest floor. In some places, the canopy is nearly impenetrable, with overlapping foliage acting like a living ceiling. Scientists have compared its density to concrete, because water and even falling objects often stop before they reach the ground. This shield protects the understory, keeping it cooler and more humid than the world above. It also means many plants and animals live their entire lives in the canopy, never descending to the soil. For them, the treetops are the true forest, complete with rivers of vines, platforms of branches, and a ceiling that is less sky than endless. Green architecture. Forest canopies can hold entire miniature worlds. High above the forest floor, a hidden realm thrives. In the canopy, mosses, orchids, and bromeliads cling to branches, creating tiny gardens that collect water in their leaves. These little pools become homes for frogs, insects, and even small crabs. Ant colonies tunnel through branches, while colorful birds and monkeys leap among the treetops. Scientists who climb into these aerial ecosystems often describe them as stepping into another planet. The canopy is so vast that it doubles the surface area of the forest, providing habitats layered above one another like stacked landscapes. For centuries, this world went unexplored, but modern canopy research has revealed it to be one of the most diverse ecosystems on Earth. It is a reminder that forests are not flat but vertical, rising into the sky and holding as much life above the ground as below. Forest canopies contain more species than the forest floor. It might seem that most life is at ground level, but the opposite can be true in rainforests. The canopy teems with more species than the forest floor itself. Insects, birds, reptiles, and mammals all find food and shelter in the treetops. Many plants grow only in this layer, clinging to branches and never touching the soil. Scientists believe more than half of all rainforest species may live exclusively in the canopy. The diversity is so immense that each square meter of canopy could contain more life than an entire meadow elsewhere. Some researchers even call the canopy the real rainforest, because it holds the majority of its creatures. For the animals and plants that thrive there, the canopy is a boundless city in the sky, busy, crowded, and rich with resources, while the ground below is just another distant layer, seldom visited. Forest floors rarely see more than 1% of sunlight. Beneath the towering canopy, the forest floor lies in near constant shadow. In dense rainforests, only a fraction of sunlight makes it down through the leaves, often less than 1%. This dimness shapes everything that grows and lives there. Plants have to adapt to low light, spreading wide leaves to capture what little sun they can. Some bloom directly on trunks, where light filters through gaps. The shadowy environment also makes the floor cooler and more humid, perfect for decomposers like fungi, termites, and beetles that recycle fallen material. For many animals, the darkness provides safety from predators, while for others it's a challenge, demanding keen senses of smell or hearing. The forest floor may feel quiet, but it is alive with motion, a shadowed stage where survival depends on thriving in the absence of light. Trees in dense forests may never see direct sunlight. In crowded forests, competition for sunlight is fierce. Some trees grow straight and fast, racing to reach the canopy before their neighbors. Others are less lucky. Entire generations of saplings may grow for decades in the shadow of larger trees, never once touched by direct sunlight. Instead, they survive on what little filtered light trickles through the canopy. Remarkably, many of these shade-tolerant species can wait patiently for years, even centuries. If an older tree falls and a patch of sunlight opens, the waiting sapling suddenly surges upward, seizing its chance. This patience is built into the life cycle of the forest, a constant, quiet contest for light. It means that even a fallen tree is not just an end, but an opportunity, a mocking growth for those that have waited their whole lives for the sun. Some forests are so dark, they feel like night at noon. In certain rainforests, the canopy is so thick that the forest floor resembles twilight, even at midday. Travelers describe these places as dim, hushed, and otherworldly, where shadows stretch endlessly and colors fade into shades of green and gray. In this near-perpetual gloom, animals have evolved extraordinary adaptations. Some frogs and insects glow faintly to attract mates, while larger animals rely more on sound than sight to find food and navigate. The darkness also keeps temperatures cool and humidity high, which helps decomposition run at lightning speed. What feels mysterious to humans is simply normal to the life inside. For the creatures of the deep forest floor, noon and midnight can look nearly the same. Time itself seems slower here, hidden under the constant shade of leaves that never let the sun fully in. Some forests contain ancient human structures still hidden. Forests are not only homes to nature, they also hide traces of human history. In the Amazon, LiDAR scanning has revealed enormous ancient cities buried beneath the trees, complete with roads, canals, and pyramids. In Cambodia, the ruins of Angkor were long swallowed by jungle before being rediscovered. Dense forests can conceal stone temples, forgotten villages, and lost trade routes for centuries, sometimes millennia. Trees grow over walls, roots wrap through stairways, and moss covers carvings until they seem like part of the natural world. For archaeologists, forests are both guardians and obstacles, preserving ruins while keeping them hidden. Each new discovery reminds us that the boundaries between human history and wild nature are not as separate as they seem. Forests are not empty spaces. They are layered with the echoes of civilizations that once thrived among the trees. There are entire ecosystems in forest tree hollows. A hollow in the trunk of an old tree may look like a simple cavity, but to countless creatures, it is a world of its own. Rainwater collects inside, forming miniature ponds where insects, frogs, and even small crabs live. Birds nest in the sheltered cavities, while bats and squirrels find roosts safe from predators. Microbes thrive in the damp wood, recycling nutrients that seep into the water. In tropical forests, these tree holes can be abundant enough to sustain whole communities of species. Each hollow becomes a self-contained ecosystem, balancing life in miniature. They remind us that forests operate on every scale, from miles of canopy to pockets small enough to fit in your hand. Even the smallest crevice in a tree can pulse with life, a hidden world nested inside a larger one. Bamboo forests can grow taller than skyscrapers in just weeks. Bamboo is not a tree but a grass, yet in forests where it dominates, it can outpace nearly any plant in growth. Certain bamboo species can grow almost a meter in a single day under the right conditions. Within weeks, shoots stretch upward, forming dense groves that tower like green skyscrapers. In Asia, bamboo forests are home to red pandas, golden monkeys, and the iconic giant panda, which feeds almost exclusively on bamboo shoots. Humans, too, rely heavily on bamboo, using it for construction, food, and even textiles. Its rapid growth makes it one of the most renewable resources on Earth. Walking through a bamboo forest feels unlike any other. The stalks rise straight and tall, creaking in the wind, creating a rhythmic, almost musical atmosphere. It's a reminder of the sheer power of life's speed when conditions are just right. Rainforest trees can flower directly on their trunks. In most forests, flowers sprout from branches high above. But in rainforests, many trees use a different strategy called cauliflory, producing flowers and fruits directly from their trunks. This allows animals like monkeys, bats, and rodents to reach and pollinate them more easily, without needing to climb into the canopy. Some of the rainforest's most iconic plants, such as cacao trees which give us chocolate, rely on this method. The trunks become decorated with clusters of blossoms or heavy fruits, hanging like ornaments on a living pillar. It's an adaptation perfectly tuned to the dense, vertical world of the forest. Cauliflory is a striking reminder that plants are endlessly inventive, shaping their forms to fit the creatures around them. In the rainforest, even the tree trunks are alive with blossoms, turning the forest floor into a garden as well. The Amazon's trees release more oxygen than all the world's grasslands. The Amazon rainforest is sometimes called the lungs of the earth, and while that phrase is a little simplified, it holds truth in one key way. The trees of the Amazon release more oxygen into the atmosphere than all the world's grasslands combined. Each day, billions of leaves photosynthesize, splitting carbon dioxide and releasing oxygen as a byproduct. Grasslands are vast too, but their smaller plants simply don't compare to the sheer scale of rainforest trees. some stretching hundreds of feet into the sky. This oxygen circulates around the planet, mixing into the air we all breathe. While much of it is used up again by plants, animals, and microbes in the forest itself, the Amazon's contribution is still immense. It is a reminder of how deeply our atmosphere is tied to the unseen daily work of trees, breathing in carbon and breathing out life. Forests provide the majority of Earth's oxygen exchange. It is easy to think of oceans as Earth's great oxygen producers, and they are. But forests play an equally critical role in the planet's oxygen exchange. Through photosynthesis, forests absorb vast amounts of carbon dioxide and release oxygen into the atmosphere. At the same time, the countless organisms that live in forests consume oxygen and release carbon back, creating a continuous cycle. Unlike fields or deserts, forests run this process at massive scales, with layer upon layer of leaves at work. While oxygen produced is balanced by consumption, forests act as stabilizers, keeping the cycle smooth and resilient. Without them, Earth's oxygen balance would falter, with unpredictable results for every breathing creature. Each inhalation we take is supported not only by oceans and plankton, but by forests, with their endless green machinery converting sunlight into the air of keen life. Some trees store water in their trunks, like living reservoirs. In certain forests, survival depends on being able to endure dry spells. Some trees have adapted by storing water directly inside their trunks. These natural reservoirs can hold thousands of liters, enough to sustain the tree through months of drought. Baobab trees in African forests are among the most famous examples, their swollen trunks capable of providing water to animals and even humans who cut into them. In tropical rainforests, other species also practice water storage, maintaining hidden reserves in their spongy wood. This adaptation helps stabilize entire ecosystems, ensuring that life can continue even when rains falter. To touch one of these trees is to touch a living well, quietly holding water within its fibers. In a way, they are both plants and guardians of water, embodying resilience in landscapes where thirst can be a constant threat. Forests store more fresh water than all the world's lakes. When we picture fresh water, we think of lakes and rivers, but forests hold more than both combined. Much of this water is hidden underground, stored in soil and aquifers that forests help replenish. Tree roots draw moisture upward, while canopies slow rainfall so it can seep gently into the ground instead of running off. In wetlands and peatlands, water is locked away in mosses and saturated soils for centuries. These hidden stores add up to a reservoir larger than all the world's lakes put together. This means forests are not only homes for wildlife, but also vital components of the global water cycle. Every drop of rain that filters through leaves and roots becomes part of a system that provides drinking water, irrigation, and stability for billions of people. Forests, quietly, are our greatest freshwater banks. Forests help shape the chemistry of the oceans. It may seem like forests and oceans are separate worlds, but they are tied through rivers. Nutrients washed from forest soils flow into streams, which carry them to seas. This input feeds plankton blooms that form the base of marine food chains. Forests also influence how much carbon dioxide dissolves in seawater through their role in absorbing or releasing carbon into the atmosphere. Even airborne particles released by trees, called aerosols, can drift over the ocean, affecting cloud cover and rainfall patterns that regulate salinity. In this sense, forests help set the stage for ocean chemistry, balancing nutrients, acidity, and carbon cycles. To imagine forests and oceans as opposites misses the truth. They are partners, passing invisible messages back and forth. The health of the sea begins in part with the shade of trees and the soil of faraway forests. Trees in a forest can change the chemistry of rain. Rain falling through a forest canopy is not the same as rain that falls in an open field. As droplets brush against leaves and bark, they pick up chemicals released by the trees. These might include organic acids, sugars, or even antimicrobial compounds. When the rain reaches the ground, its chemistry has been altered, sometimes feeding soil microbes or inhibiting pathogens. This process is called throughfall, and it creates a unique water signature for each forest. Scientists studying rainfall under trees find that the nutrients in it can fertilize the forest floor, helping seedlings grow. Some species even release compounds that discourage competitors from sprouting nearby. In this way, trees don't just passively receive rain, they change it, flavoring the water that falls upon their roots. Each shower becomes not just weather, but part of the forest's own dialogue with itself. Some forest rivers turn black from leaf chemicals. In parts of the Amazon and other tropical forests, rivers can appear dark, almost like tea. This is not pollution, but the result of tannins, natural chemicals leached from fallen leaves and plant matter. As rainwater flows through soil rich in decaying vegetation, it absorbs these tannins, staining the rivers brown or nearly black. These blackwater rivers are low in nutrients, but high in clarity, often supporting unique ecosystems adapted to their chemistry. Fish, insects, and plants living in them are different from those in nearby whitewater or sediment-rich rivers. The contrast creates a mosaic of aquatic habitats, each with its own web of life. Floating quietly on a blackwater river feels eerie and calm, as though the forest has dissolved itself into the water, painting it in the colors of leaves long fallen. Forest leaves may hold traces of distant ocean spray. It seems impossible that the sea could reach a forest deep inland, but it does. Tiny salt particles lifted from crashing waves can drift for hundreds or even thousands of miles on winds. Eventually, they settle on forest leaves, sometimes becoming part of the chemistry that trees absorb. Scientists analyzing leaf surfaces have found traces of ocean salt far from any coast. These particles may influence how leaves take in water or how they interact with sunlight. They can also serve as starting points for chemical reactions in the atmosphere above the forest. The connection is subtle but profound. Forests breathe not only their own local air, but also faint whispers from the sea. Every tree leaf may carry, in microscopic form, a reminder of waves that broke on distant shores. Leaves in a forest can change color without autumn. In temperate regions, we associate changing leaf colors with autumn. But in tropical forests, leaves can shift hues at any time of year. Young leaves often flush red or orange when they first emerge, a natural sunscreen protecting them from intense sunlight until they mature. Other species change color as a signal, perhaps to attract pollinators or warn insects away. In some forests, whole stretches of canopy can suddenly blaze with patches of red, yellow, or purple, even when there is no seasonal shift. This constant turnover of colors is one reason tropical forests look so vibrant and varied. The shifting palette is not about winter or fall, but about survival strategies woven into leaves themselves. The forest, at any moment, is alive with quiet bursts of color, as if reminding us that change is not bound to seasons. Forests influence the migration of global bird populations. For countless bird species, forests are not just homes, but waypoints on long journeys. Migratory birds use forest habitats as stopovers, resting and feeding during flights that can span continents. The availability of forest cover along these routes often determines whether a migration succeeds. Some forests provide fruit at just the right time of year, fueling flights across oceans or deserts. Others offer shelter from predators and storms. Even birds that do not live in forests year-round often depend on them for these crucial stages of their journeys. The result is that forests help shape the very patterns of global migration, guiding flocks across hemispheres. When forests vanish, entire migratory routes can collapse. To hear the chorus of birds in spring, is to hear not just local voices, but travelers whose survival depends on forests far beyond our horizon. Forest elephants engineer the structure of African forests. In the Congo Basin, forest elephants play a role far larger than their size suggests. As they move through dense undergrowth, they trample pathways that open space for light to reach the forest floor. They feed on fruits and carry seeds in their stomachs, depositing them miles away in rich piles of fertilizer. Some seeds can only sprout after passing through an elephant's digestive system, making the animals essential gardeners of the forest. Over time, elephants shape the very architecture of the forest, influencing which trees dominate and how dense the canopy grows. Without them, some regions would grow choked with vegetation, while others might lose entire species of trees. Forest elephants are not just residents of the Congo, they are engineers, sculpting their environment in ways that ripple through entire ecosystems, proving care that animals and trees are deeply intertwined in the building of forests. Some forests are maintained by bats and birds carrying seeds. Forests don't grow themselves alone. They rely on countless helpers. Bats, for instance, feed on fruits at night, then drop seeds across wide distances as they fly. Birds do the same by eating berries and later scattering seeds in their droppings. These winged dispersers allow forests to expand far beyond the shadow of any one tree. In some regions, bats are responsible for the regeneration of more than 90% of new seedlings after disturbances like fires or logging. Birds, too, keep forests resilient by ensuring diversity spreads across landscapes. Without them, many forests would shrink and fragment, unable to reseed themselves effectively. Every flutter of wings in the night sky or every bird call at dawn is part of a much larger cycle, one where forests and their flying companions co-create the Tao, green expanses that define so much of Earth's life. Certain birds guide humans to honeycombs deep in forests. In parts of Africa, a remarkable partnership exists between people and birds known as greater honey guides. These small birds have evolved to lead humans directly to wild beehives hidden in dense forests. The bird calls to attract attention, then flies ahead, pausing along the way to keep humans following. Eventually, it leads them to honeycombs they might never have found on their own. Once humans break open the hive and collect honey, the birds feast on the wax and larvae left behind. It's a cooperative relationship stretching back thousands of years, one of the few known examples where wild animals and humans communicate intentionally for mutual benefit. For forest-dwelling communities, the honey guide is both helper and companion, proof that the forest is a place not just of survival, but of surprising alliances that cross the boundaries between species. The Amazon contains more species than any other forest. No forest on Earth can match the Amazon in sheer diversity. Spanning over 5.5 million square kilometers, it is home to more than 16,000 tree species and countless animals, insects, and fungi. Scientists estimate that 1 in 10 known species on Earth lives there. Each layer of the forest adds another dimension. The canopy is alive with monkeys and birds. The understory holds jaguars and snakes, and the rivers teem with fish and EP, dolphins. Even after centuries of exploration, new species are discovered regularly, from brightly colored frogs to entire groups of insects never seen before. This concentration of life is so great that a single square kilometer can contain more plant species than all of North America. The Amazon is not just a forest, it is Earth's grand archive of biodiversity, a living library still being read, page by page. Some forests are so remote, they remain almost completely unexplored. While satellites map nearly every corner of the globe, some forests are so vast, dense, and difficult to reach that humans have barely set foot in them. Parts of Papua New Guinea, deep stretches of the Congo Basin, and isolated valleys of the Amazon remain largely untouched. Scientists suspect these places harbor thousands of undiscovered species, from insects to mammals. For local communities, they may be well known, but to the outside world, they are blank spaces on the map. The challenge of reaching them, swamps, thick canopies, or sheer remoteness, makes exploration daunting. These unexplored forests remind us that despite modern technology, Earth still holds pockets of mystery. In their depths, life continues on its own terms, unobserved, unmeasured, and unrecorded, just as it has for millions of years. Some forests grow on floating mats of vegetation. In river floodplains and wetlands, entire forests sometimes grow on mats of floating vegetation. These mats form when roots and soil interweave so tightly that they create a buoyant surface. Trees and shrubs then sprout on top, turning the mat into a drifting island of forest. Known as suds in Africa, or floating meadows in South America, these ecosystems are constantly moving, carried by winds and currents. Animals adapt to them, with fish feeding on roots dangling into the water, and birds nesting in the dense greenery. For humans, they can be both obstacles and wonders, blocking navigation but offering floating pastures. These forests blur the line between land and water, existing in a state of perpetual drift. To walk on one feels like stepping on soft ground that sways beneath your feet. A forest afloat, alive and wandering. There are forests growing beneath the ocean surface. Forests are not limited to dry land. Under the sea, kelp forests stretch upward from the ocean floor, anchored by root-like holdfasts. These towering algae can grow more than 100 feet tall, forming dense underwater canopies where light filters through like in a terrestrial forest. Fish weave among the fronds, sea otters hunt for urchins, and seals dart through the green corridors. Like land forests, kelp forests create shade, shelter, and abundant food, making them among the most productive ecosystems on Earth. In places like California and Chile, they support fisheries and protect coastlines by damping waves. Though not made of trees, their structure and role mirror terrestrial forests so closely that they are considered oceanic equivalents. They remind us that the concept of a forest extends beyond soil, thriving even in the restless blue of the sea. Some forests rest on active volcano slopes. In countries like Indonesia, Japan, and Costa Rica, forests grow on the slopes of active volcanoes. These landscapes are precarious, fertile with volcanic soil, but threatened by eruptions, ashfall, and lava flows. The minerals released by past eruptions create some of the richest soils in the world, allowing lush forests to flourish. Plants colonize new lava flows quickly, sending roots into cracks and beginning the process of renewal. Animals follow, reclaiming the land even as danger lingers beneath their feet. Forests on volcanic slopes are symbols of resilience, showing how life not only recovers from disaster, but depends on it. Every eruption sets the stage for rebirth, cycling destruction into fertility. These forests are both fragile and fierce, forever rebuilding themselves at the edge of Earth's fire. The Black Forest inspired some of the world's darkest fairy tales. Germany's Black Forest is a place of towering pines, deep shadows, and mist that clings to valleys. Its atmosphere has long stirred human imagination. The brothers Grimm drew inspiration from its dense woods when recording folk tales, stories of witches, wolves, and children lost among trees. For centuries, the forest's gloom and isolation made it a backdrop for myths of danger and magic. Yet the same forest is also filled with vibrant wildlife and picturesque villages, showing the contrast between human perception and ecological reality. What people saw as dark and forbidding was, to the animals within it, simply home. The Black Forest is a reminder that our relationship with forests is not only biological, but cultural. They shape our imaginations as much as our ecosystems, becoming theaters where fears and wonder take root side by side. Ancient forests are being preserved in stone for hundreds of millions of years. Long before humans walked the earth, forests flourished, and in some cases, they left behind fossilized remains. Petrified forests, found in places like Arizona, Argentina, and Antarctica, are made of trees turned to stone over hundreds of millions of years. Minerals replaced the organic material, preserving details down to the rings and bark textures. These stone forests reveal what Earth's ecosystems looked like in prehistoric eras, including species that no longer exist. Some fossils are so well preserved that scientists can study microscopic structures inside. Walking among them feels like wandering through time, where trunks lie frozen in mid-growth, silent and unchanging. They are reminders that forests are ancient, spanning epochs, their roots reaching not just into soil, but into the deep history of life itself. Forests are expanding in some parts of the world. Although deforestation is a global concern, not all forests are shrinking. In parts of Europe, North America, and even China, forests are actually expanding. This regrowth often happens when farmland is abandoned or when large-scale reforestation projects take root. In Europe, centuries-old farmland is slowly being reclaimed by trees, and in China, massive planting campaigns have added billions of new saplings to the landscape. These recovering forests may lack the complexity of ancient ones, but over time, they begin to attract wildlife, restore soils, and capture carbon. It is a hopeful reminder that ecosystems can recover if given the chance. Forests, though fragile, are also resilient. They can return where once they were cut, growing back into places where the sound of wind in branches has not been heard. For generations. Some forests are growing where deserts once spread. Across parts of Africa, Asia, and the Middle East, forests are beginning to sprout where barren lands once stretched. This transformation is often the result of intentional restoration efforts, where humans plant trees to combat desertification. In places like northern China's Great Green Wall, millions of trees are being cultivated to halt the spread of the Gobi Desert. In the Sahel region of Africa, communities are planting native species that thrive in dry conditions, helping restore soil and bring back shade and water. Nature also plays a role, as shifts in rainfall and climate create opportunities for regrowth. These new forests may not yet rival ancient rainforests, but they are living proof that deserts are not always destiny. With time and care, even the driest places can bloom with forests once again. The world's rarest forests exist only on tiny islands. Scattered across the oceans are islands where forests grow nowhere else on Earth. The cloud forests of Hawaii, the dragon blood tree groves of Socotra, and the palm forests of the Seychelles all exist in fragile isolation. These rare habitats are often filled with species found nowhere else, evolved in the isolation of their island homes. Because they are so limited in size, even small disturbances can have outsized impacts. A single storm, invasive species, or human settlement can reshape them dramatically. Yet their uniqueness makes them biological treasures, living museums of evolution's creativity. To walk among them is to see life that exists in no other place, forests as rare and delicate as jewels, scattered across the vast ocean. The world's smallest forests can be just a few trees wide. Not all forests are vast expanses stretching across continents. In some places, a cluster of trees just a few dozen meters wide qualifies as a forest. These miniature forests can grow in valleys, along rivers, or on isolated hills. Despite their size, they often harbor surprising biodiversity. Small mammals, birds, and insects can thrive in these pockets of habitat, treating them as vital refuges in otherwise open landscapes. Scientists studying them have found that even the tiniest forests can help store carbon, regulate water, and protect soils. For nearby communities, they may provide shade, food, or cultural meaning. These small forests remind us that size is not everything. Even a handful of trees growing together can carry the spirit and function of a forest, proving that resilience and wonder exist at every scale. Some forests contain species found nowhere else. Isolation creates uniqueness. Forests separated by mountains, rivers, or oceans often harbor species that live in no other place on Earth. Madagascar's forests, for instance, contain lemurs and baobabs unlike anything elsewhere. Australia's eucalyptus forests hold marsupials and birds that evolved in isolation. Even small patches of forest can shelter rare plants or insects that never spread beyond their boundaries. These species are often fragile, vulnerable to extinction if their habitats are lost. Yet their existence highlights the creativity of evolution, sculpting life to fit local conditions. Every forest is a stage for experiments millions of years in the making, many of which can only be seen in one corner of the planet. To step into such a forest is to enter a world unique to itself, with species that carry the story of place written in their very being. Forests can create their own weather forecasts. Forests are not passive when it comes to weather. They give clues about what is to come. Scientists studying forests have found that patterns in leaf chemistry, humidity, and even insect activity can signal changes in rainfall and temperature before they arrive. Indigenous communities around the world have long read these signs. Knowing which bird calls or tree blooms means storms are near. In a sense, forests forecast their own weather by responding to subtle shifts in the atmosphere. As trees release water vapor and chemicals, they influence cloud formation above, creating feedback loops that shape local weather. To walk through a forest is to enter a natural barometer, where every sound, smell, and shimmer of leaves holds hints of tomorrow's skies. Forests at night can be louder than cities. When the sun sets, many forests do not fall silent. They come alive with sound. Frogs croak, insects hum, owls call, and mammals rustle in the underbrush. In tropical forests especially, the combined chorus of nocturnal creatures can surpass the volume of busy urban streets. Scientists recording soundscapes at night often find layers upon layers of calls, from low rumbles to high-pitched chirps, each occupying its own frequency, like instruments in an orchestra. This nighttime chorus is not random noise. It is communication, competition, and survival playing out in sound. For humans, the effect can be overwhelming, even disorienting, a reminder that the forest never truly sleeps. Its voice simply shifts, moving from the bright chatter of daytime birds to the deep, pulsing music of night. The soundscapes of forests change dramatically from dawn to night. From the first light of dawn to the stillness of midnight, forests move through sound cycles as rich as any symphony. Morning often begins with birdsong, as countless species greet the sun. Insects take over as the day warms, their buzzing filling the air. Afternoon rains may bring a drumbeat of water on leaves, followed by the return of bird calls as storms pass. At dusk, frogs begin their chorus, soon joined by nocturnal mammals and insects. Each layer of life occupies its own time, its own rhythm, weaving a continuous soundtrack. Scientists studying these cycles find that the forest's soundscapes are not random but carefully partitioned. Each species adapts its timing to be heard without being drowned out. To listen across a full day is to hear the heartbeat of the forest, measured not in silence, but in waves of sound. Forests sing with constant insect choruses. In many forests, insects are the true musicians. Cicadas, crickets, and countless other species produce constant choruses, creating a background hum that rises and falls like breathing. Some cicada species emerge in synchronized waves, filling entire landscapes with deafening song that can be heard miles away. Others sing nightly, their rhythms overlapping in complex patterns that scientists compare to music. These insect choruses serve important purposes, attracting mates, marking territory, or confusing predators. For humans, they become the defining sound of warm nights in the woods. While birds and mammals may come and go, insects keep the soundtrack steady, a ceaseless pulse that marks the life of the forest in vibration and hum. Without them, the forest would feel strangely empty, stripped of its constant, living music. Some forests hold secrets of life's earliest evolution. Certain ancient forests preserve traces of Earth's evolutionary history. In Canada's Mistaken Point and other fossil-rich sites, imprints of primitive organisms appear in what were once forested or vegetated regions. Even today, untouched forests hold genetic lineages that stretch back hundreds of millions of years. Cycads, for example, often called living fossils, still grow in tropical forests, much as they did when dinosaurs roamed. These remnants link modern ecosystems to prehistoric ones, bridging the vast gulf of time. In their leaves, spores and seeds are clues to how life diversified, adapted, and endured. Forests are not only alive in the present, they are archives of life's deep past, holding secrets that science is only beginning to unlock. The roots of some forests stretch for miles underground. Beneath a forest lies a hidden world, as vast as the canopy above. Tree roots interlace with one another, creating sprawling networks that can stretch for miles. In places like mangrove forests, roots extend into rivers and seas, stabilizing the shoreline while reaching far underground to find nutrients. In temperate forests, roots often connect trees together, allowing them to share water and minerals. This underground web is strengthened by fungi, forming what scientists call the wood wide web. Through it, trees can send sugars, chemical signals, or even warnings of danger. It means a forest is not a collection of individuals, but a community connected by living threads underground. Though unseen, these roots are as vital as trunks or leaves, binding the forest together into one great organism that grows, communicates, and survives in Sa. Unity. Some forest trees produce their own insect repellent. Forests are full of battles we barely notice. Many trees produce natural chemicals to deter insects from chewing their leaves. Eucalyptus trees, for example, release aromatic oils that repel pests and even inhibit competing plants. Pines ooze sticky resin that traps insects while releasing sharp scents that warn others. Some species adjust their defenses depending on the season or the scale of the attack. These natural repellents are so effective that humans often borrow them. Many essential oils and herbal remedies originate from forest trees. This quiet chemical warfare ensures that forests can endure despite the billions of hungry insects living among them. Every breeze that carries the scent of pine or eucalyptus is not just fragrance, but a shield, a living defense system built into the very fabric of the forest. Some trees defend each other from predators. Trees are not silent victims when grazed by animals. Studies in African savannas have shown that when giraffes start feeding on acacia leaves, the trees release chemicals into the air that drift downwind. Nearby acacias detect these signals and quickly increase the bitter tannins in their leaves, making them unappetizing. In this way, entire groves coordinate their defenses, protecting one another from overgrazing. It's a reminder that trees are not passive fixtures. They are active participants in their environment, capable of rapid responses to threats. This cooperation gives forests resilience, ensuring that predators like insects or herbivores cannot simply consume them unchecked. The forest behaves like a single organism, responding collectively to maintain balance and survival. Trees in a forest can heal each other. In some forests, trees seem to care for their neighbors. When a tree is damaged, nearby individuals sometimes send sugars and nutrients through underground root and fungal networks to sustain it. Even stumps with no leaves, incapable of photosynthesis, have been found alive for centuries, kept nourished by surrounding trees. Scientists suggest this sharing helps maintain forest stability, preserving root systems, stabilizing soil, and preventing gaps in the canopy. It suggests that forests prioritize collective health over individual survival. While helping may sound like human behavior, this flow of resources shows how interconnected trees truly are. A forest is not just a set of trees, it is a living community where survival is shared and where one tree's strength can become another's lifeline. Forests have been called the planet's lungs, but they do much more. Forests are often described as Earth's lungs because they absorb carbon dioxide and release oxygen. Yet their role is far greater. Forests regulate rainfall, stabilize soils, cool the air, and support biodiversity on a staggering scale. They influence weather patterns across continents and shape the global carbon cycle. They provide food, medicine, and shelter for countless species, including humans. To call them lungs captures only one function, when in reality, they are more like the heart, brain, and circulatory system combined. They keep the planet alive in ways far beyond breathing, serving as regulators of Earth's climate and stewards of life's diversity. Every forest is not just a collection of trees, but a planetary system in miniature, influencing the world far beyond its boundaries. Some trees can record centuries of climate change in their rings. Each year, a tree adds a new ring of growth. In dry years, the ring is narrow. In wet years, it grows wide. Over centuries, these rings create a precise record of climate history. By studying them, scientists can reconstruct rainfall, temperature, and even volcanic events that occurred long before human records. Some ancient trees hold more than 1,000 years of climate data inside their trunks. This science, called dendrochronology, allows us to understand how forests and the planet have responded to past changes. Trees are not only witnesses to time, but archivists, storing memory in wood. Every trunk is a living timeline, carrying within it the secrets of Earth's shifting climate across generations. Forests influence Earth's climate more than we realize. The role of forests in the global climate extends beyond carbon. They release water vapor, which rises and helps form clouds, cooling the planet by reflecting sunlight. Dark canopies absorb heat, while lighter forests reflect it. The chemicals trees emit can seed clouds, influencing rainfall thousands of miles away. The Amazon, for example, helps maintain weather patterns as far as North America. Cutting down forests not only releases stored carbon, but disrupts these climate systems. Forests are not passengers in Earth's climate journey. They are drivers, constantly shaping the balance of temperature, water, and atmosphere. Their influence stretches across continents, a quiet force holding the rhythms of the planet together. Forests may be cooling the planet more than we thought. Recent studies suggest forests play an even greater role in cooling Earth than once believed. Beyond absorbing carbon, their release of water vapor creates a natural air conditioning effect. This process, called evapotranspiration, can lower regional temperatures by several degrees. Forests also increase cloud cover, which reflects sunlight and helps prevent overheating. Together, these processes may offset more warming than scientists previously estimated. In a warming world, forests are not only victims of climate change, but vital allies against it. Each tree contributes to a global cooling system, one that works invisibly yet powerfully. The shade we feel under a tree is just a tiny glimpse of the planetary scale cooling forests provide every day. Every forest is both ancient and new at the same time. Forests are paradoxes of time. Some trees may be hundreds or even thousands of years old, while saplings spring up fresh each season. Soil beneath holds remnants of forests that existed millions of years ago, even as new seedlings prepare the canopy of tomorrow. In this way, every forest is both archive and frontier, ancient in its roots, new in its shoots. When we walk among trees, we are moving through a continuum of time, where generations overlap and life cycles blend. A forest is not frozen in history, but always in motion, holding the past while growing the future. This dual nature makes forests places where time itself feels layered, both eternal and fleeting at once. Forests still hide mysteries we have yet to discover. Despite centuries of study, forests remain full of secrets. New species of plants, insects, and fungi are discovered each year, many hiding in plain sight. The way trees communicate, the role of fungi in shaping ecosystems, and the full impact of forests on climate are still only partly understood. Even the sheer number of species living in the Amazon or Congo is unknown. In many ways, forests are frontiers as mysterious as deep oceans or outer space. They hold questions about life, evolution, and survival that science is only beginning to answer. Every step beneath their canopies is a step into the unknown, reminding us that even in familiar landscapes, mystery thrives. Some forests have trees that bleed red sap. In parts of Africa, South America, and Asia, certain trees release sap so vividly red it looks like blood. The most famous is the dragon blood tree, found on the island of Socotra, whose crimson resin has been used for medicine, dye, and ritual for thousands of years. When its bark is cut, the thick red liquid flows like a wound, giving the tree a mythic presence. Other species, such as some eucalyptus, also produce red-tinged sap. To ancient peoples, these trees seemed alive in a deeper way, as though their lifeblood was visible to the world. Today, scientists study the compounds in these resins, discovering antibacterial and protective properties. What looks strange or eerie is in fact a tree's way of sealing injuries and defending itself, a reminder that even in silence, forests bleed, heal, and endure. Some rainforest trees are taller than the Statue of Liberty. Deep in the Amazon, towering rainforest trees have been measured at over 80 meters, making them taller than the Statue of Liberty. These giants are often species like the Dinitia excelsa, rising above the canopy where only a handful of trees reach such heights. Growing in isolation, they capture sunlight above the rest, serving as towering landmarks in a sea of green. Scientists believe they play a special role in shaping forest ecosystems, hosting entire communities of birds, insects, and epiphytes in their branches. Their size also allows them to store massive amounts of carbon, anchoring the forest's climate-regulating power. To stand beneath one is to feel the same awe as gazing at a skyscraper, except this one is alive, ancient, and rooted in the soil of the earth itself. The largest known tree by volume weighs more than a blue whale fleet. In California's Sierra Nevada stands the General Sherman tree, a giant sequoia that holds the title of the largest known tree by volume. Its trunk alone contains over 1,000 cubic meters of wood, so massive that it outweighs dozens of blue whales combined. Yet, despite its incredible size, the General Sherman is not the tallest tree nor the oldest, showing that different records belong to different forest giants. Its immense volume is the result of thousands of years of steady growth, layer upon layer building into a monument of living tissue. Standing before it, humans appear like insects at the base of a mountain. This single tree is a forest unto itself, hosting mosses, birds, and insects, all dependent on the vast body of one living being that has stood for over 2 millennia. Bamboo can grow nearly a meter in a day. Among the fastest growing plants on Earth, bamboo is a marvel of speed and resilience. Some species can shoot upward almost a meter in a single day, a pace visible with the naked eye if observed closely. This rapid growth allows bamboo forests to regenerate quickly after harvest or disturbance, making them vital renewable resources in many parts of Asia and beyond. Bamboo's hollow, flexible structure gives it strength and elasticity, qualities humans have used for millennia in building, weaving, and even creating paper. In forests, bamboo provides shelter for countless animals, including the iconic giant panda. Its explosive growth also stabilizes soil and reduces erosion. Bamboo's speed is not just a curiosity, but a survival strategy, allowing it to compete for sunlight and space in dense, competitive ecosystems. Forests can change entire landscapes over millennia. Forests are not passive backdrops. Over time, they reshape the very land they grow on. Roots crack rocks, slowly grinding them into soil. Fallen leaves accumulate into thick layers of fertile ground, feeding generations of new growth. Forests capture rainfall and guide rivers, sometimes redirecting their flow entirely. In some regions, like the Amazon basin, forests recycle their own water, creating conditions that maintain the landscape itself. Over thousands of years, forests have transformed barren volcanic slopes into lush ecosystems and carved fertile plains from once stony ground. These transformations happen so slowly they are invisible to human eyes, yet they mark one of nature's most powerful forces, life itself shaping the planet. The Amazon River was once a swampy forest. Before it became the massive river system we know today, the Amazon basin was largely a swampy inland forest. Around 10 million years ago, tectonic shifts and rising mountains blocked water from flowing eastward, creating vast wetlands filled with trees and wildlife. Fossil evidence suggests this swampy forest supported crocodiles the size of buses and giant turtles alongside dense vegetation. Over millions of years, as the Andes continued to rise, the waters broke through, carving the path of the modern Amazon River. Yet even now, the forest retains memory of its swampy past in its floodplains and seasonal wetlands. The Amazon is not just a river with a forest around it. It is the product of forests and water shaping one another across deep time. Some forests are shaped by seasonal floods. In places like the Amazon and parts of Southeast Asia, forests flood regularly, sometimes rising by several meters for months at a time. Instead of drowning, the trees adapt. Some species grow hollow stems that allow them to breathe even underwater. Others develop roots designed to withstand long submersion. These flooded forests become seasonal havens for fish and aquatic animals, turning the landscape into a shifting blend of river and woodland. When waters recede, nutrients are left behind, fueling bursts of growth. To live here is to accept constant change, a rhythm of flood and drought, where the forest itself becomes amphibious. These ecosystems reveal how flexible life can be, thriving in cycles that might seem impossible to endure. Forests once covered nearly the entire Earth. Hundreds of millions of years ago, before deserts spread widely and before ice caps formed, forests blanketed almost all of Earth's land surface. Vast swamps of giant ferns and trees dominated the Carboniferous period, creating the coal deposits we mine today. Later, coniferous forests stretched across ancient supercontinents, unbroken for thousands of miles. These global forests played a central role in shaping the planet's atmosphere, producing oxygen levels much higher than today and fueling the rise of giant carl, insects and amphibians. Over time, climate shifts and continental drift fractured these expanses, creating the patchwork of ecosystems we know now. But the memory remains. Once, Earth was almost entirely forest, a green world where trees were the rulers of the land. Forests will outlast most human structures. Cities, monuments, and highways often feel permanent, yet forests quietly remind us of time's true scale. Abandoned buildings are quickly reclaimed by trees, their roots breaking through concrete, vines weaving through windows, branches shading collapsed walls. Even great structures, from temples to fortresses, eventually crumble under the steady patience of growth. Forests move slowly, but their persistence is unmatched. They have outlasted civilizations before, and will likely outlast many of today's creations. Human structures measure permanence in centuries, forests measure it in millennia. When left alone, they return, covering scars and erasing the traces of human presence. In the long story of Earth, forests endure, not as monuments of stone, but as living, ever-renewing worlds. Forests remind us that life is both fragile and fierce. Forests can burn, wither or vanish in a single generation, their fragility revealed in every clear-cut hillside. Yet they can also survive ice ages, storms, and the rise and fall of empires, their resilience stretching across millions of years. This duality makes forests symbols of both vulnerability and strength. A seedling can be crushed underfoot, yet given time, it can grow into a towering giant. Entire forests can be leveled, and yet, decades later, they may return, green and humming with life. To walk among trees is to feel this paradox, that life is delicate, but also indomitable. Forests embody this truth, fragile in the moment, fierce in the long sweep of time. Some trees communicate through underground fungi. Beneath the soil of nearly every forest lies a hidden communication system, threads of fungi linking tree roots in a vast, interconnected web. Scientists call it the wood wide web because it allows trees to share signals and even resources. Through these fungal networks, a shaded sapling might receive nutrients from a larger, healthier neighbor. A tree under attack from insects might send out chemical warnings, prompting others nearby to boost their defenses. Some species appear to act like mother trees, channeling energy into younger seedlings through this hidden network. It's not communication in the human sense, but it is cooperation, carried out molecule by molecule beneath the ground. What looks like a silent forest is actually buzzing with exchanges, not through sound or sight, but through sugars, chemicals, and fungal threads. The forest, it turns out, is far more alive and more connected than it seems. The Amazon may be approaching a point of collapse. For all its vastness, the Amazon is fragile. Scientists warn that it may be nearing a dangerous tipping point. As deforestation spreads and climate change dries the air, the rainforest could begin to shift into a savanna-like ecosystem. This would mean fewer trees, less rainfall, and an irreversible unraveling of the forest's cycles. Already, parts of the Amazon now emit more carbon than they absorb, a stark reversal of its ancient role as a carbon sink. If the forest tips past this threshold, billions of tons of stored carbon could flood into the atmosphere, accelerating global warming. At the same time, countless species would lose their home. The Amazon's collapse would not only reshape South America, but also ripple through the entire planet's climate system. It is a reminder that even the mightiest ecosystems depend on delicate balances that can be pushed too far. Certain trees use chemical signals to shape the behavior of nearby plants. When a tree occupies a territory, it does not simply stand in place. Through its roots and leaves, it releases compounds that drift through soil and air in quiet currents. These substances can slow the germination of certain seeds, encourage the growth of others, or shift the direction of neighboring roots. In some cases, the chemical influence reaches far enough to create distinct patterns across the forest floor. One side of the tree may support thriving undergrowth, while the opposite side remains sparse due to subtle chemical gradients. Smaller plants respond by adjusting how they grow, how quickly they produce leaves, or how far their roots explore. Over many seasons, these invisible boundaries reshape the community around the tree, creating zones of cooperation and zones of competition. The result is an ecosystem that reflects the decisions of its tallest members, The forest becomes a landscape written partly in soil and partly in chemistry. Some trees release scents that influence the moods of animals and people. In the presence of certain trees, the air takes on a quality that feels calming even before the scent becomes noticeable. This comes from natural compounds produced by leaves, bark, and resins that drift into the environment. These compounds interact with the nervous systems of animals that breathe them in, lowering stress levels and encouraging slower heart rhythms. Birds settle more easily in branches exposed to these scents. Mammals behave more calmly in these areas, often choosing to rest or forage near these trees even when food is more abundant elsewhere. Humans experience this effect as well. Studies of forest environments show that time spent near these species can influence mood, reduce tension, and create a sense of mental clarity. These benefits arise not from symbolism, but from the chemistry released into the air. The tree shapes not only the physical structure of the forest, but also the emotional tone of the life within it. A few trees can modify the temperature of their flowers to attract pollinators. During the brief window when pollination must occur, some species raise the internal temperature of their flowers above that of the surrounding air. This warming draws insects and small animals that seek heat during cooler periods of the day. Inside the flower, metabolic processes activate and release energy that flows outward as gentle warmth. Pollinators rest on the petals or dive toward the heat source, gaining comfort while transferring pollen in the process. This strategy also helps the tree release scent molecules more efficiently, spreading them through the air at a faster rate. The flower becomes not only a source of food, but also a temporary refuge. Over generations, this temperature control has helped these species succeed even in regions where cool mornings might limit the activity of insects. The ability to generate warmth at the precise moment it is needed gives the tree a significant advantage in reproduction. Some trees can sense when they are being eaten. The moment an insect bites into a leaf, the plant experiences a physical and chemical signal that differs from harmless environmental wear. Special receptor cells recognize the exact combination of pressure, saliva, and tissue damage. These receptors trigger pathways that activate defensive processes. Within minutes, compounds begin to form in the wounded area, making the leaf less appealing. The tree may also shift resources away from the damaged section and reinforce other parts of the canopy. In some cases, the signal travels through the internal transport system and alerts distant branches that have not yet been touched. Those untouched leaves begin defensive preparations in advance. The entire tree adjusts its internal priorities based on the specific nature of the attack. This sensitivity allows it to react with precision, conserving energy while protecting itself from further harm. The response is rapid for a large organism that usually moves in slow patterns. Trees can rewrite their growth patterns in response to sound and vibration. Although trees do not possess ears, they can detect vibrations in the environment through the movement of their tissues. When certain frequencies pass through the trunk or leaves, the cells react by altering growth direction or adjusting how quickly new tissue forms. Experiments have shown that vibrations from wind, water flow, and even the movement of animals can influence how roots spread through the soil. Some roots become thicker in areas of frequent vibration, anchoring the tree more firmly. Others explore quieter regions where competition for resources may be lower. Branches also respond by shifting angles or reinforcing growth along lines that match the surrounding conditions. Over many seasons, these subtle adjustments accumulate into a pattern that reflects the physical soundtrack of the forest. The tree grows not only in response to light and water, but also to the quiet signals carried through the air and ground. Some trees grow in spirals that follow invisible environmental forces. A spiral growth pattern may appear decorative, yet it often reflects the influence of factors that are not immediately visible. Trees exposed to consistent wind from a particular direction may twist as they grow to distribute stress more evenly through the trunk. Others align themselves with patterns of sunlight or magnetic fields, creating slow rotations that continue year after year. The spiral is not a random flourish. It is a structural adaptation that improves stability, water transport, and resistance to breaking under pressure. Inside the trunk, the arrangement of fibers reflects this twist, forming a complex lattice that responds efficiently to tension. When researchers study these trees, they find that the spiral pattern often matches long-term environmental conditions far more accurately than weather records. The shape of the trunk becomes a map of the forces that shaped it. A few trees can tilt themselves back upright after falling. When storms or shifting soil cause a young tree to lean, the plant does not simply accept its new orientation. Cells on one side of the trunk begin to divide more rapidly than those on the opposite side. This uneven growth creates pressure that slowly pushes the trunk back toward a vertical position. The process may take several seasons, as it continues as long as the living tissues remain active. Roots also respond by extending more vigorously on the side opposite the tilt, creating a counterweight that stabilizes the recovering tree. Over time, the trunk regains its balance, and the canopy reorients itself toward the sky. In older trees, this ability may be less pronounced, but younger individuals can perform remarkable corrections. Some eventually stand straight, even after being pushed nearly to the ground. Some trees generate electricity through tiny internal chemical reactions. Within the tissues of certain species, natural gradients of ions create small electrical currents as part of normal metabolic activity. These currents help power internal transport systems that move nutrients and water from roots to leaves. They also guide the behavior of membranes that separate different types of cells. Although the electrical output is extremely small, it is measurable. Scientists can attach sensors to the bark and record fluctuations that correspond to changes in light, temperature, or soil moisture. These electrical patterns help researchers study tree health and environmental stress. In nature, the currents help regulate growth by coordinating activities across different parts of the tree. The trunk, branches, and roots all rely on this steady internal flow to maintain communication within the organism. While the electrical energy is not used in the way animals use nerve signals, it serves as an essential part of the tree's internal coordination. There are trees that grow bark so strong it can stop small fires. In fire-prone environments, the bark of certain species develops into a thick protective layer that shields the living tissues inside. This bark contains dense materials that resist heat and slow the movement of flames across the trunk. When a low fire sweeps through, the outer bark chars but prevents the heat from reaching the vulnerable inner layers. Inside the trunk, moisture remains stable and the cambium continues functioning. Even after repeated exposure to fire, these trees preserve enough of their vital tissues to regrow leaves and branches. Over time, many individuals accumulate patterns of darkened bark that show how often they have survived fire events. These marks reveal the resilience built into the species, a kind of living archive of environmental challenges that the tree has overcome. Some trees shed bark deliberately to remove parasites. Shedding bark is not always a sign of damage. For some species, it is a controlled process that serves as a defense against organisms that attempt to colonize the outer surface. As the bark loosens, insects, fungi, and lichens that depend on a stable surface lose their attachment and fall away. The new bark that forms beneath is clean and less likely to carry harmful organisms. In warm regions, this shedding also protects the tree from intense sunlight by revealing lighter-colored bark that reflects heat more effectively. The timing of bark loss is precise, occurring only when the new layer is ready to take over. This cycle continues for the entire life of the tree, creating patterns on the trunk that show how often renewal has taken place. The process helps the tree maintain a healthy outer surface while adapting to the challenges of its environment. A few species have bark that peels in rainbow patterns. In certain climates where sunlight, humidity, and rapid growth intersect, some trees renew their outer bark in thin sections that peel away layer by layer. Beneath each removed section lies a fresh surface with pigments that have not yet been exposed to air. These pigments may appear bright green at first, then shift into shades of blue, orange, or red as the surface matures. Over time, the entire trunk becomes a mosaic of colors that change continuously as new bark appears and old bark weathers. This cycle does more than create beauty. By peeling frequently, the tree removes organisms that try to settle on its surface. The exposed bark also regulates moisture more effectively by presenting younger and more flexible tissue to the environment. In regions with intense rainfall, this peeling helps prevent water from trapping harmful microbes against the trunk. The rainbow appearance is a sign of constant renewal, each color marking a moment in the ongoing life of the tree. Some trees grow wood dense enough to sink in water. Across tropical forests, there are species whose wood is so tightly packed with material that it falls when placed in a river or lake. This density comes from extremely slow growth in environments where nutrients favor compact structural tissues over lighter ones. The wood supports incredible weight without bending and withstands impacts that would damage softer species. Inside the trunk, the cells have thick walls that leave very little empty space, giving the tree a strength that rivals certain engineered materials. This density also protects the wood from insects that struggle to chew through it. Builders in some regions have used these trees for tools and structures that must endure constant stress because the wood resists both deformation and decay. These trees grow slowly, but each year adds a layer of remarkable strength that makes the trunk a long-lasting and nearly unbreakable presence in its ecosystem. Certain trees produce wood with natural medicinal properties. Some species store unique compounds inside their heartwood that form as the tree matures. These compounds can discourage fungal growth, repel insects, or preserve the wood long after the tree has fallen. When the wood is cut or scraped, the aroma hints at a complex blend of natural chemicals that the tree once used to defend its inner tissues. These same substances can influence the surrounding environment. Leaves that fall from these trees may alter the soil chemistry in ways that help them resist harmful microbes. People have long noticed that areas near these trees experience slower rates of decay in organic matter or noticeably fewer pests. Scientists studying the wood find that these compounds differ from species to species and often evolve in response to local threats. The tree builds its own pharmacy inside its trunk, turning defense into long-lasting resilience. Some trees make leaves that change shape as they grow older. When young leaves first form, they often appear in shapes that maximize protection from sun exposure or minimize water loss. These juvenile forms may look completely different from the mature leaves on the same tree. As the tree gains height and stability, the shape of its leaves shifts to optimize light capture, airflow, or temperature control. In some species, the transformation helps discourage animals that prefer tender leaf tissue because the mature form becomes tougher or less appealing. In others, the shape change improves the tree's resistance to wind by reducing drag. These transitions occur gradually as each new wave of growth produces slightly altered forms. Over time, the canopy becomes a mixture of shapes that reflect every stage of development. This ability to change leaf design allows the tree to adapt to new challenges at each point in its life. A few trees can fold their leaves in response to touch. Some species possess leaves with specialized cells that change internal pressure when stimulated by movement. A light touch triggers these cells to release water into surrounding tissues, causing the leaf to collapse inward or fold along a central line. This reaction is rapid compared to typical plant movements and protects the leaf from insects, rain impact, or strong gusts of wind. The process does not require any sound-based perception. It relies entirely on mechanical changes sensed within the leaf. Once the disturbance ends, the cells restore their pressure, and the leaf slowly returns to its original position. The ability to fold protects the plant from physical harm and also discourages herbivores that prefer stationary surfaces. Each fold is a moment of quick defense, a brief retreat that allows the leaf to preserve its delicate structure. Some trees create natural insect traps with sticky surfaces. A few species produce leaves or branches coated with a thin layer of adhesive fluid. This substance forms as part of the tree's normal defense system and creates surfaces that can trap small insects before they reach vital tissues. When insects land or crawl across the sticky area, they become immobilized and cannot continue feeding. Over time, the trapped insects decompose and add minute nutrient traces to the surface of the tree. While these trees are not considered carnivorous, the presence of these sticky layers shapes the behavior of insect populations around them. Fewer pests reach the inner leaves. Birds and other animals often take advantage of the trapped insects as an easy food source, forming a small ecological relationship based on the adhesive graph. Coating. The tree gains protection through a passive method that requires no movement or energy once the coating is produced. Certain trees can grow leaves that mimic the plants around them. In environments where standing out would attract herbivores, some trees have evolved leaves that resemble those of surrounding species. This resemblance includes shape, texture, and sometimes even color. The tree accomplishes this through subtle genetic adjustments that activate when the plant senses the chemical presence of nearby vegetation. The developing leaves adopt features associated with other plants, allowing the tree to blend into the background. Herbivores searching by sight or by familiarity overlook the disguised leaves and move on. This ability to mimic creates a form of camouflage that changes depending on which species occupy the surrounding area. In regions where plant communities shift regularly, the tree may adjust its leaf morphology with each new season. The result is a plant that alters its appearance in response to the broader environment. Some trees have leaves that track the movement of the sun. Throughout the day, certain species rotate their leaves to follow the path of sunlight across the sky. Small cells at the base of each leaf change shape as internal pressure shifts in response to light intensity. This movement positions the leaf so that it captures the maximum amount of energy at each moment. When evening arrives, the leaves often return to a neutral orientation to reduce water loss overnight. This tracking behavior improves the efficiency of photosynthesis and allows the tree to thrive even in regions where cloud cover or tall neighbors limit available light. The movement is subtle, yet over the course of a day, the leaves may sweep across a wide arc. The tree benefits by adjusting continuously to the changing sky, rather than relying on a fixed position. A few species produce flowers that bloom only once in many years. Some trees accumulate resources for long periods before committing to a single massive flowering event. During these waiting years, the tree strengthens its root system, expands its canopy, and stores energy within its trunk. When conditions finally align, the tree releases an extraordinary burst of flowers within a short window of time. The event attracts pollinators from far distances as the scent and color of the blooms fill the surrounding environment. After the flowering is complete, many of these species focus entirely on fruit production. The fruits often mature quickly and carry seeds that spread across large areas. This strategy ensures that the next generation begins life under ideal circumstances. The long build-up to a single flowering event allows the tree to maximize its reproductive success even in unpredictable climates. Some trees can switch between male and female flowering. In certain species, the form of the flowers produced by a tree changes depending on environmental conditions, internal energy levels, or population needs. A tree may produce male flowers during seasons when resources are limited because creating pollen requires less energy. During years with abundant sunlight and water, the same tree may produce female flowers that are more costly to develop. This flexibility allows the species to maintain stable reproduction across varying conditions. It also helps balance the ratio of male and female flowers within a population, without requiring separate individuals. Over time, the switching pattern contributes to a resilient reproductive system that adapts to long-term changes in climate or habitat structure. The ability to shift roles within the same organism reveals a level of plasticity rarely seen in large plants. Certain trees change sex depending on environmental conditions. In these remarkable species, the type of flower produced depends on signals the tree gathers from the world around it. When sunlight weakens or nutrients run low, the tree shifts toward the less demanding reproductive form, conserving energy while still participating in pollination. When water is plentiful and the canopy receives strong light, the tree redirects its strength into producing flowers that will carry seeds into the next generation. This ability gives the species a flexible strategy that prevents entire populations from failing during harsh years. Even neighboring individuals may adopt different reproductive roles depending on slight differences in soil quality or shade. Over many seasons, this shifting behavior creates a natural balance within the forest, allowing reproduction to remain stable even as conditions rise and fall. The tree does not commit to a single role. Instead, it responds intelligently to the changing landscape. Some trees use ultraviolet patterns on their flowers to guide pollinators. These floral patterns appear simple to human eyes, yet under ultraviolet light, they reveal detailed markings that stand out boldly to insects. The designs function like signs that point directly toward pollen and nectar, helping pollinators land accurately and feed efficiently. Bees and other visitors use these cues to distinguish one species from another, even when many flowers bloom in the same area. The patterns can form rings, centered highlights, or radiating streaks that match the habits of the animals that visit them most often. By providing clear guidance, the tree increases its chance of successful pollination and reduces the energy wasted on visitors that might otherwise wander across the petals without transferring pollen. These ultraviolet features evolve gradually as trees and pollinators influence one another across countless generations. The result is a partnership built on signals that humans can only see with special equipment. A few trees produce fruits that rely on only one animal species to disperse them. In these highly specialized relationships, the tree shapes its fruit to match the feeding style, digestive process, and movement patterns of a single animal. The fruit may be tough enough to withstand chewing, but soft enough to release seeds, only after passing through a particular digestive system. Sometimes the scent, taste, and even timing of ripening match the habits of that one creature. When the animal travels through the forest, the seeds are carried within its body and deposited far from the parent tree, often in locations rich with nutrients. This exclusive partnership creates a powerful but fragile bond. The tree depends completely on the animal to spread its offspring, and the animal in turn benefits from the reliable food source. Over long periods of evolution, both partners become tightly linked, forming a connection that shapes the structure of entire ecosystems. Some trees create fruits with chemical signals that tell animals when they are ripe. As the fruit matures, it releases a changing blend of scents that drift outward into the forest. Animals capable of detecting these chemical shifts use them as reliable cues that the fruit has reached peak nutrition. Long before the color fully deepens or the skin softens, the scent announces that the seeds inside are ready to be carried away. This timing matters because the seeds must be eaten exactly when they are developed enough to survive digestion. If the fruit is taken too early, the seeds may be damaged. If it falls too late, the opportunity for dispersal decreases. By coordinating chemical signals with internal development, the tree ensures that animals arrive at the perfect moment. The forest responds in predictable waves as scent-sensitive creatures gather, feast, and move outward with the next generation hidden within them. Certain tree fruits can lie dormant for years before sprouting. These fruits contain seeds protected by thick outer layers that resist moisture and breakdown. The tree produces this barrier to prevent the seed from germinating during unfavorable seasons. The soil around them may dry, flood, freeze, or shift repeatedly, yet the seed waits patiently for the combination of warmth, moisture, and microbial activity that signals a safe beginning. During this long rest, the seed remains aware of subtle changes in its environment through chemical shifts that pass through the outer coating. Once the surrounding soil reaches a stable condition, enzymes awaken and soften the protective shell. The seed then begins to absorb water and extend its first root, anchoring itself in ground that has finally become welcoming. This dormancy strategy protects the species across unpredictable climates, ensuring survival even when many years pass before the right moment arrives. Some trees rely on fire to trigger the release of their seeds. In fire-adapted landscapes, these trees bear cones or pods that remain tightly sealed under cool conditions. The structures contain resins or natural glues that soften only when exposed to the intense heat of a passing blaze. When flames sweep through and remove competing vegetation, the cones open and drop seeds onto nutrient-rich ash. This creates ideal conditions for rapid growth, as sunlight now reaches the soil unobstructed and minerals become more available. The seeds germinate quickly in this newly cleared space, taking advantage of reduced competition. This strategy allows the species to flourish in regions where fire is not a destructive force, but a recurring event that shapes the rhythm of the ecosystem. Instead of fearing fire, these trees use it as an essential part of their life cycle. A few trees use explosive mechanisms to launch their seeds great distances. These trees develop pods that dry unevenly, creating tension within the plant tissue. As moisture escapes, the outer walls bend and twist until the built-up strain reaches a breaking point. When the pod finally splits, the sudden release sends seeds flying outward with remarkable speed. Some land nearby, while others travel far enough to escape the shadow of the parent tree entirely. This launching method spreads offspring across many types of terrain, increasing the chances that at least some seedlings will take root in favorable soil. The explosive energy does not require any animal or wind assistance, making it an independent and reliable dispersal method. Over time, entire groves can form from one well-placed burst that sends seeds into hidden corners of the landscape. Some trees make seeds that ride air currents for astonishing lengths of time. These seeds develop wings, fibers, or papery structures that transform them into natural gliders. As they detach from the tree, they begin to spin or drift, catching even the gentlest currents with ease. The lightweight design allows them to rise above leaf litter, clear the canopy, and travel across open spaces. Some drift for hours before settling. During their journey, the seeds encounter a variety of microclimates, from cool, shaded valleys to bright, open ridges. This wide exploration increases the likelihood that they will land in soil suited to their needs. Evolution shapes every contour of these airborne structures, refining them so they remain stable in unpredictable winds. The tree benefits by spreading its offspring far beyond what gravity alone would permit. Certain trees form seeds that can survive long journeys across oceans. These coastal species produce buoyant seeds with thick, watertight shells that protect the inner embryo from salt and decay. Once released, the seeds enter rivers, tidal pools, or shoreline waves and drift outward into open water. Ocean currents carry them across great distances, sometimes depositing them on distant islands or shorelines weeks or months later. During their voyage, the seeds remain viable because their protective coating keeps the interior dry and insulated. When they finally reach land, fresh water softens the shell and triggers the first stages of germination. This dispersal method allows the species to colonize new regions, cross natural barriers, and maintain genetic diversity across widely separated landscapes entire coastal forests have grown from seeds that once floated through vast stretches of open sea. Some trees produce sap that hardens into natural fossils over centuries. When these trees experience wounds or stress, they release resin that captures small particles from the surrounding environment. As time passes, the resin thickens, hardens, and becomes buried within sediment or soil. Pressure and chemical changes gradually transform it into a durable substance that can preserve insects, plant fragments, and tiny traces of ancient, ecosystems. These natural fossils remain stable for tremendous spans of time, offering scientists rare glimpses into forests that existed long before modern species developed. The hardened material protects delicate structures that would otherwise decay, creating clear snapshots of life as it once appeared. Through this slow process, the tree becomes an unwitting archivist, recording the fine details of its world in a material capable of surviving far beyond the lifespan of the organism itself. A few trees create resins that preserve insects perfectly. When the bark of these trees breaks open, the protective resin seeps outward in slow, shining beads that cling to everything they touch. Small insects wandering across the wound become caught instantly, held in place by a substance that grips each tiny limb and hair. What would normally decay within hours becomes sealed away from air and moisture. Over time, the resin grows harder and more transparent, wrapping the insect in a flawless shell that protects even the most delicate structures. Wing veins, fragile eyes, pollen grains, and mouthparts remain intact as the resin ages. Long after storms, seasons, and entire generations of animals pass, the preserved creature stays suspended in perfect clarity. These preserved moments allow scientists to study tiny species that might otherwise vanish entirely from the record. The tree does not set out to capture the insect. Its only goal is to seal a wound. Yet in performing this simple act of protection, it becomes a guardian of ancient detail, offering glimpses into life that once clung to its bark. Some tree saps can flow upward against gravity in surprising ways. Inside these trees, narrow tubes form continuous corridors from roots to the highest twigs, allowing sap to travel without any mechanical pump. The movement begins when sunlight warms the leaves and water evaporates through tiny pores, pulling on the entire column of liquid below. The bond between water molecules keeps the column intact even as it climbs stunning heights. When evening cools the canopy and evaporation slows, pressure deep within the roots pushes fresh sap upward, restoring what was lost during the day. This upward movement delivers minerals from the soil to every living cell, while carrying chemical signals that coordinate growth across branches and buds. The process remains invisible to anyone standing beneath the tree, yet it powers the expansion of leaves, the healing of bark, and the rise of blossoms each season. It is one of the most elegant forms of natural engineering, fueled only by sunlight, structure, and the subtle physics of water. There are trees whose sap glows faintly in the dark. In rare forests, a cut branch or scraped patch of bark may reveal a soft radiance that unfolds as daylight fades. This glow forms when natural chemicals in the sap react with oxygen, or when tiny organisms living within the fluid produce light as part of their metabolism. The result is a gentle shimmer that clings to the wound like a ghostly veil. It is never bright enough to illuminate the forest floor, yet it becomes visible in the quiet hours of true darkness. Insects sometimes gather near the glow, drawn by its faint presence or avoiding it altogether, depending on how they interpret the signal. Researchers study these glowing patches to understand the chemistry hidden within the sap and the microscopic partners living inside it. The light requires just the right balance of moisture, temperature, and biological activity, which makes each luminous spot a rare and fascinating gray. Collaboration between tree, air, and life too small to see. Some trees produce aromatic compounds that linger in the air for hours. As sunlight warms their leaves and bark, these trees release a complex blend of airborne oils that drift outward and saturate the forest with scent. The fragrance may travel far beyond the canopy, shaping the movement of insects, birds, and mammals. Pollinating species often follow these airborne trails to hidden flowers, guided by a mixture of sweet, sharp, or resinous notes. Herbivores may avoid trees whose aromas signal strong chemical defenses. Even the soil community responds, as falling leaves carry these compounds into the ground, where they influence microbial activity. For humans walking beneath the branches, the scent feels calming or invigorating, yet each note is part of a larger chemical conversation that evolved long before people appeared. The lingering aromatic cloud continues through still air long after sunset, quietly influencing the choices of countless creatures passing through the forest. Certain trees can change the chemical makeup of their sap after injury. When bark splits or insects chew through delicate tissues, the tree rapidly alters the mixture flowing through its vessels. Defensive compounds rise in concentration near the wound, forming a chemical barrier that slows the progress of microbes and deters further feeding. Some substances thicken to seal damaged channels, while others break down invading organisms before they can reach deeper tissues. These changes radiate outward, alerting nearby cells and shifting the tree's internal priorities so that repair takes precedence over growth. Once the wound stabilizes and new tissue begins forming, the sap gradually returns to its normal balance. The transformation happens quietly, yet reveals a responsive intelligence in the way the tree protects itself. Rather than relying on a single defense, it reshapes its internal chemistry to match the challenge in front of it. Some trees host microscopic life that depends entirely on their sap. Within the flowing liquid that carries nutrients upward, entire communities of bacteria and yeasts find a complete and sheltered home. These tiny organisms drift along the SAPS path, gathering in places where conditions are warm, stable, and rich with dissolved sugars. Many of them contribute positively to the tree by breaking down waste materials or producing compounds that enhance growth and defense. Others create subtle shifts in the chemistry of the sap, helping the tree respond to stress or changes in weather. The tree's immune system keeps these populations balanced, allowing helpful organisms to thrive while keeping harmful ones under control. Over long periods, the microorganisms adapt so closely to their host that they cannot survive outside the tree's vessels. Their entire existence unfolds within narrow channels of moving liquid, experiencing day and night through changes in pressure and temperature alone. A few trees can create habitats inside hollowed trunks without dying. As certain trees age, the dense heartwood near the center of the trunk begins to break down naturally, leaving behind a hollow core. The living portion of the tree remains just beneath the bark, forming a ring of active tissue that continues to transport water and nutrients. This allows the tree to stand tall, even while the interior becomes an open space large enough to shelter animals. Birds, small mammals, reptiles, and insects all find refuge inside the protected darkness, especially during storms or extreme heat. Moisture collects on the inner walls, encouraging mosses and fungi that create additional layers of habitat. The tree adapts by reinforcing the outer wood, strengthening it to compensate for the missing center. These hollow dwellings can persist for decades, turning the tree into both a thriving organism and a living shelter for entire communities. Some trees naturally shape themselves into perfect homes for animals. Without any outside help, certain species grow limbs, curves, and chambers that line up exactly with the needs of forest wildlife. Broad branches create resting platforms for birds. Gently cupped intersections between limbs become ideal nesting places that remain dry even during heavy rain. Twisted roots form sheltered spaces where small mammals hide from predators. These shapes emerge simply because the tree follows patterns of light and gravity, yet the resulting architecture serves countless creatures. As animals reuse these features year after year, the tree becomes a familiar landmark in their territories. Birdsong, scent marks, and nesting materials all gather around it, weaving the tree into the daily lives of the forest. What appears to be an accidental arrangement of wood becomes, through use and repetition, a vital structure in the broader living network. Certain trees grow hollows that become entire ecosystems of their own. Where cavities form in trunks or large branches, rainwater, drifting seeds, fallen leaves, and fine soil gradually accumulate. Over time, the hollow transforms into a miniature forest environment, with damp air, soft ground, and filtered light. Insects burrow into the decaying material, creating tunnels and chambers. Frogs and small reptiles slip into the puddles that form after storms. Fungi trace delicate threads through the softened wood, breaking it down into rich organic matter. Sometimes even small plants take root inside these elevated pockets, creating tiny gardens held aloft by the tree's living structure. As long as the outer trunk remains strong, the entire system thrives independently from the forest floor, complete with its own cycles of growth, decomposition, and renewal. Some trees can sense and respond to the weight of animals climbing them. Branches that experience repeated pressure gradually adjust their internal structure to handle the load. Cells on the underside of a bending limb grow thicker, strengthening the wood where stress is greatest. Upper layers may stretch and adapt, ensuring the branch remains flexible without snapping. Over many seasons, well-traveled routes become noticeably sturdier than unused ones, forming natural pathways through the canopy that support regular visitors. In younger trees, sudden heavy weight may tilt the trunk, triggering slow but steady growth corrections that guide the tree back toward balance. Even leaf arrangement can shift around busy branches, spacing out surfaces so they avoid tearing when animals move past. These long-term changes reveal that the tree is constantly listening to its physical world, interpreting pressure as information and translating it into enduring structural decisions. A few trees form symbiotic partnerships with birds that protect their branches. When certain birds choose a tree as their long-term refuge, the relationship grows into something far deeper than simple shelter. Nest building, feeding, and resting all take place among the branches, and the constant presence of wings and calls creates a protective zone that deters many threats. Insects that would chew through new leaves are eaten before they can become a problem. Browsing animals avoid trees filled with vigilant eyes that sound alarms at the slightest hint of movement. Over time, the birds learn every curve and hollow of the canopy, reacting instantly to anything unusual. Their droppings enrich the soil around the roots, feeding microorganisms that support the tree's growth. The tree responds by offering sturdy limbs, seasonal food sources, and safe vantage points that make it worth returning year after year. In forests where storms and predators constantly reshape the balance of life, these partnerships act like small alliances of survival, each partner amplifying the strengths of the other. Some trees rely on bats for pollination and seed dispersal. As daylight fades and the canopy darkens, certain trees begin releasing scents that travel easily through cool evening air. These fragrances bloom when the rest of the forest quiets, guiding hungry bats toward flowers that open only at night. When the visitors feed, their fur gathers pollen grains that adhere gently to the fine hairs along their bodies. Their swift flight carries this pollen across long stretches of forest, allowing the tree to exchange genetic material far beyond the limits of daytime. Pollinators. Later in the season, when fruits ripen with a richness designed for nocturnal tastes, bats feed again and carry seeds within their digestive tracts. They release those seeds in places the tree could never reach on its own, often near water, in sheltered rock crevices, or along the edges of new clearings. This long-distance partnership shapes entire landscapes, pushing new growth into untouched soil and ensuring the continuity of species that depend on the night for their survival. Certain trees depend on fish to spread their seeds along flooded rivers. During seasonal flooding, rising waters carry fruits from these trees into gentle currents that drift through submerged forests. Fish, attracted to the scent or texture of the floating fruits, bite into them, swallowing the soft pulp and unknowingly taking on the role of seed bearers. As they travel through winding channels and deep pools, they release undamaged seeds that settle in fresh layers of silt. These deposits are rich with nutrients left behind by retreating floodwaters, making them ideal nurseries for young seedlings. The trees do not rely on wind or birds for their spread. Instead, they harness the movement of river life, trusting that fish will transport their future generations to new and fertile ground. Over many cycles, this partnership carves out long corridors of vegetation that follow the river's paths. Entire floodplain forests owe their structure to this quiet cooperation between moving water, swimming creatures, and trees that learn to let the river carry their détiter. Future. Some trees have roots that grow above water to breathe air. In wetlands, where soils remain soaked for long periods, the ground becomes starved of oxygen, making ordinary roots struggle to function. To survive, certain trees send parts of their root systems upward, lifting them into the open air where gases can flow freely. These specialized structures act almost like living chimneys, drawing oxygen down into the submerged tissues that need it most. The raised roots often form intricate shapes, rising in clusters or arching above the water's surface. Their presence changes the entire ecosystem around them by creating shelter for aquatic animals and stabilizing soft mud that would otherwise shift with every current. Even in storms, the exposed roots remain strong, absorbing shock while continuing to exchange gases. This adaptation allows the trees to thrive where others cannot, turning swamps and marshes into vibrant forests filled with unique species that depend on the breathing roots for both structure and shelter. A few trees build massive root networks that anchor coastlines. Along the edges of continents and islands, certain trees expand their roots outward in sprawling tangles that hold soil in place against the pull of tides and storms. These roots branch repeatedly, forming barriers that trap drifting sand and sediment. As the network grows denser, entire stretches of shoreline become more stable, resisting erosion that would otherwise wash away habitat for countless organisms. Fish spawn among the underwater roots, birds nest above them, and crustaceans burrow into the newly anchored ground. When strong winds drive waves toward the coast, the roots distribute the force through their vast web, protecting inland regions from damage. Over many generations, these trees can build out into shallow water, creating new land inch by inch as their roots accumulate more sediment. The coastline evolves with them, shaped by a living structure that remains flexible yet strong enough to withstand some of the harshest conditions on Earth. Some trees purify water by filtering minerals through their roots. As water travels through the soil and into the root system, these trees draw it through a series of membranes that capture excess minerals, metals, and natural compounds. This filtration process protects the tree from harmful concentrations, but it also transforms the surrounding environment. Cleaned water releases back into nearby streams, ponds, or groundwater, supporting healthier conditions for fish, amphibians, and plants. Soil around the roots becomes more stable and balanced, creating pockets of life where delicate species can take hold. When heavy rains wash debris and nutrients into the ground, the tree moderates the flow, preventing sudden changes that would disrupt the ecosystem. Over time, entire landscapes benefit from these filtering roots. They create natural purification systems that improve clarity in waterways, reduce harmful buildup in wetlands, and support thriving communities of organisms that depend on stable, healthy water to survive. Certain trees stabilize mountainsides and shape entire landscapes. On steep slopes where erosion threatens to drag soil downward with every heavy rain, these trees send deep roots into fractures and crevices, binding loose earth into a cohesive mass. Their roots weave through layers of rock and gravel, forming nets that hold everything in place. When storms arrive, the canopy intercepts much of the rainfall, slowing its descent and giving the soil time to absorb moisture without collapsing. Over decades, this stabilizing effect allows delicate understory plants to establish themselves in places that would otherwise crumble away. Streams that flow down the mountain run clearer because less sediment is washed into them. Animals use the anchored ground to travel safely across steep terrain. Entire valleys owe their shape to these quiet architects. Without them, mountainsides would slide more often, and ecosystems below would struggle to survive under the weight of continuous landslides. Some trees can grow on bare rock by slowly creating soil beneath them. Seeds that land on stone ledges or cliffsides often fail, yet these particular species have evolved roots that can wedge into the smallest cracks. As the roots thicken, they pry apart the rock grain by grain, opening new space. Fallen leaves gather around the base of the young tree and gradually break down into organic matter. Rainwater pools in tiny depressions, carrying dust and minerals that accumulate around the roots. Over many seasons, a thin layer of soil begins to form. The tree anchors itself more firmly and expands its root system deeper into the widening cavities. Eventually, the once barren rock surface becomes a miniature ecosystem, complete with mosses, insects, and young seedlings that benefit from the first pioneer. Entire cliffside forests can trace their origin to a single tree that managed to grip stone and slowly transform it into living ground. A few trees thrive in environments colder than freezing for most of the year. In regions where winter dominates the calendar, these trees carry a suite of adaptations that prevent their cells from rupturing when temperatures plunge. The water within their tissues becomes infused with natural compounds that lower its freezing point, allowing the cells to remain flexible even in extreme cold. Needles or leaves shrink and harden, reducing surface area so the tree loses less moisture to icy winds. Bark thickens into layered insulation that shields the delicate inner tissues from harsh weather. When snow piles around the base, it forms an additional blanket that protects the roots. Despite the long, dark seasons, these trees continue slow internal processes that prepare them for the brief burst of summer growth. They stand as living markers of resilience, shaping ecosystems where few other large plants can survive, and offering shelter and stability to the animals that share their probate. Frozen world. Some trees survive extreme heat by cooling themselves from within. In scorching environments where air temperatures soar, these trees use their internal water reserves to control their own temperature. Tiny pores on the leaves release vapor in controlled patterns, creating a natural cooling effect similar to sweating. This evaporative release draws heat away from the leaf surface and allows the tree to continue photosynthesis even when the surrounding air grows dangerously hot. Deep roots tap into underground water sources that remain cool and shielded from the sun. The tree channels this moisture upward, creating a gentle internal circulation that buffers the entire structure from overheating. Thick bark reflects sunlight, and leaves may orient themselves to minimize direct exposure during the harshest hours. With these strategies working together, the tree remains stable in conditions that would wither most plants. It becomes a source of shade, moisture, and life in a landscape ruled by heat. Certain trees can withstand storms strong enough to bend their trunks permanently. When fierce winds tear through a forest, some trees respond not by breaking, but by yielding in slow arcs that redistribute the stress across their entire structure. Their wood contains flexible fibers that compress on one side and stretch on the other, allowing the trunk to lean without snapping. As the storm settles, the tree does not immediately spring back. Instead, it evaluates the new forces acting on its shape. Growth tissues adjust cell by cell, adding support where the curve is greatest and reinforcing weakened areas. Over seasons, the leaning trunk becomes a stable new form shaped by memory of the storm that bent it. Branches shift their angles to regain balance, sending leaves toward the sun in graceful sweeps that compensate for the altered posture. Forests filled with such survivors often carry silent histories in their silhouettes, each curve a record of past tempests that reshaped the canopy while leaving life intact. Some trees grew thicker bark when they anticipate future fires. Signals from dry soil, intense sunlight, and rising temperatures can trigger internal changes that lead to a gradual strengthening of the outer bark. Layers accumulate more rapidly, creating a protective shield that insulates the living tissue beneath. This thick covering slows the advance of heat, allowing the tree to remain alive even when flames sweep across the forest floor. In some species, the bark cracks into wide plates that deflect heat upward rather than letting it penetrate deeply. As the lower layers shield the trunk, dormant buds hidden beneath the bark remain protected, ready to sprout fresh growth once the danger passes. Animals sheltering around the base rely on these resilient trunks as safe zones during fast-moving fires. Entire ecosystems shaped by frequent burns depend on these bark fortresses, which preserve old trees long enough to guide new generations after each blaze. A few trees increase their root strength in response to heavy winds. When strong gusts tug repeatedly at the trunk, sensors in the wood and roots detect shifting pressure. The tree responds by thickening underground supports and expanding the fine network that grips the surrounding soil. Roots begin to coil around stones, anchor deeper into compacted layers, and widen their base of support. Even the chemical composition of the roots may change, forming tougher tissues that resist tearing. Above ground, the trunk grows wood that resists twisting, while branches adjust their angles to reduce leverage during future storms. Over many seasons of wind exposure, the tree becomes increasingly anchored, turning into a steadfast presence even in open or exposed landscapes. Birds and small animals often choose these wind-hardened trees as nesting sites, sensing the stability they provide. What began as a threat becomes a signal the tree uses to refine its strength. Some trees develop resistance to pests within a single generation. When insects feed aggressively on young leaves or burrow through bark, the tree begins producing new defensive chemicals designed to disrupt the attackers. These substances may make the leaves less nutritious, impair digestion, or deter feeding through powerful aromas. Remarkably, the tree can pass this heightened readiness to its seeds, giving the next generation a head start in environments where certain pests are common. This means seedlings begin life already possessing the improved defenses that their parent developed under stress. Over time, forests shaped by recurring insect pressure become mosaics of trees that have each learned from previous assaults. The dynamic relationship between plant and pest becomes an ongoing conversation, with each new generation of trees adjusting its chemistry based on the airs, challenges its ancestors endured. Certain trees evolve new leaf chemistry within local populations. Across a wide forest, trees of the same species may experience very different conditions. Some grow in dry ridges, others in moist valleys, others in bright clearings. These variations influence which chemical compounds become most useful for survival. Over time, populations in each microenvironment adjust their leaf chemistry to meet their unique challenges. Trees in dry areas may produce compounds that retain moisture or reflect more sunlight. Trees in shady zones may shift toward pigments that capture faint light more efficiently. These changes can become so distinct that two groups of the same species living only a short distance apart develop clearly different chemical profiles. Insects and animals respond to these differences as well, forming localized relationships based on the specific chemistry they encounter. Each cluster of trees becomes a small experiment in adaptation, shaped by the subtle differences of its surroundings. Some tree species can hybridize to create entirely new forms. When compatible species grow near one another, their pollen may mix on the wind or through visiting pollinators. If the resulting seeds take root, they can develop into individuals that blend traits from both parents. These hybrids may grow with surprising vigor, combining the resilience of one species with the growth habits of another. Some inherit tolerance for cold from one parent and rapid leaf production from the other, allowing them to thrive in new environments. Over time, these hybrids may form stable populations and even diverge further from their ancestors. Forests with many closely related species often become rich laboratories of natural experimentation. Hybrid trees introduce fresh genetic combinations that reshape everything from canopy structure to flowering patterns. The forest becomes a shifting tapestry woven from both ancient lineages and newly emerging forms. A few trees carry genetic memories of past environmental events. Deep within the DNA of certain species lie instructions shaped by storms, droughts, and disease outbreaks that occurred long before the current generation stood tall. These genetic memories guide how the tree responds to stress. If ancestors endured prolonged dryness, descendants may sprout leaves that conserve water more effectively. If ancient fires swept through the region, seedlings may develop thicker bark sooner in life. These inherited traits allow the species to anticipate challenges even when conditions cycle unpredictably. The tree does not remember in a conscious sense. Instead, the memory is encoded in patterns of growth, chemical production, and timing. Forests filled with such lineages carry the accumulated wisdom of centuries, responding to each season not as isolated individuals, but as heirs. Long histories of survival. Some trees can store more carbon than entire fields of vegetation. Massive trunks, deep roots, and dense wood allow certain species to hold extraordinary amounts of carbon within their bodies. Each year, as leaves pull carbon dioxide from the air, the trees convert it into long-lasting structures that remain stable for decades or even centuries. While smaller plants also store carbon, the sheer size and longevity of these trees give them unmatched capacity. Their roots extend far into the soil, adding organic matter that becomes buried and preserved. When forests of these giants grow together, they create immense reservoirs that slow the accumulation of carbon in the atmosphere. Animals, fungi, and microorganisms all rely on the stability these trees bring to the ecosystem. Yet the climate benefit they provide reaches far beyond their immediate surroundings. Certain forests of trees regulate regional climates. When vast stands of trees release moisture through their leaves, they add humidity to the air that rises and forms clouds. These clouds influence where rain falls and how storms move across a landscape. Canopies also moderate temperature by shading the ground and cooling the air beneath them. Wind patterns shift as air flows around and through the forest, creating localized breezes that guide weather across valleys and plains. Over long periods, forests help determine the timing of seasonal rains and the stability of regional climates. The presence or absence of such tree communities can alter entire weather systems, affecting everything from river flow to agricultural cycles. These living landscapes operate like enormous natural engines that balance heat, water, and air without any deliberate intention, simply through the collective behavior of countless trees acting together. Some trees act as natural air purifiers that remove pollutants. Leaves coated with microscopic pores draw in air and absorb harmful compounds that accumulate in developed or densely populated regions. Volatile chemicals become trapped in waxy leaf surfaces, while other pollutants dissolve in moisture that forms along the leaf edges. Inside the tissues, enzymes break down many of these substances into harmless components that the tree can either store safely or release in altered forms that no longer pose a threat. Root systems also play a role, filtering contaminants that move through soil water. Forests of these trees create zones of cleaner air that benefit both wildlife and people. The purification happens quietly and continuously as part of the tree's normal breathing and nutrient cycling. With every breeze that passes through the canopy, the air grows clearer, refreshed by the silent labor of leaves and roots. A few trees release compounds that create clouds under certain conditions. In warm sunlight, certain forests breathe out vapors rich with natural chemicals that rise into the air and bind with tiny particles drifting above the canopy. As these vapors accumulate, they create clusters of microscopic droplets that seed the formation of clouds. The process begins invisibly, long before any visible shape appears in the sky. Step by step, moisture gathers around these airborne compounds until faint white veils begin to form high overhead. These clouds help cool the landscape by reflecting sunlight and encouraging rainfall that feeds the forest below. What appears to be ordinary weather is in part shaped by the continuous outbreath of these trees, which alter the atmosphere simply by living. Entire regions can experience more stable patterns of rain because of these subtle exchanges between leaf and sky. The trees do not aim to influence the heavens, yet their chemistry becomes a quiet engine that helps regulate the rhythm of clouds and light. Some tree forests influence the global movement of weather systems. Large stretches of forest release moisture through their leaves that rises, cools, and joins distant air currents. As this moisture travels, it adds weight and humidity to winds that eventually carry it across continents and oceans. In some regions, these forests act as anchors for storm paths, shaping where rain falls and how often drought occurs. The canopy slows the heating of the ground during the day and releases stored warmth at night, creating gentle differences in temperature but guide the direction of winds. Over long periods, these influences merge with larger atmospheric cycles. The forests become part of a global dialogue unfolding in the sky, affecting rainfall patterns far beyond their borders. Communities living thousands of miles away may feel the effects of a forest they have never seen. Through the arrival of timely rains or sudden shifts in seasonal storms, each grove becomes a participant in a planetary system that depends on countless interactions between land and air. Certain trees shape the migration patterns of animals over long distances. Some species produce fruits, scents, or flowering cycles that align perfectly with the routes of migratory animals. These trees become dependable markers along the journeys of birds, mammals, and even insects that return year after year. When leaves flush with nutrients or flowers open in abundance, travelers find food and rest just when they need it most. In turn, the animals disperse seeds or carry pollen to distant regions. Entire migratory maps have formed around these botanical cues. Birds may change flight paths in anticipation of certain blossoms, while large mammals follow valley forests that provide consistent forage during seasonal travel. Even aquatic life responds when riverside trees drop fruits or seeds that float across water. The forest becomes a living corridor that guides movement across mountains, plains, and coastlines. Without these dependable botanical signals, many journeys would falter, and entire chains of migration would lose the rhythm that sustains them. Some trees rely on ancient relationships with insects that still persist today. Long before human history began, certain trees formed partnerships with insects that evolved alongside them. These insects learned the timing of flowering cycles, the chemistry of leaves, and the contours of bark where they shelter. In exchange, the trees received pollination, protection, or nutrient exchange from their tiny partners. Even now, these relationships continue unchanged, despite countless shifts in climate and geography. When blossoms open, the insects respond instantly, as if guided by memory passed through generations. Some species know exactly how to drill into a flower to release pollen, while others defend the tree from leaf eaters or invading larvae. the entire interaction unfolds with precision that comes only from long shared history. Each participant carries instincts carved by ages of mutual reliance. The forest becomes home to living relics of an ancient world, still performing roles that began long before the present landscape took shape. A few trees grow alongside fungi that cannot live without them. Beneath the forest floor, these trees form intimate partnerships with fungi that weave through the soil in delicate, branching threads. The fungi wrap around or slip inside the tiniest root tips, drawing energy from the sugars the tree creates. In return, they deliver water and minerals gathered from far-reaching networks that extend beyond the tree's own roots. For the fungi, this arrangement is essential to survival. Without the tree's nourishment, they cannot sustain their sprawling underground systems. Yet the exchange benefits both sides. The fungi help the tree reach nutrients in poor soils, defend against harmful microorganisms, and adapt to shifting moisture levels. Together, they form a single functioning unit that extends beneath vast areas of woodland. Every step on the forest floor presses lightly upon this hidden partnership, a living architecture that connects tree to soil in ways that shape the entire ecosystem. Some trees develop long-term alliances with bacteria that help them grow. Inside their roots live clusters of bacteria that transform elements in the soil into forms the tree can readily use. These microscopic partners take gases from the surrounding earth and convert them into nutrients that feed the growing tree. In return, the bacteria receive steady shelter and a supply of carbohydrates. Over time, the relationship grows so fine-tuned that without these bacterial allies, the tree would fail to thrive even in ideal conditions. These bacteria inhabit specialized nodules or pockets within the roots where the environment remains stable and rich. The tree adjusts its internal chemistry to maintain these safe chambers. When conditions shift above ground, the partnership adapts below, altering nutrient flow or expanding bacterial colonies as needed. This collaboration supports entire forests by enriching the soil and allowing trees to survive in places that would otherwise be too poor or too harsh for sustained air. Growth. Certain trees rely on species that are found nowhere else on Earth. Some forests hold relationships so specific that a single tree species may depend on a single animal, insect or fungus, found only within a narrow stretch of land. These partners carry pollen, disperse seeds, or protect the tree in ways no other species can replace. Over generations, both partners adapt to each other's presence. The shape of a flower may fit perfectly against the mouthparts of a single pollinator. The timing of fruit drop may align with the daily habits of a rare animal. If either partner disappears, the tree struggles to reproduce or defend itself. These relationships reveal how tightly woven life can become when species evolve together in the same small habitat. Preserving such trees means preserving the unique companions they rely on, and with them, the irreplaceable ecological webs that hold entire landscapes together. Some trees form living communities that behave like single organisms. In certain groves, many trunks rise from the same connected root system, sharing nutrients, water, and chemical messages that coordinate their growth. What appears to be a cluster of individual trees is in fact a single living network spread across wide areas of forest. When one trunk senses stress from drought or infection, the others shift their nutrient flow to support it. Leaves in one section may change color earlier or later than others, based on signals traveling through the shared root web. If one trunk falls, the network continues, sending up new shoots that replace the lost structure. Over time, these groves shape the land as unified beings rather than isolated individuals. Their shared strength allows them to outlast storms, grazing animals, and changing climate. The forest becomes a vast living body made of many stems but one continuous life. A few tree species can recognize their own relatives. Experiments show that some trees adjust their behavior based on whether nearby individuals share close genetic ties. When growing beside unrelated neighbors, they compete more strongly, expanding roots aggressively and investing heavily in chemical defenses. When growing beside kin, their growth patterns soften. Roots avoid crossing into the same territory. Leaves angle themselves to minimize shading, and nutrient flow becomes more cooperative. This recognition likely arises from chemical cues in the soil or signals exchanged through shared fungal networks. The result is a form of quiet family awareness that shapes how the forest grows. In stands where many related individuals cluster together, competition becomes less intense and group survival improves. These familial patterns ripple across generations, influencing where seeds take root and how groves expand. Some trees share nutrients with weaker trees nearby. Through intricate underground networks formed by fungi and roots, certain trees transfer water, sugars, and minerals to neighbors struggling under shade or stress. Healthy individuals with abundant resources send support towards saplings or damaged companions. The exchange flows like a silent generosity beneath the soil. This sharing helps maintain diversity and stability within the forest, ensuring that smaller or younger trees survive long enough to contribute to the canopy. When disturbances occur, such as storms or disease outbreaks, the network responds collectively. Nutrient flow intensifies toward areas of need, allowing recovery to unfold more quickly than any single tree could manage alone. These cooperative exchanges form the unseen foundation of resilient forests, where survival is not only an individual achievement, but a shared endeavor. Certain trees can restrict nutrient flow to competitors. In crowded forests, where every trunk stretches toward the same sky, some trees learn not only to share, but also to hold back. Under the soil, long root systems and fungal threads carry nutrients, water, and chemical messages between neighbors. This network is not always generous. When a tree senses another pushing too aggressively into its territory, it can alter the biochemical signals that move through the shared pathways. Defensive compounds accumulate near the junctions where roots meet, slowing the transfer of water or minerals toward the rival. In some cases, the tree even changes the acidity of the surrounding soil so that its competitor struggles to absorb what little remains. These restrictions do not kill the resisting tree's neighbor. Instead, they limit the growth of the pushier individual, preserving light and space for the larger community. Over years of subtle negotiation, the forest becomes a tapestry of shifting alliances and quiet rivalries, shaped by invisible choices made beneath the ground. Some trees adjust their growth speed to match the rhythm of neighboring trees. Across a dense woodland, trunks and branches seem to rise independently, yet many grow in surprising synchrony. Trees sense changes in light, wind, and root pressure created by those growing nearby. When one individual begins to stretch upward rapidly, its neighbors often slow down or increase their own growth to maintain a balanced canopy. If the forest becomes too uneven, strong winds can topple the most exposed trees. By tuning their pace to the community around them, these species create a shared architecture that stabilizes the whole grove. Young saplings adjust their early growth spurts, depending on whether the elders above are expanding or resting. Mature trees sense long-term trends through chemical signals drifting through fungal networks, guiding them toward harmony rather than competition. The result is a living forest that breathes through collective timing, each trunk responding to the tempo set by its companions. A few trees alter their branch angles based on the presence of sunlight competitors. When a nearby plant begins to cast shadows, some trees adjust the orientation of their branches in slow arcs that shift over months and seasons. Sensors in the leaves detect subtle changes in the direction of light, triggering uneven growth within the supporting twigs. Branches closest to the competing plant angle away, while those facing open sky lengthen more rapidly. This does more than preserve sunlight. It reduces the stress placed on trunks and roots by distributing weight in ways that reflect the changing shape of the forest. Over time, the canopy becomes a mosaic of interlocking forms, each tree carving out its own zone of illumination with movements so gradual they become invisible to the casual observer. Birds and climbing animals rely on these shifting structures as footholds, using the angled limbs as bridges through the forest's upper levels. Every curve and tilt becomes part of the silent negotiation for light that unfolds within densely layered habitats. Some trees rewrite their internal architecture after losing major branches. When storms, lightning, or heavy snow rip away a limb, the sudden loss creates shock waves through the trunk. The tree responds by reorganizing its flow of water and nutrients, redirecting resources towards surviving branches and reinforcing the tissues around passer. The wound. Vascular channels that once fed the missing limb begin to close, while new pathways grow in different directions. Inner wood layers thicken in patterns that counter the imbalance created by the missing weight. Slowly, the entire form reshapes itself, often sending out new shoots that restore the symmetry of the canopy. These responses are not impulsive. They follow deep evolutionary strategies that allow the tree to maintain structural integrity for decades after a major injury. The repaired architecture often becomes stronger than the original, turning trauma into an opportunity for reinvention that supports future growth. Certain trees can create spiral grain patterns that strengthen their trunks. Within some species, wood fibers do not run straight from root to crown. Instead, they wrap gently around the trunk, forming a spiral pattern that adds flexibility and resilience. This twisting architecture distributes stress evenly when strong winds push against the canopy, preventing cracks from spreading through the trunk. Young trees often begin with minimal spiral, deepening the twist as they age and as the environment demands greater durability. The orientation of the spiral can even shift over the life of the tree, adjusting to long-term weather patterns and prevailing winds. When these trunks finally fall and reveal their inner structure, the graceful whirls tell a story of the forces the tree has endured. Carpenters value such wood for its strength and resistance to splitting. Yet in the forest, the spiral's true purpose is survival, allowing trees to stand firm and mature. Landscapes shaped by constant pressure. Some trees produce natural pigments that protect them from intense sunlight. In regions where the sun burns bright through much of the year, certain trees generate colorful compounds within their leaves and bark that shield delicate tissues from bound day. Ultraviolet radiation. These pigments absorb or redirect harmful wavelengths before they can damage the cells responsible for photosynthesis. The colors may appear faint or vivid depending on the season, rising in concentration when sunlight becomes strongest. As the pigments build, they create a living sunscreen that prevents overheating and reduces moisture loss. Animals respond to these colors as well. Some see them as signs of toughness or maturity, choosing to feed elsewhere. Others use the tinted leaves as navigational cues through the forest. The pigments do more than protect the tree. They become part of a visual language that shapes interactions between plant and wildlife, revealing how deeply sunlight influences the life of a forest. A few trees use chemical shields to protect their leaves from ultraviolet light. Across their leaf surfaces, specialized cells manufacture compounds that fortify the tissue against harsh radiation. These chemicals form transparent layers that do not interfere with photosynthesis, yet block wavelengths that could harm delicate structures within the leaf. During seasons of intense sunlight, the tree increases production of these protective compounds, coating its canopy with a film that absorbs energy and prevents cellular damage. When clouds return or days shorten, the shield thins, reducing the metabolic cost of maintaining it. This dynamic response allows the tree to thrive under conditions that would scorch unprotected foliage. The chemical shield also affects the behavior of insects, some of which can detect the presence of these compounds and avoid the leaves altogether. In this way, a simple protective strategy becomes a multifaceted defense against the many challenges posed by bright and relentless light. Some trees turn bright colors to signal seasonal transitions. As temperatures shift and daylight wanes, pigments inside the leaves undergo a transformation that reveals vivid reds, oranges, and yellows normally hidden beneath summer greens. These colors are not merely decorative. They serve as signals to insects that feed on leaves, indicating that the tree is preparing to withdraw nutrients and become less appealing as a food source. The bright display also helps the tree manage sunlight as the angle of the sun changes with the season. Certain pigments filter the cooler light of autumn, allowing the tree to recover valuable resources before the leaves fall. The transformation becomes an annual announcement to the forest community, marking the quiet shift into colder days. Animals respond by altering their movements, gathering food, or seeking shelter as the canopy changes hue. The brilliance that humans admire is a strategic display honed by countless cycles of adaptation. Certain trees time their leaf fall to reduce competition. In crowded forests, the moment when leaves release from the branches can determine which seedlings thrive in the next growing season. Some trees drop their leaves early, clearing the canopy so more sunlight reaches the forest floor. This encourages their own seedlings to sprout before competing species can take advantage. Others hold their leaves longer, allowing the fallen litter to form a thick layer that inhibits germination of rival plants. By controlling the timing of leaf fall, these trees influence soil temperature, light availability, and moisture retention in ways that shape the entire understory. The rhythm of shedding is tuned to local climate patterns and the behavior of neighboring species. Through these carefully timed decisions, the forest becomes a living schedule of opportunities and challenges that unfold with the seasons. Some trees renew their crowns repeatedly throughout their lives. Instead of maintaining a single canopy for their entire lifespan, certain trees shed large branches over time and grow new ones in their place. This continuous renewal allows the tree to adapt to changing light conditions, shifts in wind exposure, and damage from storms or animals. Each new crown forms stronger attachments and improved angles based on the stresses the tree has experienced. The process refreshes the tree's ability to capture sunlight while reducing the likelihood of structural failure. Older branches that no longer serve the tree drop away, creating openings for fresh growth. Entire forests exhibit this cycle of renewal, with crowns rising and falling like waves over generations. The result is a dynamic canopy that evolves with the environment, allowing trees to remain vigorous far longer than their static appearance suggests. A few trees grow crowns that shift shape in response to wind direction. In regions where storms and steady winds shape the landscape, certain trees develop crowns that slowly rotate or lean depending on the direction of the prevailing chebar. Gusts. Sensors within the leaves and branches detect pressure changes long before human senses register anything unusual. Over weeks and months, the tree adds growth to sheltered sides while limiting expansion on the windward edges. This results in crowns that subtly migrate, adapting their form to reduce drag and channel force down the trunk in safer ways. The shifting crown does more than protect the tree. Birds nesting among the branches benefit from calmer pockets of air, while small mammals find stable footing even when storms roll across the canopy. Over time, these trees become living compasses that reveal the rhythm of the wind. Their shape records years of invisible negotiation between wood and atmosphere, carving a long history of storms into the graceful geometry above. Some trees create towering canopies that generate their own weather patterns. In humid regions where sunlight and moisture abound, certain trees grow to extraordinary heights, forming upper layers that experience entirely different conditions than the ground below. Leaves in these elevated zones release so much moisture that clouds often begin as faint wisps directly above the canopy. Air cools as it rises through densely packed foliage, creating small currents that lift water vapor toward the sky. These currents can influence when rain forms, where fog gathers, and how often storms pass over the region. Within the canopy, temperatures remain steadier than the open air. Animals that live entirely in the upper branches depend on this stability, timing their foraging and nesting cycles to the microclimate shaped by the trees themselves. The towering crowns act as engines of moisture and moderation, guiding the weather in ways that ripple across entire forests. Certain trees lower the air temperature beneath them. Leaves arranged in layered patterns create pockets of cool shade even on the hottest afternoons. As sunlight strikes the canopy, water evaporates from millions of leaf surfaces, drawing heat out of the surrounding air. This natural cooling effect can drop temperatures enough to influence which plants grow beneath the branches. Soil stays moist longer, and streams running through these shaded zones remain clear and cool. Animals seek refuge here during the warmest parts of the day, depending on the tree's quiet regulation of heat. The microclimate extends outward as breezes pass through the canopy, carrying cooler air toward nearby clearings. Over years, this cooling shapes where seedlings sprout and which species thrive in the understory. The tree becomes a living oasis, altering its environment not through effort, but through the elegant mechanics of leaves and light. Some trees produce scents that calm the nervous systems of animals. Within the bark, leaves, and resins of certain species lie aromatic compounds that drift through the air in gentle waves. When released in warm sunlight or carried on cool evening breezes, these fragrances interact with the nervous systems of animals that pass beneath the branches. Birds settle more easily in the canopy, mammals become less tense as they forage, and even insects respond with slower, more measured movements. The compounds evolved primarily as defenses against pests or as signals for pollinators, yet they hold a side effect that influences the emotional landscape of the forest. Humans walking through these groves often describe a sense of calm that feels deeper than simple appreciation of beauty. The air itself seems to steady the breath. These trees have become quiet caretakers of mood and balance, shaping the psychological tone of the places where they grow. A few trees generate natural sound dampening in forest environments. Branch arrangements, leaf structures, and bark textures combine to scatter sound waves that move through the forest. Instead of echoing sharply, noise is softened as it passes around trunks and through dense foliage. In some groves, this effect becomes strong enough to create pockets of quiet, where distant sounds fade into a gentle hum. Birds use these zones for nesting, choosing calm spaces where they can hear predators more clearly. Mammals navigate with greater confidence because subtle noises remain distinct instead of getting lost in reverberation. Even heavy rain behaves differently, landing on layered leaves that muffle each drop into a soft patter. These trees create acoustic sanctuaries without intention, simply through the structure of their living bodies. They influence how the forest hears itself, shaping communication among creatures that depend on sound for survival. Some trees absorb vibrations through their trunks in unexpectedly complex ways. When footsteps, wind, or distant thunder send tremors through the forest floor, certain trees respond with intricate internal adjustments. Fibers within the trunk shift to distribute the vibrations evenly, preventing damage to delicate tissues. Roots anchor more firmly in areas where the shaking is strongest, while the canopy subtly alters its sway to counterbalance the movement. This sensitivity allows the tree to detect approaching animals long before they are visible. It also helps the tree understand the stability of the soil beneath it, adjusting growth patterns to strengthen weak zones. Over many seasons, these vibration responses become a form of environmental literacy. The tree reads the landscape through movement, learning where the earth is firm, why storms approach, and where new risks might emerge. The entire trunk becomes an instrument attuned to the rhythm of the world around it. Certain trees create acoustic channels inside forests, the arrangement of trunks and leaves in particular species, then sound in ways that guide it along predictable paths. Whispers of wind, calls of birds, and movements of animals travel farther in these channels than they would through a chaotic canopy. Birds perching in these trees use the channels to send messages across wide distances, relying on the steady flow of sound to coordinate flight or wall of danger. Even predators listen for these pathways as they track prey. Humans walking through such forests often notice unusual clarity in certain directions, as if the trees have carved invisible corridors for sound to travel. These channels form naturally from the spacing of branches and the shape of the canopy, yet they influence communication patterns for countless species, shaping the auditory map of the entire region. Some trees respond to music with subtle changes in growth. Vibrations from rhythmic sound waves travel through air and soil, reaching the tree's leaves, bark, and roots. Cells responsible for growth react to these vibrations by altering the rate at which they divide or expand. Soft, steady frequencies encourage gentle upward growth, while irregular noises may slow expansion or redistribute energy toward roots. The effect is not emotional but mechanical. The tree senses movement in its environment and interprets it as information about wind, animals, or weather. Music simply provides consistent vibrations that mimic natural patterns, prompting measurable but delicate shifts in the plant's behavior. Over many seasons, these responses can create slight differences in leaf size, branch spacing, and root extension. The tree becomes a quiet listener, responding with the only language it knows: patient growth. A few trees store chemical memories of past seasons. As the seasons cycle through warmth, cold, drought, and rain, certain trees store biochemical traces of each experience within their tissues. These changes influence how the tree reacts to the next shift in weather. If a previous year brought harsh dryness, the tree strengthens water-retaining cells before the next warm season arrives. If winter came with deep cold, the tree thickens protective layers sooner when autumn returns. These adjustments create a living archive of experience that guides responses for many years. The memories do not resemble thought, yet they serve the same purpose: learning. The tree becomes better prepared for the world it expects, shaped by the world it endured. Some trees shape the biodiversity of an entire region through their presence. By casting shade, enriching soil, sheltering animals, and controlling moisture, certain trees determine which species can survive within their reach. Their fallen leaves feed the ground, their branches protect young plants from harsh sunlight, and their roots channel water into the deeper earth. Birds choose nesting sites based on the stability of their limbs. Insects specialize in their bark or flowers. Mammals rely on the fruits they drop or the hollows they form. When these trees flourish, entire communities flourish around them. When they vanish, the structure of the forest shifts, sometimes collapsing into simpler forms with fewer species. These trees act as keystone forces that hold complex ecosystems together. Their presence is not simply one element among many. It is the foundation upon which the diversity of life in the region is built. Certain plants can change the acidity of the soil they grow in. Plants don't just adapt to soil, sometimes they alter it. By releasing specific chemicals through their roots, certain species can change the pH of the surrounding ground, making it more acidic or more alkaline. This ability shapes which other plants can grow nearby, giving the host species a competitive edge. For example, pines and oaks drop acidic litter that lowers soil pH, favoring organisms adapted to those conditions. Other plants raise soil pH to improve nutrient availability. These changes ripple through entire ecosystems, influencing fungi, microbes, and animals as well. The soil beneath our feet isn't static. It is constantly reshaped by the plants that live in it. Every forest floor and meadow carries the chemical imprint of its vegetation. a living record of how plants engineer their own environments to suit their needs. Some trees can pump water upward higher than a skyscraper. One of the greatest mysteries of plant biology is how tall trees move water from their roots to their highest leaves. In species like coast redwoods, water must travel over 300 feet upward, taller than many skyscrapers. The mechanism relies on cohesion, the tendency of water molecules to stick together, combined with the pull of evaporation at the leaves. This creates a continuous column of water stretching from roots to crown, rising against gravity without pumps or muscles. The feat is so extreme that scientists still study the limits of how high water can climb. Yet forests prove it happens every day, silently and flawlessly. To stand beneath a towering tree and realize that every leaf at the top is drinking from the ground below is to marvel at a living system more efficient than any human-built machine. The Amazon River floods forests that fish pollinate plants in. Each year, the Amazon River rises with seasonal rains, flooding vast areas of forest. Instead of harming the plants, this cycle creates extraordinary adaptations. Some trees flower and fruit during the floods, relying on fish to spread their seeds. The fish eat the fruits that fall into the water, carrying the seeds in their bellies until they are deposited elsewhere. In this way, fish act as pollinators and dispersers in an ecosystem where water and forest merge. The flooded forests become a surreal world, with tree trunks submerged and animals swimming through the canopy. It is a vivid reminder that plants don't exist in isolation. They are woven into webs of interaction with animals, rivers, and climate. In the Amazon, even the fish help the trees, proving that cooperation can take the most unexpected forms. Some plants use sticky hairs to trap and drown insects. Not all insect-trapping plants are true carnivores. Some use sticky hairs on their leaves or stems to ensnare small insects that land on them. Once trapped, the insect may die and decompose, with nutrients washing into the soil and indirectly benefiting the plant. Other times, the hairs deter herbivores by making the plant less pleasant to eat. In some species, like wild tobacco, sticky hairs trap insects that would otherwise damage the leaves, turning the corpses into a protective shield. These strategies blur the boundary between passive defense and active feeding. They show how plants employ countless variations on survival, mixing stickiness, chemistry, and chance. What looks like a delicate hair on a leaf may in fact be a deadly snare, designed not to nourish the plant directly, but to tip the balance in its favor against the insect. World. Plants can produce toxins strong enough to be used in medicines. Many of the world's most powerful drugs began as plant toxins. The foxglove plant produces compounds that, in controlled doses, treat heart conditions. Willow bark contains salicin, the natural precursor to aspirin. The rosy periwinkle gave rise to life-saving chemotherapy drugs. These chemicals evolved as defenses, bitter or poisonous compounds meant to deter herbivores. Yet humans have learned to harness them, transforming poisons into cures. This duality, danger and healing intertwined, shows the complexity of plant chemistry. Every forest and meadow holds potential medicines waiting to be discovered. The next leaf or flower could carry molecules capable of saving lives. To the plant, it is merely defense. To us, it is possibility. In every toxin lies a hidden gift, a reminder that the boundaries between harm and healing are often thinner than we realize. Some algae blur the line between plant and animal life. Algae are often grouped with plants, but some species challenge neat categories. Certain algae can photosynthesize like plants, capturing sunlight for energy, but also move or consume other organisms like animals. Dinoflagellates, for example, can both make their own food and hunt for prey. Others form symbiotic relationships with animals, living inside corals or sea slugs to share energy. These organisms highlight how blurry the boundary between plant and animal really is. Evolution has experimented with many ways of capturing energy, and algae sit at the crossroads. To us, they may seem simple, but they represent some of the most versatile and ancient life forms on Earth. Looking into a droplet of pond water reveals this hidden flexibility, tiny beings that remind us categories are human inventions, while life itself resists easy definitions. Trees can live for thousands of years, older than civilizations. Some trees are so ancient that they predate entire human cultures. Bristlecone pines in California have been alive for nearly 5,000 years, older than the pyramids of Egypt. Olive trees, yews, and sequoias also reach extraordinary ages, standing as living witnesses to millennia of change. Their longevity comes from slow growth, strong wood, and the ability to regenerate damaged tissues. These trees are not just organisms but archives, recording climate shifts, droughts, and fires in their rings. To stand beside one is to brush against deep time, to feel the presence of a life that has outlasted empires and languages. They remind us that in the plant kingdom, patience can be the ultimate survival strategy. Where humans measure history in centuries, trees quietly count in millennia, rooted in place yet stretching endlessly through time. Trees can live for thousands of years, older than civilizations. Some trees are so ancient that they predate human history as we know it. Bristlecone pines in California, for example, have lived for nearly 5 millennia. These gnarled survivors sprouted long before the pyramids were built, weathering storms, droughts, and centuries of change. Their wood grows slowly and densely, resisting decay, while damaged tissues can be sealed off to protect the tree's core. Every ring in their trunks records the passing of years, offering scientists a timeline of climate shifts stretching back thousands of seasons. To stand beside such a tree is to feel the enormity of time pressing gently against your skin. They remind us that while civilizations rise and fall, nature carries on in silence, rooted in patience. Trees are not just witnesses to history, they are living history, still breathing in the present while holding stories that stretch deep into the past. Certain plants can smell nearby pollinators and respond. Plants don't have noses, but they can sense scent molecules in the air. Some species detect the chemicals released by approaching pollinators and respond almost immediately. For instance, certain flowers increase nectar production or release their own fragrances when they detect bee pheromones nearby. Others shift the timing of bloom opening, ensuring they're at their most inviting precisely when pollinators are present. This sensitivity is a kind of olfactory awareness, allowing plants to anticipate and adjust to the animals they rely on. To us, the idea of a flower smelling a bee seems strange, but it reflects the remarkable complexity of plant senses. Plants exist in constant dialogue with their environment, perceiving cues far beyond our own. When we walk through a garden, we may not notice, but the plants may already be responding to visitors in ways as subtle as breath on the wind. Some vines strangle entire trees to reach sunlight. Not all vines are gentle climbers. Some, like strangler figs, begin life as tiny seeds dropped by birds onto the branches of other trees. From there, the young fig sends roots downward, wrapping tightly around the host's trunk. Over decades, these roots thicken, constricting the host tree until it eventually dies. The fig then stands alone, supported by a lattice of its own roots, having used its host as scaffolding. This strategy allows the vine to reach sunlight in crowded forests, bypassing the struggle of growing from the dark forest floor. To see a strangler fig is to witness both beauty and ruthlessness intertwined, a living reminder that plants, too, compete fiercely for survival. Even without teeth or claws, they wield strategies of conquest, using patience and pressure to reshape the forest one tree at a time. The oldest known tree is nearly 5,000 years old. Among the high mountains of California grows a tree called Methuselah, a bristlecone pine estimated to be almost 5,000 years old. It sprouted long before written language, agriculture, or the rise of great civilizations. Gnarled and twisted by time, it survives in harsh conditions where few other plants endure. Cold winds, thin soils, and extreme weather have not killed it. Instead, they have preserved it, slowing its growth to a crawl. Each year adds only the thinnest of rings, building a body dense and resilient. Methuselah stands as one of the oldest living beings on Earth, older than empires, older than myth. Its existence humbles us, reminding us that life can stretch across timescales far beyond human imagination. When we measure our lives in decades, Methuselah measures in millennia, standing silent as ages pass in the shadow of its patient branches. Some plants survive in boiling hot springs. In the most extreme environments, where water bubbles and steams at near boiling temperatures, certain plants still manage to live. Algae and mosses have been found in geothermal springs, thriving where few organisms dare exist. Their proteins and cell structures are adapted to withstand heat that would destroy ordinary plants, allowing them to photosynthesize in liquid worlds that shimmer with coal. Steam. These hardy pioneers are studied for insights into life's possibilities, from bioengineering to the search for extraterrestrial organisms. If life can endure in boiling waters on Earth, perhaps it can survive in equally extreme places on other planets. To see green threads weaving through scalding pools is to realize that life's determination knows few boundaries. Even in environments that seem utterly hostile, plants find ways to endure, turning heat into habitat. Leaves can trap bubbles of air to help aquatic plants float. For plants living underwater, staying afloat can be as important as staying rooted. Many aquatic species have evolved leaves with specialized structures that trap air bubbles. These pockets act like tiny life jackets, helping the plant rise toward sunlight at the water's surface. Lotus leaves, for example, repel water and encourage bubbles to form, keeping them buoyant and dry above the pond. Other aquatic plants have spongy tissues filled with air spaces that keep entire stems floating. The result is a delicate balance between sinking and rising, guided by invisible pockets of air. To us, a lily pad drifting on a pond is simply peaceful. But inside its tissues is engineering as precise as any vessel, a living raft designed to hold sunlight steady above the water. Each floating leaf is a reminder of nature's ingenuity, rising on nothing but bubbles and breath. Some plants defend themselves with sharp crystals inside their tissues. Beneath the softness of many leaves lurks a hidden defense. Some plants produce microscopic crystals of calcium oxalate within their tissues, shaped like tiny needles. When an animal bites into the leaf, these crystals pierce soft tissues in the mouth, causing irritation, swelling, or even burning pain. The effect is immediate and memorable, discouraging further feeding. Taro, rhubarb, and dieffenbatia, sometimes called dumb cana, are among the plants that employ this strategy. To humans, they can be dangerous if eaten raw, but in nature, they function as armor, invisible until disturbed. The idea that a leaf can hide a forest of microscopic daggers is astonishing. Plants may seem defenseless, but their chemistry and structure often create barriers more effective than thorns or bark. Every bite is a gamble, reminding herbivores that even the gentlest-looking greenery can fight back in ways unseen. Flowers sometimes bloom in synchrony across vast regions. In some species, blooming is not an individual choice, but a coordinated event. Certain bamboos, for example, flower simultaneously across entire regions, even when separated by hundreds of miles. The synchronization happens on mysterious internal clocks, often spanning decades. Once the bloom is complete, the plants produce seeds and then die, resetting the cycle. The result can be a massive flush of food for animals, followed by sudden scarcity when the plants die back. Other species, like some desert wildflowers, also bloom in synchrony after rare rains, creating breathtaking waves of color across landscapes. These events remind us that plants move to rhythms we rarely perceive. Rhythms measured not in hours or seasons, but in decades and centuries. When the moment comes, the result is spectacular. A landscape transformed, as if the plants have chosen to sing in unison, releasing their beauty all at once. There are plants that can store memory of touch for minutes. Experiments with sensitive plants like Mimosa pudica have shown that they can remember being touched. When repeatedly disturbed, their leaves stop folding in response, as if the plant has learned the stimulus is harmless. What's more, this memory can last for minutes, even hours, before fading. It isn't memory in the way animals experience it, but a physiological form of storing information. The plant adjusts its responses based on past experiences, conserving energy by ignoring unnecessary signals. This suggests that plants are not just reacting blindly, but processing information in subtle ways. To think of a plant holding onto the trace of a touch is remarkable. It blurs the line between sensation and thought, suggesting that intelligence can take many forms, some as quiet and green as a leaf holding the ghost of a moment long, after it has passed. Some trees can regrow entirely from a single fallen branch. For certain trees, even a broken branch is not the end. If a limb falls to the ground and conditions are right, it can sprout roots and grow into a new tree. Willows, poplars, and banyans are famous for this regenerative ability. In some tropical regions, entire groves are created from branches that have taken root, each one genetically identical to the parent. This capacity ensures survival after storms or damage, turning accidents into opportunities. To us, a fallen branch may look like debris. To the tree, it is simply another chance at life, another reach toward the sky. This resilience shows us how plants refuse to be defined by fragility. Even in pieces, they carry the potential to rise again, blurring the line between ending and beginning. Plants remind us that life on Earth is both fragile and astonishing. From the smallest moss to the oldest tree, plants embody resilience, creativity, and patience. They shape the air we breathe, the food we eat, and the landscapes we inhabit. Yet they are also vulnerable to drought, fire, disease, and human activity. Their survival is a delicate balance, achieved through ingenious strategies, chemical defenses, hidden senses, and astonishing adaptations. In their stillness, we might overlook them. But when we pause, we see their richness. Forests that create rain, seeds that wait centuries, roots that reach deeper than buildings, flowers that sense and respond to the world around them. Plants remind us that life is not only fierce, but also endlessly inventive, weaving survival into every leaf and root. To walk among them is to remember that Earth's green world is fragile, astonishing, and inseparable from our own. Some flowers use reflective petals to stand out in low light. In shaded woodland edges, deep forest floors, and the dim minutes of dawn and dusk, some blossoms have turned their petals into natural reflectors. Instead of simply absorbing light, the surface of each petal is built from layers that scatter and bounce brightness back outward. Tiny folds, ridges, and air-filled spaces inside the tissue act together like a field of mirrors, catching even weak rays that filter through leaves. To human eyes, this can look like a soft glow, but to insects with more sensitive vision, it becomes a bright signal against a dark background. The effect is especially strong in flowers with pale or metallic hues, where reflected light is not buried under heavy pigment. Pollinators that are active in low light learn that these shining targets are worth visiting, so the plant gains attention at times when other species fade into the quad. shadows. Reflective petals turn scarce light into a reliable calling card. Certain mountain flowers grow hairy petals as natural insulation. In high alpine meadows, the air can feel gentle one moment and cut like ice the next. Flowers that choose to bloom in this unstable world must protect extremely delicate tissues from freezing winds and harsh radiation. Some have solved this problem by covering their petals and outer floral parts with fine hairs that trap a thin layer of still air. This trapped layer acts like a tiny blanket, slowing the escape of warmth generated by the sun and by the plant's own metabolism. The hairs also scatter intense ultraviolet light that pours down through clear mountain skies, preventing damage to sensitive pigments and pollen. When insects land, they find a surface that is slightly less cold than the open air, which encourages them to stay longer and move more actively inside the bloom. Hairy petals are not just a visual quirk. They are carefully evolved insulation that allows these flowers to operate in a climate that swings between brilliance and frost. Some flowers produce nectar with complex chemical messages. Sweetness is only the beginning of what many nectars contain. Within the clear liquid hidden at the base of certain blossoms is a cocktail of sugars, amino acids, ions, and specialized compounds that influence the minds and ET, bodies of visiting animals. Some of these molecules sharpen memory, helping a bee remember the scent and shape of a particular flower so it returns more often. Others adjust the energy content or viscosity of the nectar, shaping how quickly a pollinator feeds and how long it lingers. In some species, the mixture changes as the bloom ages. Early nectar may encourage exploration and learning, while later nectar calms visitors once enough pollen has been moved. Even the microbes that live in nectar can alter its chemistry, adding another layer of signals. Pollinators do not consciously interpret these messages, but their behavior shifts in predictable ways. The plant uses chemistry to guide partners toward patterns of movement that best support successful reproduction. There are flowers whose seeds travel on water for great distances. Along riverbanks, lakeshores, and coastal wetlands, certain flowering plants turn water into a highway for their offspring. Their seeds develop with buoyant structures that keep them afloat, such as spongy tissues, trapped air pockets, or thick protective coats that resist soaking. When fruits ripen and break open, seeds drop onto the surface and begin drifting with currents and waves. Some ride gentle streams that carry them far downstream. Others enter tidal waters where rhythmic surges move them back and forth until they lodge in a suitable patch of mud or sand. During the journey, the protective layers shield the embryo from salt, decay, and sudden changes in temperature. This method allows a single plant to spread descendants over wide areas, reaching new islands, river bends, or distant shorelines without any help from animals or wind. Each flower becomes the starting point for a quiet voyage that may end many landscapes away. Some flowers can bloom under thick snow. When winter loosens its grip only slightly, a few determined species are already preparing to flower. Beneath the snow, their underground bulbs, rhizomes, or storage roots have been waiting through months of cold with reserves of energy ready to release. As soon as soil warms by even a small amount, growth begins. Buds push upward, sometimes while the surface is still covered by icy layers. The tip of the developing shoot can generate enough warmth through active metabolism to melt a narrow tunnel as it rises. By the time the bug reaches open air, it may still be surrounded by white ground and chilled wind, yet it opens anyway. These early blooms take advantage of light that is not yet blocked by leaves and of pollinators that have very few other food sources. Snow-resistant petals are often thick and waxy, protecting reproductive parts from freezing droplets. The entire strategy is a race to capture the first workable days of the year. A few flowers build gentle microclimates inside their blossoms. Step inside the curved chamber of certain blooms, and the air feels noticeably different from the world outside, at least if you were small enough to notice. Petals that form cups, funnels, or overlapping roofs create pockets where wind slows and humidity climbs. Sunlight that enters is absorbed and re-emitted as soft warmth, which the enclosing structure holds close. Within this sheltered space, temperature fluctuates less sharply, keeping pollen grains hydrated and stigmas receptive. For insects, these microclimates provide a resting place that is calmer and milder than the surrounding environment. On chilly mornings, a bee can warm up faster by lingering inside. On hot, dry afternoons, the slightly cooler, moister air can reduce stress. Plants that invest in this internal architecture often gain more consistent pollination because visitors stay longer and move more thoroughly through the reproductive ND parts. The flower becomes a tiny room with climate controls tuned to its own needs. Some flowers grow only on slopes facing specific directions. Across a hilly landscape, conditions on a north-facing slope can differ dramatically from those on a south-facing one, even over short distances. Sunlight strikes at different angles, evaporation rates change, and soil remains cooler or warmer depending on exposure. Certain flowering species become so closely adapted to these patterns that they appear only on slopes that face a particular direction. Their seeds may germinate successfully only when winter snow melts at the right pace, or when spring sunshine arrives with a specific intensity. The roots expect a particular moisture regime, neither too dry nor too saturated, which is created by the daily path of light across that slope. As a result, populations can form narrow bands along hillsides, tracing invisible lines of temperature, light, and water. To someone walking the landscape, it may look almost mysterious that the same flower vanishes as soon as the hill turns. In reality, it is the mark of extremely precise environmental tuning. Certain flowers time their blooming to avoid competitors. In ecosystems buzzing with activity, many species share the same general pollinators. Instead of relying on brighter colors or larger displays, some plants choose a subtler tactic by shifting their flowering schedule. They open buds earlier in the season, later in the season, or during specific windows within that season when other blooms are scarce. This timing reduces the clutter of signals that pollinators must sort through and increases the likelihood that visitors will focus on their blossoms. The internal controls that set this schedule draw on cues such as day length, accumulated warmth, and patterns of rainfall. When conditions align with the plant's inherited timing rules, entire populations may burst into flower together, creating a brief period of dominance. Once pollination is complete, the flowers fade, just as other species begin. This staggered flowering helps multiple plants share the same set of pollinators without direct conflict, each taking a turn at the spotlight. Some flowers hide their nectar deep inside narrow tubes. Instead of placing rewards on an open surface, certain plants tuck nectar far inside elongated floral tubes. Only animals with the right anatomical tools can reach these concealed reserves. Long-tongued bees, hawk moths with extended feeding organs, or birds with slender beaks can probe to the bottom, while less specialized visitors cannot. This architectural choice filters out inefficient guests that might sip a little and leave without touching pollen in helpful ways. When a suitable pollinator does reach in, its head or face inevitably presses against the ring of anthers and the receptive stigma positioned around the tube entrance. Pollen dusts the exact body parts that will contact the next flower of the same kind. By pairing hidden nectar with precise geometry, the plant orchestrates reliable pollen transfer while protecting its valuable resource from casual theft. The depth of the tube becomes a gatekeeper shaping the entire pollination partnership. There are flowers whose colors shift with soil chemistry. In some species, petal color is not a fixed trait, but a sensitive reflection of the ground they grow in. Pigment molecules in the petals change their structure depending on the balance between acidity and alkalinity in the surrounding soil solution that feeds the prairie plant. When roots draw up water rich in certain ions, the internal environment of petal cells shifts, and the same pigment can appear as soft pink, deep violet, or clear blue. Gardeners sometimes notice that the same kind of shrub wears different hues in different beds, or that colors transform gradually as soil conditions change. In the wild, this responsiveness can influence which pollinators are attracted, or how well blooms blend with or stand out from the background. It may also allow the plant to adjust to subtle changes in mineral availability. Each flower becomes a small living indicator of the hidden chemistry beneath it, translating invisible conditions into visible shades. Some flowers thrive in volcanic landscapes. In regions shaped by eruptions and fresh lava flows, a few remarkable flowering plants take root long before most other life returns. Volcanic ground begins as a harsh mix of ash, pumice, and fractured rock that holds very little water. These flowers survive by anchoring their roots into the smallest crevices, where bits of moisture and minerals collect after rare rainfalls. The ash itself becomes a source of slow-releasing nutrients as it breaks down, creating fertile pockets that these plants can access before any competitors arrive. Their blossoms appear quickly during short windows of favorable weather, allowing them to complete an entire reproductive cycle in conditions that shift rapidly between intense heat and sudden chill. Their roots help stabilize loose volcanic debris, gradually turning barren fields into surfaces that future species can inhabit. These plants are among the first signs of life after destructive events, and their presence demonstrates that even in newly formed landscapes, flowers find ways to adapt, endure, and rebuild the foundations of an ecosystem. Certain flowers attract pollinators with infrared heat signatures. Some blossoms communicate using warmth rather than color. Their petals or central structures produce subtle patterns of heat that stand out to insects capable of sensing temperature differences. These warm zones guide pollinators toward nectar and pollen, allowing the visitor to navigate even in dim light. The heat comes from concentrated metabolic activity in tissues that act like tiny furnaces within the bloom. During peak pollinator activity, the flower increases this output to create a stronger thermal signal. When fewer visitors are around, the warmth fades to conserve energy. To many insects, temperature-based cues are easier to detect than changes in color, especially in dense or shadowed environments. The thermal patterns also help certain pollinators warm their flight muscles before taking off again. By offering both guidance and comfort, the flower increases the likelihood that each visitor will stay long enough to transfer pollen. This technique shows how blossoms can use invisible forms of communication to interact with the living world. Some flowers carry microscopic mirrors inside their petals. Within the petals of a few species are tiny reflective structures arranged in layers that redirect incoming light. These microscopic mirrors intensify brightness by bouncing light multiple times before it exits the surface, creating shimmering effects that are especially visible to insects with sensitive vision. The reflective layers may enhance a single color by channeling it through membranes that amplify its intensity, or they may produce subtle iridescent flashes. Change with viewing angle. These mirrors are made from precise arrangements of clear cells and air-filled spaces, crafted through natural growth rather than any external influence. Besides attracting pollinators, the reflections can protect delicate inner tissues by pushing away excessive sunlight. This optical adaptation provides advantages in competitive habitats where many blossoms bloom at once. Each petal becomes both a signal and a shield, demonstrating how flowers can shape light at microscopic scales to improve survival and reproduction. There are flowers that use Velcro-like surfaces to hold pollinators. Some flowers have evolved surfaces filled with tiny hooks or barbs that gently catch onto the bodies of visiting insects. These structures hold the visitor in place long enough to ensure that pollen is picked up or deposited in exactly the right location. The hooks are flexible, allowing the insect to move without injury, yet firm enough to slow its progress and guide it towards specific structures inside the boom. As the insect navigates these textured surfaces, it passes over anthers and stigmas arranged to maximize contact. This slows nectar thieves that might otherwise slip in and out without contributing to pollination, while encouraging legitimate visitors to interact more fully with the flower. Once the pollinator has completed its task, it can pull free without difficulty. These surfaces reveal how texture alone can shape behavior and create a controlled exchange between animal and plant, all without need for traps or forced biche. Some flowers can survive fire and bloom after ash settles. In fire-dependent ecosystems, certain flowers rely on flames to begin their life cycles. While the visible plant may perish in a blaze, protected structures remain hidden underground, where heat cannot reach them fully. After a fire passes, the landscape becomes open and bright, and nutrients released from burned vegetation enrich the soil. These conditions signal the buried tissues to awaken. Shoots emerge quickly, drawing from stored reserves that were saved during the previous growing season. Many seeds in these species require exposure to the chemicals released by smoke to break dormancy, ensuring that germination only occurs once fire has cleared competing vegetation. When the new flowers appear, often in large groups, they attract pollinators that search for nourishment in the newly exposed environment. This cycle is not merely survival. It is a strategy that depends on fire as a catalyst for renewal, allowing these plants to claim the landscape at the exact moment when it is most favorable. Certain flowers manipulate airflow to spread their scent efficiently. Blossoms that rely heavily on fragrance often use clever structural designs to guide air currents. Some petals form channels that draw breeze through the flower, allowing scent molecules to disperse at greater distances with minimal effort. Other shapes create vortices that lift aroma upward into layers of air where flying insects travel. Even slight curves or ridges can influence how wind moves across the bloom, shaping scent distribution with surprising precision. These airflow patterns reduce the amount of fragrance needed to reach pollinators, helping the plant conserve energy. Pollinators benefit from clear odor trails that guide them efficiently toward the source. By manipulating air in these subtle ways, flowers extend their reach far beyond what a simple release of scent could achieve. The bloom becomes a small architectural device built to communicate with the atmosphere itself. Some flowers contain natural sunscreens to protect their pollen. Bright sunlight supports growth but can damage the sensitive grains that carry a plant's genetic material. To prevent this, certain flowers produce protective molecules that absorb harmful ultraviolet light before it reaches pollen. These compounds settle into the outer layers of petals and anthers, forming a shield that remains stable through long hours of exposure. Many of these protective pigments also influence visible color, contributing to deep blues, rich purples, or warm reds. As sunlight intensifies, the flower may increase production of these molecules, strengthening its defenses during the hottest part of the day. By safeguarding pollen from ultraviolet injury, the plant ensures that grains remain viable when carried to the next bloom. This built-in defense system shows how flowers combine beauty with function, transforming vivid color into a line of protection for their most delicate structures. There are flowers that grow on rocks with almost no soil. Certain species flourish in environments where soil is nearly absent, clinging to steep cliffs and stone walls that most plants cannot tolerate. Their roots search for microscopic pockets of dust and mineral fragments trapped in cracks. Over time, the roots widen these spaces as they grow, slowly creating a more stable foothold. Because nutrients are scarce, these plants grow slowly and allocate resources carefully. Their leaves may be thick, waxy, or reduced in size to conserve water. Despite these challenges, they produce blossoms that attract pollinators traveling along rock faces or windy ridges. The flowers often bloom during brief periods when moisture is present, taking advantage of every rare opportunity. Their persistence transforms barren stone into living habitat. These cliff dwellers demonstrate how little a plant truly needs when it is adapted perfectly to extremes. Some flowers hide their own scent from predators. While many blossoms rely on fragrance to attract pollinators, others must avoid drawing unwanted attention from animals that might damage them. These species release scent only in specific directions or only within enclosed spaces formed by their petals. A pollinator that enters the chamber can detect the aroma easily, yet predators outside smell very little. Some flowers alter their scent chemistry so that nectar carrying notes remain undetectable until a trusted visitor is physically close. Others release fragrance only during short windows of time when certain threats are inactive. These strategies allow the plant to communicate selectively, ensuring that its signals reach those who help rather than those who harm. Scent becomes a controlled resource used with care to balance attraction and protection. Certain flowers use petal temperature to attract insects. Warmth can serve as a powerful invitation, and some blossoms create temperatures higher than the surrounding air. Petals absorb sunlight efficiently, or the plant concentrates metabolic activity in specific tissues that radiate gentle heat. This warmth becomes a beacon to insects that benefit from elevated body temperature, especially in cool climates or early morning hours. A pollinator landing on such a bloom may remain longer than it would in a cold environment, exploring the structure more thoroughly and interacting with pollen ingress. More effective patterns. The warm petals also help volatile scent molecules rise into the air, increasing the distance over which the flower can be detected. By offering thermal comfort, these flowers increase their chances of being visited repeatedly. Their temperature-based strategy blends energy management, attraction, and timing into one subtle but powerful advantage. Some flowers have built-in lenses that focus light. Certain blossoms contain petal tissues arranged in smooth curves that shape and redirect sunlight the moment it touches their surface. These natural lenses concentrate brightness toward the hidden reproductive structures at the center of the bloom. By doing this, the flower keeps pollen warmer and more active during cool mornings or cloudy periods when temperatures normally limit its effectiveness. Plant cells create this effect by forming layers with slightly different densities, which causes light to bend gently as it passes through. The focused glow can also appear as a subtle shimmer visible to insects that are drawn to bright contrast. Some pollinators rely heavily on distinctions in light intensity, so this focused reflection becomes a practical signal, not just a visual flourish. The phenomenon allows the plant to attract visitors without producing large amounts of pigment, saving valuable energy. It also provides an advantage in shaded environments where light is scattered and weak. Through simple growth and careful cellular architecture, the flower creates a tiny optical device that strengthens almost every part of its reproductive AE. Strategy. There are flowers that grow in complete darkness inside caves. Deep within certain caves, where daylight never enters and photosynthesis becomes impossible, a few rare flowering plants survive by forging unusual partnerships. Instead of relying on sunlight, these species draw nourishment from underground fungi that break down organic matter carried into the cavern by dripping water. Wandering animals. The plants trade structural stability and a safe habitat in exchange for a steady supply of minerals and carbon compounds that the fungi unlock from decaying GE. Debris. With no need for green pigments, the flowers appear pale, ghost-like, or even translucent. Their petals are often thick to withstand constant humidity, and their scents linger longer in the still air, guiding cave insects that navigate by touch and smell. These pollinators do not depend on color, so the plant invests in texture and fragrance rather than visual appeal. Some blooms appear only when temperature and moisture conditions reach a narrow balance that might last for only a short time. These flowers show that darkness does not prevent the cycle of blooming. Instead, it creates a world where life adapts through partnerships and sensory strategies very different from those outside the cave. Some flowers offer caffeinated nectar to influence pollinator memory. A few blossoms create nectar that contains natural stimulants, including mild amounts of caffeine produced by unique biochemical pathways within the plant. When certain insects drink this nectar, the compound sharpens their ability to remember specific scents, petal shapes, and flight paths leading to the bloom. The effect is subtle, yet powerful. A pollinator that forms strong memories of a particular flower usually returns more often, ensuring that the plant receives repeated visits that greatly increase the chances of successful pollen transfer. The flower benefits by encouraging loyalty without providing more nectar than usual. The stimulant does not harm the visitor. Instead, it enhances learning centers within the insect's nervous system, making the bloom stand out among many competing options. Over time, this creates a pattern in which pollinators develop reliable routes that lead back to the same species again and again. The mechanism is one of the most elegant examples of how plants can influence behavior through chemistry alone, shaping relationships that appear almost intentional. A few aquatic flowers create floating highways for beetles. Some water-dwelling plants produce blossoms that rest gently on the surface of ponds, marshes, or slow-moving streams. Their broad, sturdy petals form platforms that allow beetles and other crawling insects to travel across the water without sinking. These floating pathways guide visitors toward the flower's center, where scent, texture, and warmth encourage them to explore. The structure of each petal distributes weight across a large area, preventing even heavier insects from breaking the surface tension. Some species create subtle slopes that direct movement inward, while others produce glossy patches that reflect light, helping insects locate the bloom from a separate distance. Beetles often become covered in pollen as they crawl across these surfaces, and their habit of wandering from one floating flower to another increases the likelihood of successful pollination. The cooperation between plant and insect transforms the water itself into part of the strategy. Each blossom becomes not just a food source, but a bridge that supports life above a liquid world. Some flowers use fungal networks to coordinate blooming. In certain forests and grasslands, flowering plants are connected to vast underground webs formed by symbiotic fungi. These fungal strands move nutrients, minerals, and chemical messages between roots. When one plant senses a change in its environment, such as the arrival of favorable moisture or the presence of specific microbes, it releases signals into the power network. Other plants of the same species detect these cues and adjust their internal cycles so that blooming occurs in a synchronized wave. This coordination increases the chance that pollinators will encounter many blossoms at once, boosting overall reproductive success. The network also helps plants conserve energy by preventing early or poorly timed flowering. Because the fungal partners exchange nutrients in both directions, each plant strengthens the system by supporting the others. The blooming event becomes a community decision guided by shared information flowing silently through the soil. This cooperation shows how flowers participate in an underground communication system far more intricate than anything seen above the surface. Certain flowers form symbiotic partnerships with birds. Some blossoms evolve structures that rely entirely on specific birds for pollination. Their tubes match the length of the bird's beak, their colors appeal to avian vision, and their nectar composition supports the high energy demands of rapid flight. In return, the bird receives a dependable food source that few competitors can access. The partnership becomes so precise that the plant may bloom only when migratory patterns bring its avian partner back into the region. Feather placement, feeding posture, and wing movement all influence where pollen attaches during each visit. The bird becomes a mobile bridge between blossoms scattered across a landscape. For the plant, this specialized strategy eliminates the inefficiency of attracting multiple pollinators. For the bird, it creates a reliable route that provides nourishment during long journeys. This relationship reveals how two very different forms of life can shape one another through countless generations of mutual benefit. Some flowers use sticky threads to capture airborne pollen. While many plants rely on insects or wind, a few species use delicate sticky threads produced inside their blossoms to catch airborne pollen drifting through the palm down. Environment. These threads form a fine mesh that coats the inner surfaces of the petals or hangs between structures that create narrow passageways. As air moves past the bloom, stray pollen grains that belong to the same species become trapped. Once collected, the grains are moved slowly by capillary forces or gentle petal movements toward the receptive stigma. This method allows the plant to gather pollen even in areas where pollinators are scarce or where breezes are unpredictable. The threads remain effective because they resist drying out and maintain consistent tackiness throughout the blooming period. This quiet strategy blends the randomness of wind with the precision of guided capture. Instead of waiting for a direct visitor, the flower builds its own net to gather what the air brings. There are flowers that bloom for only a single hour. Some species open their blossoms for an extremely brief window, sometimes less than the span of one passing cloud. These flowers store energy and build internal pressure for hours or days before releasing their petals in a sudden unfurling. The short blooming period aligns with a precise moment in the daily rhythm of their environment. It may coincide with the activity of a single insect, a specific change in humidity, or a narrow burst of sunlight that reaches a hidden location. During that hour, the plant performs all essential exchanges of pollen and nectar, trusting that its chosen partners will arrive exactly on time. Once the moment passes, the blossom closes permanently, protecting developing seeds from unnecessary damage. This intense strategy reduces exposure to predators, harsh weather, and energy loss. The flower exists in full form for only the briefest glimpse, yet the entire future of the plant depends on that carefully chosen interval. Some flowers generate subtle magnetic fields. A few species produce faint magnetic signatures through the movement of charged particles within their cells. These fields are incredibly weak, yet certain insects possess sensory organs capable of detecting variations in magnetic direction and intensity. As a pollinator approaches, it notices the shift in the local magnetic pattern and uses it to locate the most rewarding part of the bloom. This effect is not created deliberately. It arises naturally from the arrangement of ions, metabolic processes, and the flow of nutrients through the plant's tissues. Still, the structure of the blossom can enhance or focus the magnetic field along particular pathways, creating a consistent signal. The field may also interact with incoming pollen grains or influence how particles settle within the flower. Although invisible to humans, this method adds another layer of subtle communication between plant and pollinator. It demonstrates how even the smallest forces can play meaningful roles in natural interactions. Certain flowers bloom in rhythms linked to lunar cycles. Some species coordinate their flowering with the phases of the moon. Their internal clocks respond not only to changes in daylight, but also to variations in nighttime brightness and gravitational influence. When the moon reaches a specific point in its cycle, these plants initiate a chain of biological events that leads to synchronized blooming across entire populations. Pollinators that travel at night use the increased light to navigate between blossoms more efficiently during these periods. The timing also reduces competition with species that rely solely on solar cues. In coastal regions, the lunar rhythm may align with tidal patterns that influence moisture levels or temperature changes. By linking their blooming to a cosmic cycle, these flowers create predictability in environments where conditions shift constantly. This connection between plant biology and the steady movement of the moon reveals how deeply the rhythms of life can reach into the natural world. Some flowers produce nectar that changes flavor throughout the day. Within certain blossoms, nectar is not a fixed substance. Its composition shifts through the hours as the plant adjusts sugars, amino acids, and aromatic compounds in response to temperature, humidity, and visitor activity. Early in the morning, the nectar may be richer in simple sugars that provide a fast burst of energy to insects shaking off the cool air of dawn. As heat rises toward midday, the nectar may grow thicker or slightly more complex, creating a reward that lingers on the mouthparts of experienced pollinators that can navigate crowded habitats. Near evening, the flower may produce nectar with softer or more fragrant notes that appeal to late-arriving species such as crepuscular moths. These timed adjustments are controlled by internal biochemical pathways that respond to light and nutrient availability. By constantly editing the flavor and texture of nectar, the plant shapes the behavior of the creatures that visit it. The strategy ensures that each type of pollinator receives a reward tailored to its own patterns, while the flower gains consistent and efficient pollination across a full cycle of daylight. There are flowers that release warm fragrances only at sunset. In certain habitats, blossoms wait until daylight fades before releasing their most inviting scents. As the sun dips and the air cools, these plants begin producing volatile molecules that rise in gentle waves. The warmth in these fragrances comes from subtle chemical reactions that require less metabolic effort during evening hours. The result is a rich scent that spreads farther through calm twilight air than it would during the heat of midday. The timing aligns with the foraging habits of nocturnal visitors such as moths and night-active beetles that depend more on scent than on sight. These pollinators travel long distances guided by aromatic trails drifting across open landscapes. The flowers conserve energy by releasing fragrance only when their preferred partners are active, avoiding waste during daylight hours when scent would evaporate quickly or draw unwanted attention. This rhythm creates a predictable meeting point between plant and pollinator within the quiet transition between daylight and darkness. Some flowers host tiny invertebrate communities inside their blossoms. Inside the sheltered folds of certain flowers live miniature ecosystems composed of insects, mites, and other small creatures. These invertebrates seek refuge within the petals where humidity remains stable, predators are scarce, and food particles collect naturally. The microhabitat may include pools of condensed moisture, traces of nectar, fallen pollen grains, and plant oils that support an entire community. Some flowers even generate subtle warmth or maintain slightly higher humidity that allows these tiny residents to thrive. The presence of invertebrates can benefit the plant because their movements stir pollen, clean surfaces, or deter harmful insects through simple competition. Over time, these communities develop predictable patterns. Certain species arrive first, preparing the space by consuming debris. Others follow, feeding on the residue or taking advantage of the protective chamber. The flower becomes more than a reproductive structure. It becomes a small dwelling that supports life far beyond its own needs, demonstrating how complex interactions emerge even in temporary spaces. Certain flowers build chemical defenses stronger during full sun. Some blooms increase their defensive chemistry during the brightest hours of the day. When sunlight becomes intense, these plants activate enzymes that release compounds meant to deter herbivores or harmful microbes. Many of these chemicals are bitter or pungent, discouraging animals that might bite into petals or drink nectar without contributing to pollination. Heat and ultraviolet radiation can also trigger the formation of protective pigments that absorb harmful wavelengths. These pigments appear as deeper reds, purples, or blues and shield delicate structures beneath the petal surface. As evening approaches and light softens, the plant reduces its defensive output to conserve resources. This rise and fall in chemical strength follows a daily cycle controlled by internal clocks that respond to signals of light intensity. By building stronger defenses at the moment when damage is most likely, the plant preserves its fertility and ensures that pollinators encounter blossoms in healthy condition. Some flowers bloom underground and never see light. A handful of rare species produce blossoms entirely beneath the soil surface where light cannot reach. These plants rely on roots and underground stems that navigate through warm, moist earth. Instead of attracting flying pollinators, they form relationships with burrowing insects or small mammals that travel through the soil. The blossoms produce strong scents that drift through tunnels and cracks, guiding visitors by smell alone. Because petals are protected from sunlight, they do not need vibrant colors or photosynthetic tissues. They are often pale, thick, and resilient, designed to withstand pressure from the surrounding earth. The flower may open within a small chamber created by shifting roots or by the movement of underground animals. Pollination occurs quietly in darkness as visitors carry pollen from one hidden bloom to another. This strategy protects the plant from harsh weather and predators, while allowing reproduction in environments where surface conditions are unpredictable or hostile. A few flowers have petals that act like solar panels. In regions with intense sun, some blossoms build petal surfaces that capture and store light energy for short periods. These petals contain specialized pigments and internal structures that absorb sunlight efficiently and convert a portion of it into warmth or improved AEN, metabolic function. The slight increase in temperature inside the bloom helps pollen mature at a steadier rate and keeps visiting insects comfortable enough to stay longer. The captured energy also supports the plant's ability to maintain fragrance production during cooler periods. The effect resembles the way natural solar collectors accumulate heat. The petals do not generate electricity, but they direct absorbed radiation toward reproductive tissues that depend on consistent environmental conditions. By turning sunshine into a controlled resource, these flowers maintain a reliable microenvironment that buffers them from sudden cloud cover or cold winds. The adaptation highlights how petals can serve as functional organs rather than simple displays. Some flowers rely entirely on wind-sculpted blizzards of pollen. There are blossoms that do not court animals at all. They release vast quantities of lightweight pollen into open air, where wind currents carry it across fields, valleys, or forests. The pollen grains are shaped to travel efficiently, often with smooth surfaces and internal structures that help them stay aloft. These flowers usually lack bright colors or strong scents because they do not need to attract visitors. Instead, they invest heavily in producing enormous amounts of pollen to ensure that at least some grains find their way to receptive structures on distant plants. The timing of release often coincides with dry conditions and steady breezes that allow pollen to drift freely. Because the process is unpredictable, the plants have evolved broad margins for success, releasing more pollen than they could ever use. The air becomes the medium of reproduction, turning the landscape into a silent cloud of drifting potential. Certain flowers grow symmetrically only under specific temperatures. Some species produce perfectly balanced blossoms only when the surrounding air remains within a narrow temperature range. If conditions are too cold or too warm, petals may form uneven shapes or fail to align properly around the center. The symmetry depends on the rate at which cells divide and expand, processes that are extremely sensitive to heat. Within the ideal temperature window, growth occurs evenly across each side of the flower, creating the familiar star-like or radial patterns associated with many species. When temperatures drift from that range, the flower adapts by producing asymmetrical forms that may still function, but appear distinctly different from the ideal bati. Structure. Pollinators often prefer the more symmetrical version, which encourages the plant to bloom at times of year when the environment supports reliable development. This connection between form and temperature shows how deeply climate influences floral architecture. Some flowers can detect vibrations from approaching pollinators. There are blossoms that respond to the subtle trembling of air produced by the wing beats of insects. Their petals and internal tissues behave like finely tuned sensors that pick up vibrations passing through the plant structure. When the correct pattern of movement is detected, the flower activates rapid adjustments such as increasing nectar concentration or repositioning reproductive structures. These shifts make the bloom more rewarding and more prepared for the arrival of its visitor. The detection is possible because plant cells are connected by flexible walls that transmit mechanical signals efficiently. Different species recognize different vibration signatures, allowing them to distinguish between helpful pollinators and creatures that would provide no benefit. This sensory ability helps flowers conserve resources by offering their best rewards only when the right partners are nearby. It also synchronizes the timing of pollen release with the moment of contact, improving the accuracy of pollination. There are flowers that evolved petals shaped like radar dishes. A few remarkable species grew petals curved in ways that gather and reflect sound. These shapes act much like tiny listening bowls that amplify the acoustic signals created by flying insects. When certain pollinators approach, the dish-shaped petal focuses the sound towards sensitive tissues that register the vibration. The flower uses this information to determine when to release scent, when to shift its internal temperature, or when to expose fresh pollen. The curved surface also helps some insects locate the bloom by reflecting their own sounds back toward them. This neutral use of acoustics creates a sensory dialogue between plant and pollinator. The petal does not merely sit in the environment. It becomes an active surface that influences sound waves traveling through the air. By shaping themselves into efficient acoustic tools, these flowers demonstrate that nature can discover similar solutions again and again, even in organisms that remain rooted in place. Some flowers produce soap-like compounds on their surfaces. A small group of flowering plants creates natural foaming compounds across the surfaces of their petals and leaves. These soap-like molecules form when the plant combines certain fatty acids with specialized sugars that break surface tension in water. When rain or dew collects, the liquid picks up these compounds and forms small bubbles along the edges of the blossom. These bubbles deter many insects that might chew on delicate petal tissue, since the slippery coating reduces their ability to grip and climb. The compounds also help the plant remove dust, pollen from other species, and fungal spores that settle in humid conditions. When breezes pass through the flower, the bubbles break and release molecules that can carry subtle scents or defensive signals into the air. The soapy coating also protects the petals from excessive moisture, preventing water from pooling in ways that could cause rot. This adaptation shows how even a fragile-looking blossom can use chemistry to keep its surface clean, safe, and ready for the sensitive work of reproduction. Certain flowers create nectar pools that resemble tiny lakes. In some species, nectar is produced not in small drops, but in large open pools that fill wide floral chambers. These pools can span the entire width of the blossom, forming shallow basins that shimmer in the light, as if reflecting the sky above. The depth and volume of nectar attract larger visitors such as beetles, butterflies, or birds that can move across the pool without damaging the delicate interior. The liquid acts as both a reward and a habitat. Tiny organisms sometimes grow at the edges, feeding on minerals and organic traces dissolved in the nectar. Some flowers use the reflective surface to enhance visibility. Light bounces off the nectar and illuminates complex petal patterns that guide pollinators toward the center. The plant invests heavily in producing this reservoir, but it gains a wide variety of visitors that assist with pollen transfer. These nectar pools transform each flower into a miniature oasis where many forms of life gather and interact. Some flowers protect their seeds with chemical armor. Certain plants guard their developing seeds by surrounding them with potent chemical barriers. These compounds accumulate in tissues that wrap around the seed, creating a protective zone that discourages herbivores, fungi, and insects from invading. The chemicals may taste bitter, produce mild irritation or inhibit the growth of bacteria. As the seed matures, the concentration of these compounds increases until the protective tissue becomes a kind of shield. Once the seed is ready for dispersal, the chemical armor shifts in composition so that decay or digestion becomes easier when the seed reaches the correct SAF environment. In this way, the plant ensures survival at 2 stages. First, it keeps threats away during development. Later, it supports germination by allowing the protective layer to break down only under the right conditions. This approach allows the species to protect its future without investing heavily in thick walls or hard shells. Chemistry becomes the seed's first defense and its final key to safe emergence. There are flowers that form labyrinths for insects to navigate. Some blossoms create elaborate internal pathways that twist, rise, and curve in ways that guide an insect through a controlled journey. Instead of offering direct access to nectar, the flower builds a chamber filled with small ridges, folds, or spiral passages. As a pollinator enters, it must follow these routes, brushing against pollen-coated surfaces positioned at precise angles. The maze ensures that the insect cannot move too quickly or reach the reward without completing the path. These guided journeys also discourage nectar thieves that are not strong or agile enough to navigate the structure. The labyrinth may vary in complexity between species, but the purpose is always the same. The plant regulates how each visitor interacts with its reproductive parts. These intricate floral designs show how structure alone can create a step-by-step process that transforms a simple visit into an effective pollination event. Some flowers offer shelter to cold pollinators overnight. In chillier climates, certain blossoms become resting places for insects that struggle to maintain body warmth after sunset. Their petals form soft, insulating chambers that trap heat absorbed during the day. Inside these spaces, the temperature remains higher than the surrounding air, allowing pollinators such as small bees or beetles to survive the cold night. The flower gains an advantage as well. When the insect awakens in the morning, it often feeds immediately on the nectar, brushing against fresh pollen and carrying it to nearby blooms. Some flowers even close slightly at night, creating a barrier that shields their guests from wind and frost. This quiet hospitality strengthens the relationship between plant and pollinator, ensuring that both benefit from the arrangement. The blossom becomes not only a food source but a refuge, providing comfort and safety within its fragile-looking walls. A few flowers build petal structures that function like ladders. Some species construct their petals with stepped ridges or tiny protrusions that resemble miniature ladders. These structures help insects climb toward the nectar, especially in plants with deep floral chambers. Without the ladder-like supports, many pollinators would slip on smooth surfaces and fail to reach the inner region. The ridges also ensure that visiting insects position themselves in ways that align perfectly with the anthers and stigmas. As the insect ascends or descends the petal steps, pollen transfers with impressive precision. The design can accommodate creatures with a variety of body sizes and leg shapes, making the bloom accessible to more than one type of pollinator. The plant benefits by increasing the number of successful visits while reducing damage that might occur if insects scraped their way upward. These textured petals show how a simple structural change can transform a blossom into an efficient, visitor-friendly environment. Some flowers time their scent release with pollinator peak activity. A number of flowering species release fragrance according to strict schedules tied to the behavior of their preferred pollinators. Internal biological clocks control when scent molecules are produced and how quickly they evaporate into the surrounding air. If a pollinator becomes active at dawn, the flower increases its fragrance just before the first light appears. If the pollinator comes out at midday, the bloom saves its energy until the sun stands high. These rhythms require finely tuned chemical pathways that respond to cycles of light and temperature. The timing also prevents waste, since producing scent constantly would drain valuable resources. By coordinating fragrance with pollinator routines, the plant ensures that each scent plume reaches its intended audience while avoiding attention from creatures that might cause harm. This optimized schedule turns scent into a precise communication tool built on the quiet movements of time itself. Certain flowers turn their blossoms to face approaching bees. There are blossoms that shift their orientation slightly when they sense the vibrations produced by nearby bees. These flowers move by altering internal water pressure within specialized cells that can stiffen or relax the petal base. The adjustment is subtle, yet it places the blossom in the most accessible position for a smooth landing. Turning toward the visitor increases the chance that pollen-carrying parts of the bee will make direct contact with the reproductive structures. It also reduces the risk that the bee will collide awkwardly with the petal edges and retreat without entering. The movement happens swiftly once the flower detects the correct vibration signature. Other environmental noises do not trigger the same response. This selective turning highlights an advanced form of sensitivity where the blossom recognizes the presence of its main pollinator before direct contact even occurs. Some flowers can sense when nectar thieves arrive. A few species detect when an animal attempts to take nectar without contributing to pollination. These intruders may pierce the side of the flower or slip into the chamber without touching the pollen-producing structures. The plant responds by reducing nectar production or thickening the fluid so that it becomes harder to rob. Some blossoms close slightly around the opening, forcing the intruder to work harder or abandon the attempt. These responses rely on mechanical sensors built into the floral tissue. When pressure or movement patterns differ from those of legitimate pollinators, the flower activates its defenses. By discouraging nectar theft, the plant preserves valuable resources for partners that assist with its reproductive success. This awareness shows that flowers can distinguish between helpful visitors and unhelpful ones through simple yet effective sensitivity. There are flowers that grow exclusively on one hidden cliff or canyon. Certain species exist in extraordinarily limited habitats, confined to a single cliff face, canyon wall, or isolated rock shelf that meets their precise needs. These locations may offer unique conditions such as mineral-rich water seeping through limestone, a narrow band of temperature stability, or wind patterns that protect delicate stems from damage. The flowers growing in these secret locations often develop features unlike any found in nearby regions. Their roots anchor into cracks formed generations ago, and their seeds disperse only short distances because the surrounding terrain provides no suitable foothold. Many of these species remain unknown to science for long periods because their habitats are difficult to reach. The survival of these specialized blossoms depends entirely on the stability of the small environments they occupy. Their existence demonstrates how deeply plants can adapt to specific places, forming delicate living communities that cling to the quiet edges of the world. Some flowers use micro-vibration to dislodge pollen. Certain blossoms rely on finely tuned vibrations to release their pollen. Their anthers hold the grains inside narrow chambers that do not open on their own. Instead, they wait for a very specific frequency of vibration produced by the wing beats or body movements of visiting insects. When a pollinator lands and begins to buzz, the vibration passes into the flower's structure. The tiny shaking loosens pollen grains and sends them out in a controlled burst that coats the visitor with remarkable precision. This process prevents random loss of pollen in wind or rain and ensures that the grains fall directly onto the body parts most likely to touch another bloom. Different species respond to different frequencies, which means only certain insects can trigger the release. The system works like a living lock and key, matching the flower's needs with the abilities of its partners. The precision of this method allows the plant to conserve energy by producing only the amount of pollen that will actually be used. Micro-vibration pollination is one of the most delicate forms of communication between plant and animal, carried out entirely through gentle sounds, tiny movements. Certain flowers build nectaries with multiple chambers. Inside some blossoms are nectaries divided into small, interconnected pockets that store different concentrations or types of liquid. These chambers work together to create a complex structure that controls how a visitor moves through the bloom. When a pollinator inserts its feeding organ, it must navigate through a sequence of chambers, each offering a slightly different taste or texture. This pathway naturally positioned the insect for maximum contact with pollen-producing surfaces. The design also slows down feeding, preventing visitors from draining the nectar too quickly. Some chambers refill faster than others, allowing the flower to ration its resources while still providing a satisfying reward. The architecture may even influence which species can reach the inner compartments, ensuring that only the most effective pollinators complete the journey. This multi-chamber system demonstrates how flowers use internal spatial design to shape behavior. The bloom becomes a guided environment where every turn supports the plant's reproductive success. Some flowers use vibrant metallic pigments visible only up close. A few species develop pigments that produce shimmering colors that shift with the angle of light. These pigments create effects that resemble metal or polished mineral surfaces. To the human eye, these blooms may look ordinary from a distance, but up close, the petals reveal intricate optical patterns that catch attention instantly. Pollinators that approach from nearby see these metallic flashes as strong visual cues. The pigments are formed by layers of cells that reflect light selectively, creating tones that move from gold to copper to blue as the insect circles the blossom. These shimmering patterns may indicate nectar availability or signal that the flower is fresh and ready for pollination. Because the effect is visible only at close range, it encourages insects to approach deeply rather than hovering uncertainly. This adaptation allows the plant to reserve its strongest signaling tools for the final moments before contact, guiding pollinators with precision while bow, conserving energy on long-distance displays. There are flowers that host microbial allies inside their petals. Within the hidden tissues of certain blossoms live microbial partners that perform important tasks for the plant. These microbes may consume harmful pathogens, stabilize nectar chemistry, or produce subtle scents that help attract pollinators. The relationship forms through mutual benefit. The microbes receive a protected habitat rich in nutrients, while the plant gains services that improve its overall reproductive success. Some species adjust nectar acidity to support specific microbial communities that produce helpful compounds. Others create tiny pockets inside their petals where these microorganisms can thrive without being washed away by rain or disturbed by visitors. The presence of these allies can influence the taste and texture of nectar, creating unique profiles that certain pollinators come to prefer. These partnerships reveal an intricate layer of cooperation taking place inside each bloom. The flower becomes a living home that supports more than one kind of organism, forming quiet alliances that strengthen its ability to survive and reproduce. Some flowers bloom in colors humans cannot see. There are blossoms that display hues outside the range of human vision. These colors lie in ultraviolet regions that insects perceive clearly. To a bee, the petals may shine with bright patterns, stripes, or halos that guide it toward nectar and pollen. To humans, the same blossom may appear pale or plain. The pigments responsible for these invisible colors form when the plant creates compounds designed specifically to reflect ultraviolet wavelengths. These compounds also protect the flower from harsh sunlight by absorbing damaging rays. Ultraviolet patterns help pollinators distinguish between fresh and depleted blooms because the markings often fade as the flower ages. This visual language exists outside our perception that plays a major role in the daily interactions between flowers and insects. The world of color becomes far richer when viewed through eyes built to recognize wavelengths that our own cannot detect. Certain flowers produce nectar that glows faintly in the dark. In some regions, nighttime pollinators navigate using scent and subtle reflections of moonlight. A few flowers enhance this process by producing nectar that emits a soft bioluminescent glow. The glow arises from chemical reactions that release light as molecules break down within the nectar. The illumination is gentle, often visible only in very low light conditions, yet it provides enough brightness to attract moths and other nocturnal insects. The glowing nectar sits in shallow pools or along narrow channels that lead visitors deep into the bloom. The plant uses this luminous signal sparingly because producing bioluminescent compounds requires energy. The result is a nighttime display that appears only during peak pollinator activity. These glowing nectars transform the darkness into a quiet, shimmering world, where each bloom becomes a guiding lamp for the creatures that depend on it. Some flowers use scent decoys that mimic insect pheromones. Certain blossoms release chemical signals that imitate the pheromones used by insects to communicate with each other. These signals may resemble the scent of a mate, a nesting site, or a fresh food source. When an insect approaches, expecting something familiar, it instead encounters the bloom. During the investigation, it brushes against pollen-producing structures and transfers grains to its body. The plant gains pollination without offering nectar or any other reward. The decoy does not last long because insects learn quickly to ignore false signals. However, the strategy works effectively during the short blooming periods of these species. The scent molecules are produced with remarkable precision, matching not just the general aroma but complex blends that insects use to locate partners. This method allows the plant to communicate in a language that another species already understands, bending that language toward its own needs. There are flowers that share pollinators through complex negotiation tactics. In some ecosystems, multiple flowering species rely on the same pollinators. Instead of competing blindly, they develop strategies that allow them to share these visitors in a coordinated way. One plant may bloom early in the day, another at midday, and another in the late afternoon. Their colors may contrast so strongly that pollinators can move between them without confusion. Some species adjust nectar volume based on how frequently the pollinator visits each type of bloom. If the pollinator begins favoring one species too heavily, another species may increase scent output to attract attention back. These subtle adjustments create a dynamic balance. No single plant dominates entirely, and pollinators receive a continuous sequence of resources. This quiet negotiation takes place without conscious choice. It unfolds through natural selection, shaping traits that support coexistence. The result is a network of interactions where every species gains stability by recognizing the presence of others. Some flowers shape air currents to carry their pollen farther. The architecture of certain blossoms is designed to influence the movement of surrounding air. Their petals form channels that direct breezes across the anthers, lifting pollen into rising currents. Some petals have curved edges that funnel the air upward, helping the pollen travel above ground level where winds are stronger and more consistent. The bloom itself becomes a small aerodynamic structure that uses the motion of the atmosphere as a tool. This strategy benefits plants that have fewer pollinators available or that live in open habitats where wind is a reliable partner. The guided airflow also helps avoid losing pollen to surfaces that would trap or damage it. By shaping the wind rather than relying on it passively, these species increase the distance over which their pollen can travel. Air becomes a carefully managed resource rather than a random force. Certain flowers produce wax coatings to survive extreme heat. In scorching environments where sunlight and high temperatures threaten delicate tissues, some flowers develop thick, waxy coatings across their petals. These coatings reflect a portion of incoming sunlight and reduce water loss through evaporation. The wax forms a smooth barrier that prevents heat from penetrating too deeply into the flower. Some coatings even carry a faint reflective sheen that cools the bloom by bouncing light away. During the hottest hours of the day, This barrier keeps pollen viable and protects nectar from drying out. The coating may soften slightly in lower temperatures, allowing the petals to open fully when conditions are safe. This adaptation enables the plant to bloom in places where heat would otherwise destroy reproductive structures. Wax-coated flowers show how resilient a blossom can become when shaped by an environment that tests every vulnerable surface. Some flowers create spiral petal patterns with mathematical precision. Within certain species, petals grow according to strict numerical relationships that produce spirals identical to patterns found in shells, hurricanes, and galaxies. These flowers rely on growth zones located at the center of the bud. As the petals form, each new one emerges at a specific angle from the previous one. This angle repeats through the entire bloom, creating spirals that follow mathematical ratios found widely in living systems. The spiral arrangement helps the flower distribute sunlight evenly across its surface and reduces overlap that could block important tissues. The pattern also influences how pollinators land and move across the bloom. As they follow the natural curves created by the petals, their bodies encounter the reproductive structures in predictable ways that increase pollen transfer. The spiral design is not simply decorative. It serves practical purposes connected to light, airflow, and movement. By shaping itself according to these timeless patterns, the flower becomes a living expression of order that nature repeats across many scales. There are flowers that use natural buoyancy to float upright. Some aquatic blossoms stay perfectly upright on the surface of still water because their tissues contain pockets of air that create natural buoyancy. These pockets form between layers of petal cells and within specialized structures at the base of the bloom. When the flower rises to the surface, the trapped air keeps it level and stable even when gentle ripples move across the pond. The upright posture helps the blossom display its colors and scents more clearly to visiting insects. It also keeps pollen dry and accessible. The buoyancy allows the flower to expand fully, without being weighed down by moisture. If wind pushes the blossom sideways, the flexible stems and floating tissues guide it back into position. Some species even adjust the distribution of air within their tissues as they age, maintaining balance throughout the blooming period. This ability transforms the water from a potential hazard into a supportive stage. Some flowers store heat from the previous day. In environments where nights become cold quickly, certain blossoms gather warmth during daylight hours and hold it through the evening. Their petals contain dense tissues that absorb solar energy slowly. This stored warmth radiates gently throughout the night, keeping the inner chambers of the flower at a stable temperature. The heat protects pollen grains that would otherwise lose viability in sudden drops of temperature. It also offers comfort to insects that shelter inside the bloom. When morning arrives, the retained warmth encourages early activity in visiting pollinators that are drawn to the inviting microclimate. This adaptation helps the plant begin its daily cycle earlier than nearby species, gaining more time for successful pollination. Storing heat requires careful control of water content, tissue density, and cellular arrangement. The result is a quiet thermal reservoir built entirely through growth and structure, allowing the bloom to thrive despite fluctuating temperatures. Certain flowers form camouflage patterns that hide them from grazers. Not all blossoms seek attention. Some must conceal themselves from grazing animals that might eat the flowers before they can mature. These species develop petal patterns that mimic the appearance of surrounding leaves, rocks, or soil. The colors blend into the environment so effectively that the bloom becomes difficult to spot from a distance. Some flowers even create markings that resemble shadows or light speckles found naturally on the forest floor. When a grazer passes, the flower remains unnoticed while quietly carrying out its reproductive tasks. The camouflage also protects the plant from insects that feed on petals rather than nectar. By blending into their surroundings, these blossoms reduce unwanted interactions and conserve the energy needed to repair damage. The patterns develop as the petals grow, guided by pigments arranged in subtle gradients and textures. The bloom becomes a master of invisibility, surviving by remaining unseen. Some flowers bloom in sequence to guide pollinators through a habitat. In certain landscapes, multiple blossoms of the same species open in a carefully timed order. Plants at one end of the habitat bloom first, followed by those farther along a natural path such as a stream, ridge, or meadow edge. Pollinators follow the unfolding wave of blossoms as they move through the area in search of fresh nectar. This blooming sequence directs the insects from one plant to the next, ensuring that pollen travels across long distances. The strategy increases genetic diversity and reduces competition among individual flowers, since each one receives attention in its own window of time. Opportunity. Internal timing mechanisms within the plant respond to small differences in temperature, soil moisture, or sunlight exposure. As a result, each individual knows when to open in harmony with the landscape. The flowering wave becomes a coordinated journey that supports both plant and pollinator. A few flowers grow petals that function like nets. Some species develop petals with interlaced fibers that create delicate net-like structures. These fibers stretch across gaps or openings within the bloom, forming surfaces that are strong enough for insects to grip, yet flexible enough to move with the visitor's troughs. Wait. The netting helps guide the pollinator toward the nectar chamber by creating surfaces that direct its movement. Small creatures cannot slip through the openings, and larger ones must step carefully across them. As they do, they rub against pollen-covered structures arranged below the net. The plant uses this design to position the insect precisely where contact is most effective. The net also helps protect the flower from rain by breaking droplets into smaller amounts that slide away instead of collecting in the bloom. The result is a functional lattice built from living tissue that supports movement, protects delicate areas, and enhances pollination accuracy. Some flowers change their nectar volume according to visitor frequency. Certain blossoms monitor how often pollinators arrive and adjust their nectar production accordingly. If visits are frequent, the plant produces smaller amounts of nectar to conserve energy. Pollinators that already know the bloom will continue to return even when the reward is modest. If visits decline, the flower increases the volume or richness of the nectar to attract new attention. This dynamic adjustment requires sensory mechanisms that detect physical contact or subtle changes in pollen removal. The plant uses this information to determine how much nectar to produce in the following hours. The result is an efficient system that balances resource use with reproductive needs. The flower never wastes nectar during periods of heavy visitation and never leaves itself unnoticed when activity slows. This adaptive strategy reveals how closely flowers monitor their surroundings and how rapidly they can respond through internal chemical pathways. Certain flowers build hollow petals that act like resonating chambers. Some blossoms create petals with interior cavities that trap and amplify sound. When small insects hover nearby, the vibrations from their wingbeats enter these hollow spaces and produce slight echoes. The heightened sound helps pollinators locate the bloom in dense vegetation where visibility is low. The resonance also alerts the flower to the presence of a visitor, allowing it to prepare pollen or adjust nectar concentration. These cavities must maintain a specific shape and thickness to produce the right acoustic effect. They fall naturally as the petals close around small pockets of air during development. The echo produced inside the hollow petal is subtle to human ears, but clear to many insects that rely on sound for navigation. By enhancing acoustic signals, the flower communicates within a sensory world often overlooked. Some flowers emit scents that travel vast distances on wind cones. There are species that create fragrance molecules so light and volatile that they drift for great distances across open landscapes. These scents rise with warm air currents during the day or travel along cooler ground layers at night. Pollinators detect the aroma from far away, and follow the scent trail until they reach the bloom. Producing such long-range signals requires the plant to invest in compounds that evaporate easily yet remain stable over time. The fragrance often changes subtly as it moves through the air, creating a gradient that helps insects determine direction. By sending scent across distances, these flowers compensate for living in sparse environments where pollinators are few. The bloom becomes a beacon carried by the wind. There are flowers that develop only after many years of dormancy. Some species wait through long stretches of time before producing their first blossom. During these years of dormancy, the plant stores energy in underground structures and builds nutrients slowly through modest growth. It does not risk flowering until conditions reach a combination of moisture, warmth, and soil richness that supports successful reproduction. When the moment arrives, the plant directs its stored resources into one intense blooming event. The flowers may appear in great numbers across a habitat, where they remained hidden for many seasons. Pollinators respond quickly to this sudden abundance. After the bloom fades, the plants return to their quiet underground existence for many more years. This strategy reduces the risk of flowering in unfavorable conditions and ensures that each bloom has the best possible chance of attracting attention. Some flowers build deep underground tubers that feed their blooms. There are flowering plants that create large underground tubers acting as long-term reservoirs of water, minerals, and stored energy. These tubers remain hidden beneath the soil while the surface environment shifts through seasons of drought, heat, and unpredictable weather. When the time to bloom arrives, the plant draws from this underground storehouse to produce blossoms that seem almost impossible for such harsh conditions. The tuber supplies steady moisture even when rainfall is scarce. It also provides starches that fuel rapid growth of stems and petals. Because the tuber remains insulated underground, it endures extremes that the rest of the plant cannot. Some species use these reservoirs to produce spectacular blooms after long periods of complete dormancy. The flower that appears above ground is often the smallest part of the organism, supported entirely by the strength of its hidden root structure. This approach gives the plant freedom to survive in regions that swing between abundance and scarcity. The bloom becomes a brief display powered by years of stored sunlight and careful patience beneath the earth. Certain flowers release mist like aromas that hover close to the ground. A number of blossoms create fragrances that behave differently from typical floral scents. Instead of rising into the air, these aromatic molecules cling to cooler pockets of atmosphere close to the soil. The scent spreads like a thin mist that drifts along ground level rather than lifting upward. This effect forms because the molecules are heavier and condense more readily in cooler layers of air. Many ground-dwelling insects travel within these layers, following scent trails that drift across leaf litter and low vegetation. The plant designs its fragrance to remain exactly where its preferred pollinators live and move. The mist-like aroma can collect in small hollows where air remains still, forming scent pools that guide visitors toward the bloom. Because the fragrance does not rise quickly, the plant uses far less energy to maintain it. This focused distribution creates an intimate pathway between the flower and the creatures that navigate the quiet world near the earth. Some flowers form secret chambers where seeds mature safely. Within some species, the flower develops a protective chamber deep inside its structure that serves as a safe room for maturing seeds. This chamber shields the developing offspring from herbivores, insects, and harsh weather. Its walls may thicken over time or accumulate compounds that discourage pests. The interior remains stable, maintaining humid conditions that support early seed growth. Once the seeds reach the appropriate stage, the chamber slowly opens or splits, releasing them into the environment. Some plants create chambers that stay sealed until triggered by precise environmental cues, such as rainfall or warmth. This ensures that seeds enter the world at the moment when survival is most likely. The development of hidden chambers transforms the bloom into both a reproductive display and a fortress. The flower becomes the first guardian of the next generation, using structure and chemistry to protect the tiny life waiting inside. There are flowers that use surface tension as a pollination mechanism. A few remarkable blossoms rely on the physics of surface tension to transfer pollen. They produce small droplets of liquid that cling to the tips of their anthers. When a visiting insect touches the droplet, the surface tension pulls it toward the insect's body, carrying pollen grains with it. The liquid spreads across the insect in a thin film that evaporates quickly, leaving the pollen securely attached. Some blossoms position these droplets along narrow channels that amplify the effect, guiding each droplet's movement with surprising precision. The method works even in gentle breezes, because the droplets remain anchored until touched directly. This approach allows the plant to deliver pollen without relying on powder that could drift away. By using water-based physics to its advantage, the flower ensures that every contact becomes a meaningful exchange. It is a finely tuned partnership between biology and the smallest forces of nature. Some flowers create entire microhabitats for ant colonies. Certain plants build blossoms that support full communities of ants living within or around their flowers. These ants receive shelter in small cavities or hollowed structures that form naturally as the bloom develops. In exchange, the ants defend the flower from harmful insects that might chew on petals or steal nectar without helping with pollination. The ants patrol continuously, removing pests and keeping the surface clean. The flower sometimes produces tiny droplets of sugary liquid specifically for the ants, strengthening their loyalty. As they move across the petals, the ants may also accidentally transfer pollen from one bloom to another. Although they are not the primary pollinators, their presence creates a protective environment that allows legitimate visitors to feed safely. The relationship becomes an intricate example of cooperation between plant and colony. The flower provides a miniature home, and the ants provide security, forming a small world of activity around each bloom. Certain flowers build curled funnels that spin pollinators gently. Some blossoms shape their petals into curved funnels that create a spiraling path toward the nectar. When a pollinator enters the funnel, the smooth curves guide it through a gentle rotation. This slow turning motion positions the insect so that pollen-coated surfaces brush against specific parts of its body. The funnel narrows near the center, ensuring that the pollinator moves close to the reproductive structures before reaching the reward. The swirling pathway prevents quick escapes and encourages a longer visit. The experience is not uncomfortable for the insect. Instead, the curve of the petals works with its movements, allowing it to glide naturally along the spiral. This design increases the chances of successful pollination and reduces the amount of nectar the plant needs to produce. It transforms the bloom into a fluid, dynamic environment where shape controls the flow of each interaction. Some flowers emit scents that change dramatically with temperature. A number of species release fragrances that shift in character depending on the warmth of the surrounding air. At cooler temperatures, the scent may be light, gentle, or slightly sweet. As the air warms, the plant activates enzymes that convert certain molecules into others with stronger or more complex aromas. The scent may become richer, deeper, or more noticeable from greater distances. These changes help the flower coordinate with the activity patterns of its pollinators. Insects that move during cooler hours receive subtle hints of the bloom, while those active in hotter conditions follow stronger trails. The temperature-dependent scent also prevents excessive fragrance production when it would evaporate too quickly. By aligning aroma with the rhythms of the day, the flower ensures that every molecule of fragrance serves a purpose. The bloom communicates in a shifting language shaped entirely by heat. As we come to the end of our rainforest journey, you can let the images settle like warm mist in your mind. We wandered beneath towering canopies where sunlight breaks into small, drifting patches. We followed the sense of layers, from shadowed forest floor to the high, bright leaves, and we listened for the way life fills every opening. In a rainforest, nothing is wasted. Water moves in patient loops, rising and falling, feeding roots, leaf and cloud. Sound travels differently there too, softened by green distance, as if the forest is always holding its own breath between raindrops. You may have noticed how the rainforest feels both ancient and busy, a place of constant exchange. Threads of connection run everywhere, through soil and sap, through flight and footfall, through the slow work of growth that never truly stops. Even when the air is still, the forest is making and remaking itself, moment by moment. If you're still awake and you'd like to keep drifting with us, there will be another video waiting on your screen. You can follow it like a lantern along a dark path, one calm step at a time. And if these bedtime science journeys are part of your routine now, you might consider liking, subscribing, or leaving a comment. It helps more tired minds find their way here. For now, you do not need to hold on to anything. Let your jaw unclench. Let your tongue rest. Let your breathing find a slower rhythm that feels easy to keep. Allow the rainforest to fade into a hush of leaves and distant rain, and let your thoughts thin out as sleep comes closer. Sleep well, and good night.